Oh, it's toasty in here, huh? Right, so I find myself in front of some kind of a middle-sized black hole. And that's because today's compilation video is going to be about black holes. Now currently I'm taking a bit of a short break because my voice is actually not doing so well and I think I might have caught something. In the meanwhile, enjoy some of the older videos, some of the longer compilations, and I'll see you soon. Hello wonderful person, this is Anton, and today we're going to be discussing this pretty interesting and somewhat unexpected discovery of what seems to be a supermassive black hole that instead of destroying stars and instead of consuming matter, seems to be responsible for actually creating new stars and doing so extremely actively in this particular galaxy not so far away from us. And that's of course something that has never really been seen before, even though certain theories in the past have proposed this being possible. And so let's talk a little bit more about this and what all of this means, and also learn a little bit more about the details from the paper that as always you can find in the description below. First of all, where exactly is this located? This is in a dwarf galaxy known as Hyades 2-10. The dwarf galaxy that sort of looks like this, and as you can probably see from this image, possesses some extremely bright features here and there, and that's because this is what's usually referred to as the starburst galaxy. A galaxy known to possess a huge amount of different star-forming regions and generally displaying some very beautiful features all across the galaxy itself. And a lot of theories today suggest that these starburst galaxies are usually the result of some sort of a galactic collision or massive galactic interaction where suddenly a lot of gas starts to be condensed in certain regions of the galaxy, which then results in very thick clouds, which then produce various regions where stars form. And this particular galaxy is also somewhat unique because it's a type of a starburst galaxy that we sometimes refer to as a Wolf-Rayet starburst galaxy. Wolf-Rayet stars are really interesting and very intriguing, and there's actually a video about this that might have already come out and should be available either in the description below or somewhere above me, and it kind of explains a little bit more about these particular stars. But in essence, this represents an extremely active region with massive amounts of gas forming lots of stars and extremely massive, very large stars, very similar to what's happening in the nearby Large Magellanic Cloud. Some of the most extreme stars and some of the most massive, brightest, and also most energetic stars nearby are all located in the Large Magellanic Cloud in a region known as the Tarantula Nebula. And so this is very similar. There are a lot of these really huge, massive, very active stars, some of them potentially hundreds of masses of the Sun. And that's kind of what you see here, except that obviously this is much farther away. The distance to this galaxy is about 34 million light years away from us. And originally when the scientists discovered this object, because of its relatively small size, they actually thought this was a nebula much closer to us. And it wasn't until 1970s when the scientists officially confirmed that this was actually a galaxy. But because it was thought to be some sort of a planetary nebula, it received the name of Hyades 2-10 because the American astronomer Carl Hyades was responsible for creating a database with this particular galaxy becoming one of the members. Anyway, today we know that this is definitely a galaxy, and a very intriguing galaxy. And back in 2011, so basically about 10 years ago or 11 years ago, the scientists studying this galaxy in more detail identified a relatively massive black hole somewhere in the region right here. The black hole that was most likely approximately 3 million masses of the Sun. And that's actually surprisingly massive for such a small galaxy. It's actually somewhat similar in mass to what we have in the Milky Way galaxy, even though the Milky Way possesses approximately 10 times more stars. And this is unexpectedly massive for a dwarf galaxy. The only other dwarf galaxy that I know of where a massive black hole was discovered is the recently identified black hole in the middle of the Leo 1 dwarf galaxy not so far from the Milky Way. But this is of course an exception, not the rule. We don't expect these massive black holes inside these galaxies, so already quite a big mystery. And the presence of such a big black hole in such a small galaxy kind of already suggests that maybe these black holes were formed before the galaxies were even created. So that potentially explains some of the mysteries of their origin. But that's not really what we're talking about. Normally we expect these massive black holes to also, especially when they're active, be responsible for, well, basically stopping star production. The proper term for this is quenching. Star quenching is when a massive black hole becomes active, and it obviously becomes active when something like this happens, so either a star or a really massive cloud of matter starts to fall into the black hole and then forms a really large accretion disk, and most importantly these really large outflows astrophysical jets as they're known, coming from both sides of the black hole, which then ends up producing huge effects such as, for example, galactic winds that spread through the entire galaxy, heating up the gas and preventing further star formation. Now this is the general explanation for why many galaxies, many active galaxies, completely stop star production and end up remaining somewhat quiet for a very long time until something else happens, for example, another galactic collision or some other disturbance. But that's not really what's happening in this galaxy at all. In this case, when this black hole became active, it had a practically opposite effect. The actual streams coming from the jets seem to have triggered star formation that's clearly visible in the region you see right here, with the star formation following the actual shape of the jet. So there are actually several different star forming regions along this line, and really big one here. This is actually forming what's known as a superstar cluster, which is sort of like the precursor to a lot of smaller clusters or a lot of other globular clusters that usually form in galaxies. And all of the stuff here seems to be relatively young, possibly 4 to 5 million years old, with the images produced by the Hubble telescope quite clearly showing us that the gas stretching here is definitely produced by the black hole in the middle. With the scientists even sort of comparing this to a kind of an umbilical cord that seems to stretch from the black hole to the star-forming region, which I guess is somewhat symbolic in a sense. Because it seems to be the only black hole we know of that's physically forming new stars through the emissions from its jets. But how exactly is any of this happening, and most importantly, why is it that we're not seeing any of this in other galaxies? Well, the answer to this is very likely because of the power involved. Unlike other powerful emissions, such as for example from quasars or some other really powerful galaxies with very massive black holes in their center, the power of the jets here is a lot weaker. Even the material seems to be moving a lot slower. And so all of this material coming from the black hole is actually hitting this huge relatively dense cloud that already existed here, most likely at speeds of about 500 kilometers per second, not at relativistic speeds as it usually would be happening. Also, the distance here is approximately 230 light years, so this is happening somewhat farther away from the black hole itself, and possibly far enough not to be affected by other things close to the black hole, but close enough and packed enough to sort of stay as a single cloud and not to fly apart. And so because this particular black hole is not too active and not too massive, and also because it didn't really produce these very powerful emission effects, all of this seems to suggest that in some cases, instead of stopping star forming activity, some black holes, if the conditions are just right, actually create more stars in the process. With I guess one requirement in this case being just in the right place and having just the right density of all of this primordial gas in order for it to then start sort of clumping together and produce new stars. In other words, because this is the only galaxy we know of where this is happening, it seems to be relatively rare. But chances are we're definitely going to be finding more of these, and more importantly, it might even help us understand a little bit more about our own galaxy and our own central black hole as well. For example, in some of the previous videos, I've mentioned how the scientists clearly identified signs of star formation happening not so far from the Milky Way central black hole, Sagittarius A star. And on top of this, there have also been signs of somewhat medium size or medium power activity from the central black hole. Now, is there some sort of a connection? Is it something similar that might have happened in the Milky Way galaxy? And could all of this have possibly created these stars? Well, right now we don't obviously know, but the implication from this study is actually somewhat intriguing. More importantly, by studying this particular galaxy, the scientists are really hoping to finally understand how such massive black holes have actually formed in the universe. Right now, the creation and the formation of supermassive black holes is still a bit of a mystery. We still really don't know if they were formed possibly before the matter solidified, and possibly from some sort of a primordial matter that existed early in the universe, or if they formed from the collection of early stars, or if they might have formed in some other way. But by studying galaxies like this, and learning a little bit more about how black holes grow here, all of this could become more clear. So definitely a pretty interesting galaxy and a pretty interesting discovery. Actually, some other discoveries here also suggested that this galaxy has recently experienced some sort of a collision, which could explain the star formation. Most of this is due to the detection of a tidal tail that seems to stretch somewhere right here. But that's not something that would be unexpected. Galactic collisions happen all the time. However, detecting a black hole that seems to be causing several star-forming regions that you see all over the place here, that's of course another story. In the last few years, there have been several announcements suggesting a potential discovery of the closest black hole to the solar system. You can find previous videos about this in the description, but in essence, it became one of the major challenges for modern astronomy, an attempt to discover a black hole by using modern observations and modern techniques, and by knowing what we know about these unusual objects. And in this case, we're of course talking about smaller, stellar mass black holes that are usually produced by massive stars going supernova, with the average mass of approximately 10 solar masses. We're obviously not talking about giant black holes like the ones in the center of the galaxy. And pretty much every major black hole discovered in the Milky Way galaxy has actually been only found because of its partner. Usually, by absorbing the mass from the partner, a black hole becomes what's known as the X-ray binary. It produces super powerful emissions visible in the X-rays, and very often other frequencies as well, with all of this visible from thousands of light years away. But all of these X-ray binaries are relatively far away, thousands of light years away from planet Earth, and they're also not particularly numerous, compared to the number of black holes we expect in the Milky Way. Our galaxy is expected to hide at least 100 million different black holes because of previous supernova, and only a handful has been discovered so far. But a lot of newer studies try to focus on discovering them by using something else. In this case, either gravitational lensing effects when they pass in front of a star, or by seeing various gravitational anomalies from a star that might be nearby that could be changing its orbit in a somewhat unusual manner. And well, relatively recently, we've discussed one of these discoveries coming from the Gaia telescope. A discovery of potentially the nearest black hole to us, the black hole known as Gaia BH1, the first such black hole confirmed by the Gaia telescope, located about 1600 light-years away. But now we have a new study that seems to present evidence for something possibly much closer. Actually 10 times closer, 153 light-years away. But the evidence in this case is more statistical and not necessarily of the actual observation. So, hello wonderful person, this is Anton. Let's discuss this new discovery and a new announcement in regards to the potentially closest black hole to planet Earth, or maybe even two, once again discovered using Gaia data, but in this case looking at something slightly different. Looking at this. This is the Hyades cluster, one of the most well-known star clusters, located in the constellation of Taurus, at a distance of just over 150 light-years away from planet Earth. But in this case, this is not a globular cluster, it's what's known as an open cluster. A location of active star formation where many different stars were formed as a result of a molecular cloud forming various overdensities collapsing into various stars, representing a somewhat spherical group of several hundred stars, all of them of relatively similar age, similar chemical parameters, and even similar motion across the space. But unlike globular clusters that exist for billions of years, open clusters do not. They actually fall apart, losing mass every few million years. And so normally, after about a billion years, most of them dissolve completely, which is very likely how the solar system began as well, in some kind of an open cluster that existed 4.6 billion years ago. Although there are definitely exceptions. There's a tiny fraction of these clusters that survive for billions of years, with the stars permanently locked in a dance around one another. A few of these have been discovered in the last few years. But when it comes to this Hyades cluster, it's somewhere in the middle. It's approximately 625 million years old, and it definitely already lost a lot of mass, with many stars dispersing across the galaxy. In terms of size, it's about 33 light-years across, but it does actually have a much denser core that's about 8.8 light-years across, representing most of the mass and most of the tightly bound stars. Interestingly enough, today, most of the stars here are relatively small. Anything over 2.3 solar masses has already actually changed into either white dwarf or went supernova, creating a neutron star or a black hole. But the majority of stars here are much smaller in size and in mass, typical red dwarfs or K-type stars. But because this is also the most studied cluster, in the last few years scientists discovered at least 8 confirmed white dwarfs, naturally suggesting that many bigger stars and more massive stars left their remnants in the middle. And that of course implies that there should be, technically, black holes in here as well. black holes that were left behind by some of the most massive stars that very likely existed here over 400 million years ago. And since modern observations are so extremely accurate, finding these black holes has become kind of possible. It's even become possible to find planets here, with one already confirmed around a star known as Epsilon Tauri. And so by focusing on motions of stars in this cluster, the researchers behind this paper performed various computer simulations in order to compare the results from simulations to physical observations from the Gaia telescope. And the focus in this case was on actual positions and velocities of stars inside the Hyades cluster, which because of Gaia telescope have been measured with extreme precision in the last few years. For example, here's what the motion of these stars looks like according to Gaia telescope. And when the results were compared, the positions and the velocities did not necessarily match up. But they did match very well once you introduce at least 2 to maybe 3 black holes of the stellar mass type, basically the ones similar to Gaia BH1. And so in other words, by trying to simulate the results and compare them to the physical observations, they realized that there may be something hidden inside of this cluster, changing the orbits of stars overall. And the best match was if there were 2 or maybe even 3 stellar mass black holes right in the center of the cluster. Which of course should not come as a surprise, because white dwarfs have already been discovered here as well. But unlike white dwarfs, black holes are obviously invisible. And naturally, if confirmed and if this is correct, this would be the closest black holes discovered so far, and possibly even some of the closest black holes in general. It would be extremely difficult to find anything closer, and within about 150 light years away from us, no binary systems are known to us potentially hosting something massive and invisible. And so the black holes inside this cluster could definitely be the closest. But exactly where they are, or even if they are here, is really not a question we can answer anytime soon, because at the moment there's just no way to confirm them, unless somehow one of them makes itself known, either by suddenly absorbing a lot of mass and emitting a lot of X-rays, or by passing in front of one of the stars and producing gravitational lensing effects. These types of effects can be observed by some of the future telescopes like the Nancy Grace Roman telescope, but it's not possible just yet. And so until these future discoveries, at least for now, this is definitely a pretty strong contender for the location with the closest black holes to planet Earth. Hello wonderful person, this is Anton, and today we're going to be talking about black holes once again, because yet another study might have found a resolution to a relatively old mystery. The mystery of the origin of certain supermassive black holes, or more specifically, how smaller black holes, these so-called intermediate mass black holes, can with time and through the absorption of a lot of mass, turn into various massive giants we're observing across the universe. With certain black holes, as you know from some of the previous videos that you can find somewhere in the description below, reaching masses of billions of masses of the Sun. That's basically thousands of times more massive than the central black hole in the Milky Way galaxy. But it's always been a bit of a mystery how they grow so large and where exactly they actually form. With the other mystery being the lack of information or the lack of evidence for the existence of the actual process of growth. So basically, what feeds these black holes and does so really fast in order to create these tremendously large giants? The mystery that's been bugging scientists for a very long time. And one of the pieces of this mystery was, of course, the lack of observations in regards to in-between mass black holes, these so-called intermediate mass black holes. The black holes we discussed in some of the previous videos, whose origin only recently became more apparent as we started discovering their signs across the universe. For example, there is an intermediate mass black hole in the middle of this spiral galaxy with a relatively long name, RX J1140.1 plus 0307. And another one probably located inside the globular cluster known as M31G1. But how they formed, and more importantly, how they then turned into supermassive black holes, that's of course the mystery that we couldn't really answer until relatively recently. With the answers finally coming from the observations of the iconic X-ray telescope known as Chandra, the most sensitive X-ray telescope ever produced. The telescope that in the past allowed us to detect some really interesting things happening around distant black holes, such as for example a destruction of a single star, the so-called tidal disruption event. with some of these tidal disruption events even involving some unusual objects, such as a white dwarf that in theory can produce a very powerful explosion that sometimes is referred to as an F-bot. That's of course one of the explanations for how this happens. But in a more recent study, the scientists decided to take a look at 108 different galaxies using both Chandra observations and some of the observations from other telescopes such as the Hubble telescope, to try to compare various dense star clusters with the X-ray emissions coming from those clusters. Because at least in theory, if we detect a really dense cluster that also seems to produce a tremendous amount of X-rays, usually this would imply only one thing. Something really massive is eating up a lot of mass on the inside and is producing all of these X-rays, and the only explanation for this is of course a massive black hole. With all of this also based on theories involving what's known as a nuclear star cluster, NSC for short. Here's one inside our own galaxy, the Milky Way. And these are usually star clusters with very high density and really high luminosity, normally located relatively close to the center of the galaxy. With a lot of these objects resembling a typical globular cluster, and you can learn more about these in some of the previous videos right there or in the description. But normally much denser, containing a lot more stars, and sometimes even mass equivalent to a typical supermassive black hole, millions or sometimes several hundred millions masses of the Sun. And because of this, many stars in these regions will usually orbit around one another, or basically around the central region, very fast. The faster they orbit, the more likely they're going to start colliding and creating a lot of chaos. And so theoretically, if we actually find a bunch of these nuclear star clusters that do have very high velocity of stars within them, what's known as the dispersion velocity, there is actually a high chance that many of them are actively producing very massive black holes. Simply through the process of the central black hole in a cluster, causing a lot of destruction and a lot of chaos, with a lot of matter eventually falling into it and basically causing even more chaos as a result. In the past, the theory predicted that any kind of a nuclear cluster whose dispersion velocity is approximately 40 km per second or higher, or basically where the average speed of stars is 40 km per second, would usually start producing these relatively massive black holes. But this was based on different models and different theories and was never really officially proven or seen anywhere. But now the scientists decided to try to prove this. They took a look at a bunch of different galaxies, 108 as I mentioned, and took a look at certain regions where there are very dense, very highly clustered regions, specifically nuclear star clusters with a lot of really massive stars at high velocities moving around one another, a very high dispersion velocity. In most cases, anything that had velocity of over 40 km per second would always contain a powerful X-ray source right in their center. Without exception, the vast majority of them had something going on, and that something is very likely some sort of an intermediate mass black hole absorbing anywhere from hundreds to even thousands masses of the Sun and growing more massive every year, becoming a supermassive black hole. With quite a lot of these unusual clusters discovered in various galaxies, and some galaxies even containing several in various regions. Which of course means that first of all, intermediate mass black holes definitely exist and definitely grow really fast, and also explains how supermassive black holes come to be and how they can eventually completely destroy various clusters and possibly even collide with the central black hole, giving it even more mass. But one of the more important discoveries in this case is the fact that all of this is happening in galaxies relatively close to us. None of this is in those regions in the beginning of the universe. Which of course suggests that supermassive black holes can even grow to their massive size right now. It's not something that only happened back in the days, and it's not something that's going to stop anytime soon. This definitely seems to be an ongoing process, and it seems to mostly rely on these nuclear star clusters, which very likely then become globular clusters as they lose some of the mass, most likely due to these central black holes. Or maybe it's the other way around. Maybe the collision between various globular clusters and their approach to the central black hole causes them to turn into nuclear star clusters, which then results in the formation of the central black hole that becomes very destructive to the other stars. And because a typical nuclear star cluster seems to contain a mix of young and old stars, this explanation might make a little bit more sense, although the actual nature of these unusual objects is still not entirely clear. But what is clear is that normally they are the most massive and the most dense star cluster objects in typical galaxies. And more importantly, they usually contain some kind of a black hole in the middle, and they also contain enough mass to, in theory, produce a supermassive black hole. And this study seems to definitively show that this is the case. A typical dense cluster with a lot of different stars colliding and moving around really fast will usually have some kind of a central X-ray region with very high power. Very likely some kind of a massive black hole. With the process eventually stopping once there are no more stars left, or once all of this mass sort of solidifies in the center with only some stars remaining on the outskirts. But I guess the important part from all of this is that all of this kind of also connects to some of the previous detections from the iconic LIGO that detected various gravitational waves from objects that seem to be somewhat too massive to exist. So in this case, intermediate mass black holes. And it's actually quite likely that it might have happened in a region very similar to what was seen in the study. So basically some kind of a massive coalition of different black holes and different stars, really massive stars, located in some kind of a nuclear star cluster where a lot of collisions happen really fast and the black holes end up growing faster and faster as they accumulate more mass. But I guess more importantly, the study also proves that we can study supermassive black holes and their growth and their development using some of the nearby galaxies and not just the galaxies at the edge of the observable universe. We can literally look at these nuclear star clusters in any one of these galaxies from the study and try to analyze how black holes grow and what exactly happens to them in order to then turn into these massive giants in the center. Something I'm sure will end up being a new study in the next few years. It's spinning around me. Hello wonderful person, this is Anton, and today we're going to be talking about a pretty interesting discovery, at least in terms of the astronomical achievements. A discovery of yet another very difficult to see black hole somewhere out there in a nearby galaxy known as the Large Magellanic Cloud. And more specifically, it's actually a discovery using an extremely interesting technique. Because as you can probably imagine, by nature, black holes are extremely difficult to find. And so even though we expect millions and millions of them in our own galaxy, we've only discovered a handful. But today we're going to find out a little bit more about this particular discovery and why it's actually somewhat interesting in terms of scientific achievements. Although, let's start with this image right here, because the location itself is also extremely interesting. This location is known as the Tarantula Nebula. It's probably one of the most iconic star-forming regions around us, and it's actually one of the most important astronomical regions to begin with. A lot of really interesting things are happening here at all times. And in this case, we're focusing on the part that you see, which is essentially the star that we're discussing today. And if you've ever seen the image of Large Magellanic Cloud, you probably know that it doesn't really look like a typical spiral galaxy. And it's very likely because it's actively interacting with the Milky Way galaxy and with its partner Small Magellanic Cloud. And because of all of this interaction, it essentially formed these relatively active regions, and one of them is right here. So this region that we refer to as the Tarantula Nebula, with another really interesting region that you can kind of see in the middle, known as R136, is probably one of the most well-known regions in astronomy. This region produces a lot of new stars. Many of these stars are extremely active and extremely massive, and the most massive star ever found, R136A1, is located right there, somewhere in the middle of this. It's not really clear how massive the star is, but it's very likely close to about 300 masses of the Sun, with the R136 region by itself containing several million masses of the Sun as well. And because there are so many massive and very active stars here, it's sort of expected that many of them will go supernova, as one of them has in the past. The most recent nearby supernova was the supernova known as SN 1987, which was detected in 1987. The supernova you can learn more about in one of the previous videos right there or in the description, with a lot more potential supernova happening in the next few hundreds of years. So this region is kind of expected to have these because of the amount of stars being actively generated and sort of creating these massive objects. But at the same time, because of this, because of how we know that stars go supernova and turn into various neutron stars and black holes, we also expect a much higher population of black holes in this region as well. Black holes that could be completely by themselves, or maybe with a small partner, or possibly even absorbing mass from their partner. And when it comes to black holes, there's really only two ways currently of essentially finding them. Either if they're absorbing a lot of mass, like the one doing right here, and then emitting a lot of X-rays and a lot of other really high frequency energy, or if they're orbiting around their partner in just the right way, so that the partner seems to be actually moving as well, around some kind of an invisible object. And so in other words, if we were to take a look at all of these stars, and if we then somehow found a way to see their wobble or their interaction with the nearby objects, and then suddenly we discovered one of them kind of going back and forth regularly, but also around another object that we cannot see, at least in theory, it would imply that we might have found some kind of a black hole. Although obviously, there could be other explanations as well. For example, maybe it's not a black hole, but a much smaller star that we just cannot see. Or maybe the star itself is somewhat unusual and periodic and tends to change its brightness, which kind of makes it appear like something is shifting it around. Which means that the scientists have to be super careful when trying to make these claims. And that's actually what the team behind the study does. They're really good at sort of disputing these discoveries of various black holes. You can learn a little bit more about their discovery in the description below, but they're essentially the team known to debunk various black hole discoveries. They were the ones that debunked the closest black hole to us, a video that you can also find in the description or somewhere right there, explaining that this was essentially just a different type of a star that did not really have a black hole around it, with their overall observations and analysis usually being extremely detailed and very difficult to argue with. But this obviously doesn't stop the scientists from trying again, and from essentially trying to find these so-called dormant black holes. Black holes that are not really emitting much light, they're not producing much energy, and are only interacting with the nearby environment in some very minor ways, with the Tarantula Nebula very likely being the best place to look for these black holes because of the amount of massive stars which we expect to produce black holes to begin with. And this region is extremely interesting for a lot of different reasons. So for example, one of the ways that we think all of this is generated is because of the interaction with nearby galaxies that create what's known as ram pressure. A kind of a pressure in the gas which generates a much thicker wave of material either escaping or moving into a certain region, which then, if it collides into something else, can suddenly start the formation of new stars. For example, the iconic ring galaxies, many of which are still difficult to explain, are believed to be created in a somewhat similar way, where all of the gas escaping the central region collides with something on the outskirts and starts forming these stars that form a ring around the galaxy. Here's actually one of the more iconic images showing us how all of this works. But in our case, it's a much smaller galaxy and a much smaller wave. But it still generates a lot of new stars, and many of these stars then generate black holes. Or neutron stars, like in the case of SN 1987 supernova I mentioned previously. The neutron star was actually only recently discovered. Video in the description. And eventually we believe that these objects might even form what's known as the globular cluster, which will then sort of circulate around the galaxy for billions of years. Although the exact future of these objects is currently unknown. But what we do know is that the region is very active, and obviously produces quite a lot of various types of radiation, including X-rays. And so potentially seeing an X-ray emitting black hole in this case is also somewhat challenging. There's just way too much noise. There is, however, a way for the scientists to see if there is something invisible causing various stars to orbit in unusual ways. And this is actually a technique that was also discussed in a study previously, where the scientists essentially look at the wobble of the star by comparing its redshifts and blue shifts. In other words, if I'm looking at a star and suddenly I see that the star blue shifts or its frequency increases just a little bit, and then red shifts or its frequency decreases, but does so periodically and for no apparent reason, it means that something massive is orbiting around it. And based on the amount of frequency change, it becomes possible to determine the mass of this unusual object. And when the scientists looked at this one particular star, the star that's approximately 25 times the mass of our own sun, and located about 160,000 light years away from us, they've realized that something else is orbiting around it that's about 9 times the mass of our sun. But despite looking for a partner, they couldn't see one. It was an invisible dot in the night skies. And they actually found this after looking at thousands and thousands of stars in this region. and so this is obviously not an extremely common discovery and seems to be kind of rare. According to the scientists, they've actually discovered quite a few of these wobbling objects, but many of them turned out to have some kind of a partner that was then visible. But this binary, VFTS243, appeared to be the only one so far where the wobble is completely unexplained. Or I guess it is explained by a relatively massive black hole, 9 masses of our own sun. But assuming that this is a black hole, which it seems to be at the moment, there is a problem with how exactly did it form. Mostly because there are clearly no signs of any supernova ever happening here. Or the more thorough analysis revealed that it was not created via a typical Type 2 supernova, which we generally believe create these types of black holes 9 masses of the Sun. So if it wasn't a supernova, then how exactly did it form? Well, most likely through the other method the scientists believe may exist as well, the direct collapse. Essentially, a star of a certain mass, upon reaching certain conditions, can collapse into a black hole without any explosions, without anything. Something that we do believe happens with really massive stars, stars that are hundreds of masses of the Sun, although in this case they should also be producing much more massive black holes. And because at the moment the best explanation for this particular black hole is the collapse scenario, it becomes a little bit unclear why this black hole is not more massive. Although it is quite possible that the partner in this case could have played a role in this. It could have maybe stolen some of the mass as the star was about to go supernova, while also somehow causing the collapse to occur and preventing the supernova from occurring. And so at the moment, it's not entirely clear. Hello wonderful person, this is Anton, and today we're going to be discussing some of the new updates and new discoveries coming from the iconic galaxy known as M87 or Messier 87. The galaxy that became famous because of this. The tremendously massive, very powerful and extremely bright black hole that became the target of the Event Horizon Telescope that was able to capture various microwave emissions coming from this black hole, producing the image you see right here. In other words, representing the first ever image of an actual physical black hole, with several additional reworked images later also showing us things like polarized light coming from the vicinity of this black hole as well. And so in this video we're going to discuss some of the new updates about this image, we're also going to discuss some of the new discoveries about this galaxy, but even talk about some of the discoveries in regards to the jet coming from this black hole as well. And as always, all of the additional links and all of the additional papers are in the description below. But first, quick reminder. So what exactly happened here back in 2019? A team of scientists using various radio and microwave telescopes proposed a somewhat unusual idea. Why don't we combine the data from various telescopes to essentially create a kind of a virtual telescope? Or essentially a telescope that in theory could be the size of planet Earth. Can we actually capture something really far away and something relatively small by using this unusual technique? And eventually they realized that it should be technically possible, assuming that it also involves relatively complex math and algorithms that can then recreate all of this data based on just 6 points able to capture microwave light. And so for several years, a lot of these scientists were collecting data for this specific project they now refer to as Event Horizon Telescope. Telescope whose main purpose was to capture the picture or an actual image of a distant black hole. And even though most of us might think that the central black hole in the Milky Way galaxy might be the biggest one and the easiest to capture, it turned out that the galaxy Messier 87, located approximately 50 million light years away from us, contained an ultramassive black hole that was even bigger, even brighter, and had a lot of matter in the accretion disk, moving even slower, allowing for much easier capture. The galaxy that was also known for its very beautiful jet pointed almost directly at us. And this jet, of course, is a telltale sign that there is a very active, very massive, and a very intriguing black hole somewhere at the center. And in 2019, we got the first image, which was of course one of the most exciting discoveries of the year, but also a few more reworked images, adding things like polarized light from various observations that took a look at some of the other frequencies in the vicinity. Here's actually another image of this region, visible by the Chandra's X-ray telescope, mixed with radio observations as well. And since that original image, we obviously also got the image from our own galaxy, Sagittarius A star, although I guess it wasn't really as exciting as some of us hoped. You can learn more about this in the video in the description. But it looks like now, after just over 4 years, we have another update to this very famous, very iconic image. And this time, the black hole looks like this. Now, it is a little bit different, but it's essentially the same image. And it's probably a little bit more accurate. Because this time the scientists used some of the new techniques using artificial intelligence in order to generate an even more accurate image of what was taken by using various computational models and combining it with actual observations, or basically filling some of the missing gaps with data collected by the artificial intelligence by learning from other models. This specific model is known as Primo, and it looks like it was able to achieve the highest possible resolution using modern observations and using modern techniques, in the process creating a much sharper image with the overall width of the ring decreasing dramatically as well. Which, by the way, for the scientists is really important because in this particular case, this will allow them to test various theories of gravity with a lot more accuracy. And in order to achieve this, the scientists used analysis of approximately 30,000 simulated images of various black holes and trained the artificial intelligence to look for common patterns that could then be applied to M87. Something that can now technically be applied to other black holes, including Sagittarius A star. Or in other words, in the next few months we might be able to see a much better picture of a black hole in the middle of our own galaxy. The image you see right here is based more on probability as opposed to actual physical observations. But this was just the first discovery about M87. The scientists were also able to work out something else about the galaxy itself. And specifically, by using completely new techniques and new observations, the scientists were able to recreate a kind of a three-dimensional model of this unusual massive galaxy. Once again, the galaxy that's about 53 million light years away from us, but that seems to be way more massive than it should be. It's basically one of the most massive galaxies in the vicinity. And turns out that this galaxy is not really as spherical as we thought. Despite the photos making it appear elliptical and somewhat spherical, it actually seems to be basically potato-shaped. Or triaxial if you want to be more scientific. And since this is a science channel, I guess I'm gonna have to use triaxial and not potato-shaped. Now, just to kind of give you an illustration of what we believe this galaxy to look like, previous research assumed it to be sort of like this. This is sort of what most elliptical galaxies appear to us from a distance. But in this case, it appears as a perfect sphere. A somewhat diffuse sphere, but sphere nevertheless. But in order to assess the actual shape, the scientists relied on various techniques including astrometry, by looking at the overall motion of stars inside the galaxy. But because this galaxy is 50 billion light years away from us, it's practically impossible to see individual stars. You can, however, detect swarms of stars, and of course detect their motion across the galaxy. And so by using these swarms, they were able to do two things. First, determine that the galaxy is not spherical and that it seems to be rotating around a third axis, thus it's called triaxial. But second, also recalculate the mass of the central black hole, with the result resembling something like this. And interestingly, it seems to be spinning around its third axis at a velocity of about 25 km per second, which is obviously really slow, but detectable by modern telescopes. And so this is essentially what this galaxy is doing, very likely a result of massive collisions back in the days. But this also resulted in a recalculation of the mass of the black hole. Before, the scientists thought that maybe it's about 6.5 billion solar masses. The new calculations suggest that it's a little bit less, maybe 5.4 billion solar masses, definitely providing a bit of a discrepancy. And it's actually these discrepancies and the fact that this galaxy is not spherical can help the scientists figure out how the galaxy and the central black hole evolved in the last few billions of years. We don't really have these answers yet, but we probably will in the next few years. More importantly, this very accurate calculation of the central black hole can now help the scientists work out some of the other properties of the black hole itself, including its spin, something that's not very easy to measure. We know that these black holes spin, and some of them spin really fast, but the spin rate of M87 black hole, also known as Poehi, is currently not really clear. But apart from knowing the shape, knowing the mass, which is about 10 times the mass of the Milky Way galaxy, and of course now figuring out the mass of the black hole, the scientists were also able to learn something new about the central jet. The jet is approximately 5,000 light years in length and ejects material at nearly the speed of light, and more importantly, points almost directly at us, as a result producing a very unusual effect where the material seems to move 6 times the speed of light. You can learn more about this phenomenon in the description below. But just to clarify, the stuff here is not moving at faster than the speed of light, it just appears to do so. It's a kind of a visual illusion. But by using new techniques and new observations, the scientists also looked at some of the more details of this jet, in the process discovering what sort of shapes it seems to form on the inside and what very likely causes all of these unusual formations. Strangely enough, it seems to kind of resemble a double helix, basically DNA. In other words, by using very powerful magnetic polarization techniques, the scientists worked out that it seems to form these unusual helical structures inside the jet. And even though the jet should be weakening away from the black hole, a lot of these unusual instabilities seem to produce regions of higher pressure, which then encourage the formation of new helical structures. Or I guess in simpler words, there's some really complex magnetic interaction going on here that causes the jet to form very strange shapes, and shapes that seem to last for thousands and thousands of light years. And how exactly this happens, to some extent is explored in this relatively recent paper, but technically still is not very well understood. It does seem to involve really powerful interaction with magnetic fields, and a lot of various instabilities formed on the inside. Once again suggesting that a lot of the jets in a lot of different objects are mostly produced by very powerful magnetic fields much closer to the black hole or to the central region itself. And the magnetic fields are most likely the result of the interaction inside the accretion disk, with a lot of magnetic lines in this case wrapping around in such a way that they form these jet-like formations. Although this is one of the bigger mysteries, so we're probably going to be coming back and talking more about this once the scientists figure out how exactly this works.
Hello wonderful person, this is Anton, and today we're going to be talking about a completely accidental and somewhat surprising discovery of what seems to be the fastest growing black hole in the nearby universe. A black hole that creates the brightest quasar that we've ever discovered, at least within the distance of approximately 10 billion light years away from us. And what's really unusual is that this is such a bright object that it was actually always there. But it was accidentally missed by a lot of previous surveys because of its location in the night skies. Or in other words, because it was in this unusual blind spot that was created by different surveys that was basically missed because this represents a location approximately 18 degrees above the galactic plane that a lot of previous surveys managed to somehow miss. And that's of course because some of the regions of our galaxy are just very difficult to observe because there's just so much stuff, a lot of dust and a lot of other stars and a lot of other objects that make the observation of the rest of the universe somewhat difficult. So many surveys avoid these regions because the disk itself will just block everything behind it. Although here we're mostly talking about surveys looking for distant objects such as distant galaxies and very distant quasars. Although, quick clarification, so what is a quasar? Well, quasar is just another way of saying an extremely bright and usually extremely massive black hole, very often in the center of a galaxy that's feeding so fast and produces so much energy that it ends up creating the brightest objects in the universe, the objects visible literally from the edge of the universe, with the word quasar itself simply meaning quasi-stellar radio source. And we actually know quite a lot of these objects, and many of them have been quite extensively studied. And as far as we know, they're all produced in exactly the same way, the way that you see right here. So basically these are black holes that are feeding extremely fast. And because of their power and also because of the way that they're feeding, they also tend to produce a lot of feedback that tends to then change the galaxies where they're located. As a matter of fact, many scientists today even believe that many quasars eventually sort of kill the galaxies, stopping the production of stars. Or at least some do, not all of them. And the more powerful the quasar, the more powerful the illumination or the so-called feedback mechanism that then changes the galaxy. This is actually the phenomenon that generally transforms the galaxies and tends to create very different types of galaxies afterwards. And the more massive the black hole, the more of this feedback mechanism is going to be creating, the more brightness and the more power it's going to be producing as well. And actually, fun fact here, one of the main reasons some scientists believe that the Milky Way galaxy is kind of unique and kind of different from a lot of other galaxies is that the black hole here, the Sagittarius A-star black hole, is much smaller in terms of mass and in terms of size compared to a lot of other supermassive black holes in other galaxies. And because of this, it probably was never a very powerful quasar to begin with, and because of this it probably never really influenced a lot of objects in the vicinity to the same extent as some of the other black holes. And because of this, our planet might have had a chance to establish permanent life. Now, it's a speculation that's somewhat difficult to prove, but many scientists do believe this idea, and it sort of is one of the reasons why we think we're located in an extremely unique galaxy. But we'll actually talk more about why we think so in some of the future videos. But quasars are really important in modern navigation and modern communication. Pretty much every modern system using GPS or any other system that uses navigation or time measurement from some of the sources on the ground will rely on the map you see right here. This shows us the various quasars used to determine the exact location on the planet. So in other words, quasars are some of the most important objects when it comes to directly detect something on the planet. I've actually discussed this in some of the older videos that should be in the description or somewhere right there, but in essence, quasars are essential for modern technology, for modern timekeeping, and for modern GPS systems that rely on extreme precision. And here we're specifically talking about quasars that are very bright. And so it is very surprising that the scientists have just found one of the brightest quasars literally in plain sight. The quasar that produces approximately 7,000 times more luminosity, more light, than our entire galaxy, the Milky Way. And that is ridiculously bright. According to the scientists behind this paper, it sort of means that we found the fastest growing black hole ever. The black hole that seems to be absorbing roughly around one mass of planet Earth every single second. Okay, let me repeat this. Every single second, it's eating a single planet Earth. That's by mass, of course. And in the process, produces a tremendous amount of energy. Now, as you probably already know, or you might have heard before, the energy itself in this case is not really coming from the black hole, as it's actually coming from the accretion disk. The black hole itself is obviously black, it doesn't really allow any light to escape, but the accretion disk, because of its size and because of its energy, will end up creating tremendous amount of luminosity and will also create a lot of energy that will then escape from this region. It also creates a kind of a radiation pressure very similar to a typical star, where a lot of things, a lot of gas, a lot of dust, sort of gets pushed away from the center of the galaxy and moves a little bit to the outskirts, or sometimes actually gets completely displaced by all of this pressure. There's also a very important concept known as the Eddington luminosity that comes into play here. It refers to a kind of a balance reached between the gravity and the pressure from the luminosity itself. So basically, the brightness here will push things away, whereas the gravity is going to pull things in. And at some point, a kind of a balance is reached. Now, if you get too much luminosity, if things start to get too bright, the object will most likely fall apart. Usually this is a case with many stars. Whereas if the outer pressure and the luminosity stops, the object starts to collapse and then can actually initiate a supernova, for example. And because of the Eddington limit as it's known, there is a limit to how fast certain black holes can grow in size. Because as the black hole grows in size, it starts to emit more luminosity, and this starts to push away a lot of the mass that tries to come in. At some point it reaches the balance, with the total growth of the black hole sort of becoming more or less permanent. This is actually one of the reasons why the scientists have trouble explaining the existence of some of the most massive black holes in the ancient universe. A lot of them simply did not have enough time in the universe to become so massive. But in this particular case, this black hole is approximately 2.6 billion times the mass of the Sun, and based on the observations of its Eddington luminosity, it seems to make sense. But what doesn't make sense is, why is it still so bright and why is it still eating so much material? Oh, and a quick clarification. The light coming from this particular black hole is about 7 billion years old, which means that by now the black hole very likely quieted down. But it's still the youngest quasar currently known to us to be so extremely powerful. The quasar currently known as J1144-4308. The quasar that beats the previous record holder, 3C273 that you see right here, by about 8 times. Essentially it's about 8 times brighter than this. But despite its brightness, it was only found when the scientists were actually looking for different binary stars and were looking at things in the ultraviolet light. But because it's so bright, it even appears in some of the oldest photographs taken back in 1901. So it was always there, it was always very bright, but we just somehow missed it. And really the biggest mystery about this quasar is, why is it still active? Many quasars by that time in the universe have already quieted down. None of them were producing so much energy. Yet this one is still doing stuff, and still doing stuff very actively. Why? That's not really known right now. One potential explanation here is a collision between two different galaxies, with maybe even two different quasars just combining into one and creating some kind of a mega quasar, or alternatively maybe being some kind of a black hole that's spinning super fast, releasing so much more energy than any other black hole. At the moment, it's not really clear. It's just clear that this object is very bright, so bright as a matter of fact that apparently you can even see it with a regular telescope during the night that's dark enough. More intriguingly, the same team that found this quasar also identified 80 more potential candidates that might have been missed by previous surveys. Hello wonderful person, this is Anton, and today we're going to be discussing the first ever discovery of what the scientists refer to as a rogue black hole. A black hole traveling completely by itself, without any partners, without anything. And as you can probably imagine, it would be pretty difficult to detect such an object. It does not emit any light, it does not produce any energy, such as any astrophysical jets that would be visible to us, it doesn't emit anything. So the question is, of course, how did they actually do it? And is it really there? And from what I've seen so far in the paper, it really seems like they did a pretty good job at making sure that this black hole is real. And it took them nearly a decade to actually prove all of this. And so it's a pretty groundbreaking study in that sense, especially considering that quite a lot of claims have been made in the past about the potential discoveries of these so-called black holes. But before I explain to you how they found this, it's also kind of important to understand why this is a big deal. Now naturally, black holes today are not really a mystery and nothing to be super excited about. They seem to be everywhere. As a matter of fact, not so long ago we've talked about this map you see right here. This is a map of millions of different black holes, very far away black holes, that was created by radio astronomers in Australia. The video for this should be somewhere in the description. But there are different types of black holes out there, and some are extremely elusive despite being very numerous. So for example, these ones, all of them are supermassive black holes. Black holes that we normally find in the middle of a typical galaxy. Almost all galaxies so far seem to have them. There are some exceptions. For example, the Triangle Galaxy, once again the video in the description. The scientists have been discovering a lot of binary black holes colliding and producing gravitational waves, something that the scientists have been doing since 2015. The example right here is from LIGO, showing us how these black holes produce these gravitational waves. This is also not something that's unusual anymore. And then there is also the discovery of several dozen systems, usually binary systems, where a black hole is absorbing some of the mass from its partner star and essentially is re-emitting it as astrophysical jets visible from planet Earth. Although these objects are not as common as some of the other black holes discovered so far. And the only reason we can even see them is because of the amounts of energy they release because of the mass being absorbed from the star. But there are obviously a lot of other similar black holes, at least in terms of mass, expected theoretically. As a matter of fact, most of the massive stars over approximately 20 masses of the Sun, when they explode, should be producing these so-called stellar mass black holes. And considering the fact that we've seen quite a lot of supernova over the last few years that do end up producing black holes, usually in distant galaxies though, we generally expect a lot of these black holes to exist in the vicinity. But how would you possibly see them? For example, this black hole right here is just a few masses of the Sun in mass, and in terms of the diameter of the shadow of the black hole that you see right here, which is essentially the part that's blocking the light, it's really only possibly 15 to maybe 20 kilometers in diameter. And so if we look at this from a distance of several thousand light years away from us, it's practically impossible to detect this. So how did the scientists in this paper do it? Well, using a somewhat similar technique to how Arthur Eddington that you see right here was able to use the 1919 solar eclipse to prove the ideas that Einstein proposed. The idea that a massive object is actually going to be bending the sunlight, or any starlight, just a little bit, assuming that it passes in front of the observer. In other words, it proved the ideas behind spacetime and behind the gravitational lensing effects. And specifically, he was able to definitively prove that, as the title of this particular newspaper says, the stars were not where they seemed to be. In other words, the starlight itself shifted because of the gravitational effects during this particular solar eclipse. And this discovery then led to Albert Einstein becoming a somewhat household name. And what he did was use the technique known as astrometry, the extremely precise way of measuring the position of distant stars or any distant bright object, revealing their motion across the night skies or showing slight changes in their position. For example, it's possible to use astrometry to detect slight wobbles of stars' orbit, which could then indicate that there's some sort of a planet nearby. Or it can even be used to look at our own sun and determine these slight motions across the night skies, discovering where the center of mass of the entire solar system lies. So in this image you can actually see the year and the location of the center of mass of the solar system compared to our own sun.
And so by essentially combining the idea of gravitational microlensing, which usually ends up producing a slight peak in brightness, as you can kind of see right here. This is due to the production of what's known as the Einstein lens, also sometimes referred to as the gravitational lens, that sort of resembles this. And by combining this idea with astrometry, which measures tiny variations of the star motion across the night skies, it becomes possible to essentially determine if something massive like a black hole passed in front of a distant object. And there are really only two expectations from a typical massive black holes when it comes to these observations. First of all, the actual gravitational lens has to be pretty long. As a matter of fact, the longer it is, the more massive the object is. But it also depends, obviously, on the speed of the black hole moving across the night skies. At the same time, the actual changes in astrometry, or the slight variations of the star location, and in this case we're talking about the starlight from several stars, also sort of signifies that something really massive passed in front of this region. And by measuring the actual shifts in the star location, or by measuring the astrometry, it becomes possible, combined with the gravitational lens, to determine the total mass of the black hole, the speed of the black hole across the night skies, and pretty much all of the other parameters, which are essentially the two methods used in this particular study. But they also needed to get data from somewhere, and it just so happens that in the last decade or so, two major projects have been collecting a lot of gravitational lensing data from a lot of different stars. We have OGLE, the Polish project that has already discovered quite a lot of various unusual objects, including several potential planets, and then we have the project known as MOA, Microlensing Observations in Astrophysics. Not as productive as OGLE, but still a pretty cool project nevertheless. And in June of 2011, there was an unusual brightening of a distant star located around 20,000 light-years away from us. It was detected by both projects and was listed as this right here, with the star visible in this image, with the lensing effect producing the increase in magnitude visible in this graph. But this was just a gravitational lens, it did not include any astrometry. To get the astrometry data, very accurate astrometry data, they had to now look at the same location for several years using Hubble Space Telescope, which allowed them to confirm that not only did the star change in brightness as expected from the gravitational lens, and did so relatively slowly, but there was also a relatively small shift in the astrometry position of these stars nearby, with the actual changes in the astrometry being much smaller than what Arthur Eddington was able to detect in 1919, obviously suggesting that we now have much more sensitive techniques. And following the years of calculations and observations, the scientists determined that the best explanation here was a black hole that was approximately 7.1 masses of the Sun in mass, passing in front of a star at approximately 5,000 light-years away from us, with the star itself being about 20,000 light-years away from us. And in this case, they even determined the speed of the black hole. It was moving pretty fast, approximately 45 kilometers per second, compared to the stars nearby. But one of the main reasons they believe it's a black hole is really because of the length of this gravitational lens. It lasted for approximately 300 days, suggesting a relatively massive object. But here the scientists also made some conjectures and some speculations about the potential origin of this black hole, simply due to its mass and due to its velocity across the night skies. Here they believe that the supernova that produced this black hole might have ended up kicking it out of the actual system, giving it the necessary speed to move that fast. And that's mostly because of that high velocity. If it wasn't moving that fast, it could have actually been created in some other way. But I guess more importantly, this finally confirms that these solitary black holes definitely exist. They're very difficult to find, but they are definitely out there. And there's quite a big chance we're going to be finding more of them in the near future. Specifically, possibly in the next few years, possibly in 2025. And that's because in 2025, the iconic ESA's Gaia telescope is going to be releasing the astrometric data for billions and billions of star systems that it's been observing for several years now. Getting all of this data is going to be absolutely crucial for finding more of these mysterious black holes quietly traveling across the galaxy. Hello wonderful person, this is Anton, and today we're going to be discussing both black holes and dark matter, two exciting phenomena that many scientists believe will help us explain the universe even better. And although we are pretty sure black holes exist and there are quite a lot of them out there,
When it comes to the mysterious dark matter, the story is not as clear-cut. The only evidence we have for this unusual dark matter is really circumstantial, but there is a lot of it. And I mean like a lot. And most of it is impossible to explain using any other explanation other than it's some kind of a particle or some kind of a mass that interacts with everything gravitationally, but not through electromagnetic means, which is why it doesn't produce light and seems to be kind of invisible. And though obviously it may sound kind of strange, it's not unusual for particle physics. As a matter of fact, neutrinos were also believed to be very hypothetical, taking many years to finally be discovered and to finally be proven. And so in that sense, a lot of scientists do believe that dark matter does actually exist as some sort of a hypothetical particle, it just nobody really knows what particle and where to even start looking. But this recent study actually provides even more evidence for its existence as a particle and not some unusual phenomenon or some unusual formula that we don't understand. With all of this coming from this study that as always you can find in the description below, with the title pretty much telling us everything. Indirect evidence for dark matter density spikes around stellar mass black holes. Because in this case what the scientists did was take a look at a somewhat old hypothesis in regards to dark matter and in regards to their relationship to black holes. And specifically, the idea that black holes can sometimes, or possibly even a lot of times, swallow dark matter and basically increase in mass as well. Which obviously suggests that a lot of other massive objects would probably be doing something similar as well. But naturally this means that while the black hole is swallowing dark matter, some of this dark matter is going to be orbiting around it, with quite a lot of it potentially coming really close to the black hole's event horizon, or maybe even assuming orbits around the black hole, possibly even permanent orbits. In other words, we know that black holes have an accretion disk, but there's also quite a big chance that some black holes, or maybe even all black holes, possess another accretion disk pretty much made out of some kind of dark matter. And since dark matter is believed to represent approximately 85% of all mass in the universe, it would not be surprising if these particular disks, if they existed, would be pretty massive as well. But unlike a typical accretion disk that produces huge amounts of light and is visible from the edge of the universe, anything involving dark matter would be pretty much invisible and only detectable through gravitational effects. And so knowing all of this, the scientists wanted to find out if this is actually what's happening around two relatively known X-ray binaries. Essentially, a black hole and a star in orbit around one another. And this is, by the way, how the first black hole ever was confirmed as well. That black hole is known as Cygnus X1, and there is an older video on the channel that goes through a little bit more detail, both about the discovery and about recent discoveries from this unusual system. But in this case they did not focus on this black hole, they chose to focus on two other black holes in the Milky Way. XTE J1118 plus 480, the system that's easily visible in the X-ray frequency, with this X-ray image taken back in 2001, with the potential mass of this black hole being about 6 to possibly 7 solar masses, and A0620-00, slightly smaller black hole at possibly 5 to 6 solar masses, with this image showing us what it looks like using infrared light taken by Sloan Digital Sky Survey. And because this is a binary system with a star and a black hole inside, the light curve in this case looks something like this. And that's because the star orbits around the black hole, in this case approximately 7.7 hours per orbit, which allows the scientists to calculate extremely precise orbital parameters in both of these relatively distant systems. And so by taking a lot of data from these two star systems and by looking at these light curves, and by specifically focusing on the changes in the orbital period, the scientists in this paper were able to calculate the overall orbital decay for both of these star systems, or essentially by how much the star's orbit decreases with every orbit around the black hole. And so, for example, because of the gravitational waves from the black hole, generally any object orbiting the black hole is going to slowly come closer and closer to the object. And that's of course how black hole collisions work as well. In this case, by producing gravitational waves, black holes cause one another to drop in orbit and eventually collide. But when the scientists took a look at these two systems, and obviously considered all of the possible effects, they realized that the orbital change was actually a little bit more dramatic. Or basically that the star decay in this case was slowing down by about 1 millisecond per year more than it should. And modern theories, including Einsteinian theories, cannot really explain this. And so instead, the scientists in this paper tried to come up with different models trying to explain what's happening. In this case, using computer simulations, to come up with a model that would try to explain this using what's known as dark matter dynamical friction model. Or basically a model that would consider the presence of dark matter as a potential source for the actual slowdown. In other words, dark matter orbiting a black hole and gravitationally pulling at these stars might be the reason why these stars in this case were slowing down a little bit more than they should. And the simulations did reveal that the observed rates were almost directly matched with the predicted model, which actually is a pretty big deal. Now, the original prediction suggested that the orbital decay should be close to about 0.02 milliseconds per year, but the rate that was observed from these two systems was approximately 50 times higher. So this was definitely a very significant effect that could not be explained in any other way. But once dark matter was added into the computer models, it all suddenly made sense. The observations and the predicted calculations were almost exactly the same, which basically confirms that black holes most likely swallow a lot of dark matter, and some of it is probably stuck in orbit around the black hole, forming its own version of the accretion disk, and thus having a lot of effects on objects nearby, which sort of makes this a really exciting study. But because this is a pretty big claim, it will definitely require a lot of follow-up studies and a lot of additional observations. As a matter of fact, in this study, the scientists already mentioned that we know of 18 more similar systems, and specifically 18 more binary systems, with at least one black hole, where all of this can then be investigated in order to either confirm or disprove these particular observations. And so chances are that in the next few years, as more scientists investigate those other systems, we might have even more understanding of what's actually happening here, and either finally have even more proof for the existence of dark matter, or maybe discover some new phenomenon that nobody ever knew existed.
Hello wonderful person, this is Anton, and today we're going to be discussing black holes. And to be more specific, the first black hole ever discovered, the first black hole to be ever confirmed. The black hole that you see right here, known as Cygnus X1. This is obviously not the real images, just a simulation of that black hole, but today the scientists are almost certain it's definitely there, and is actually the most well-studied black hole ever, something the scientists have been studying for at least 5 decades. Here's one of many X-ray images taken by various observatories. And this black hole actually kind of became famous back in 1975, when the iconic Stephen Hawking and Kip Thorne, who you see on the left, decided to have a kind of a friendly bet because they couldn't really agree on exactly what the scientists discovered. And originally, this object was identified back in 1964 during some of the earliest flights using what's known as sounding rockets. The rockets that usually are used, even today, for various types of relatively cheap research using suborbital flight, where the rocket reaches really high altitudes, collects a lot of data, and then falls back to the planet, returning the data to be studied. And so in 1964, one of these flights used X-ray detectors and found 8 separate sources that nobody knew existed until then. And one of these sources was Cygnus X1, extremely strong and by then completely unknown. And because of this, the scientists decided to launch an actual X-ray telescope, paving the way for the X-ray astronomy. This was Uhuru, launched in 1970. And so some of the initial observations from Uhuru established that this object was extremely powerful, but it was also emitting X-rays that varied quite a lot, with certain X-ray bursts only lasting for approximately 1 millisecond. And this implied to the scientists that this object must have been really small, mostly because of the speed of light. It basically means that the light in this case only had a chance to be created and to travel for around 1 millisecond. If you do the calculations, it suggested that the object was maybe only about 300 kilometers in size. And back then, this was really unusual, this was kind of unexpected, and nobody really knew what this object was. And so these two wonderful astrophysicists made a bet. Kip Thorne said it was a black hole. Stephen Hawking said it probably wasn't. And by 1990, Stephen Hawking lost. Very thorough observations from Cygnus X1, along with multiple measurements, quite definitively determined that this object was meeting all of the expectations for a typical solar mass black hole. An object approximately 21.2 times the solar mass, and too small to be anything else, any kind of a normal star or any other type of an object, with the size of the event horizon in this case being around 300 kilometers. But possibly even smaller than that. But naturally, because this object was also kind of far away, nearly 7,000 light years away from us, all of this took years and years of studies and years of investigations. But here's one of the better pictures we have of this object from Chandra X-ray Observatory, literally showing us what it sort of looks like in the X-rays. It does resemble a star, and a really bright star visible from 7,000 light years away. And the earlier questions here were, well, what's sort of creating these X-rays and where is all of this energy coming from? And it actually did not take long to answer this because the scientists also identified its partner, a supergiant variable star known as HGE 226868,
that orbits approximately 0.2 astronomical units away from the black hole, or approximately 20% the distance of Earth to the Sun. But because this is a powerful star, it also produces quite a lot of stellar winds, which in the end ends up releasing huge amounts of matter that kind of accumulates around the black hole and creates the accretion disk. And this results in all of the energy we're detecting from the black hole, with the disk in this case very likely being in millions of degrees, which is basically why we're seeing X-rays, and quite a lot of them as well. But there's also obviously relativistic jets coming from this object, arranged in a perpendicular formation to the disk itself, that very likely release things almost at the speed of light. Although in this case we don't really know as much about the jets and we don't really see them as well either. But nevertheless, because of all of these various features, this is also known as a microquasar, or basically something that seems to resemble a typical quasar, but in this case is just a tiny star that just seems to produce very similar features because of the black hole in the middle. But because this particular system seems to be also associated with a much larger region, the region we refer to as Cygnus OB3, in this case it becomes possible to determine the age of this particular system. It's probably around 5 million years old. But unlike a typical scenario that basically produces a black hole from some kind of a supernova, in this case because the partner star is still so close to the black hole, and also because this black hole is relatively massive, over 20 solar masses in total, today the assumption is that this black hole very likely formed as a result of what's known as a direct collapse. It didn't go through the supernova, the star just collapsed into the black hole directly, with the original star being approximately 40 solar masses or possibly a little bit bigger. Although a huge amount of this mass was probably also shed prior to this because the star was probably super active and emitted huge amounts of matter over time. But now, after decades and decades of studies, the scientists discovered something else unusual about this system and something that nobody really expected. Something that was recently discovered by IXPE, Imaging X-ray Polarimetry Explorer. A satellite that doesn't just measure the X-rays, it also is able to measure the polarization of light, or basically by how much the light is sort of turned and shifted, something that's usually produced by various magnetic fields. And so the scientists behind this recent paper that you can find in the description below were able to directly measure the shape and the orientation of a lot of hot plasma located in the region, determining the positioning of the accretion disk and of course the jets as well. In the process discovering that the X-rays were not really coming from the jets at all, from the accretion disk only, and specifically from the region approximately 2000 kilometers perpendicular to the jets, which we do believe is produced by the accretion disk itself. In other words, they were able to pinpoint exactly where most of the powerful X-rays are coming from, establishing a really important fact about black holes. It really looks like the accretion disk represents the most powerful part of any black hole. Most of the energy, most of the emissions, and of course the jets themselves are all formed by the accretion disk from the matter that coalesces around a typical black hole or a neutron star. In this case, determining that the orientation of this disk to us was kind of similar to how you see it here. Almost edge on, about 4 degrees away from the edge. But the orientation of this particular accretion disk is very different from the orientation of the orbit of the star around the black hole. And that creates a bit of a problem because it's kind of difficult to explain how or why the disk suddenly became shifted so much and so dramatically, with one potential explanation once again being maybe a supernova. In other words, maybe there was a supernova here after all, which is what sort of shifted the rotation of the black hole, shifting the orientation of the disk in the process, making it spin differently from the orbital plane. More importantly, also establishing that the disk itself is kind of thin and is almost directly perpendicular to the jets, confirming that they do seem to depend on each other, and it's very likely that the disk produces everything that we see. But these are also some of the most accurate observations of X-rays coming from nearby a black hole, which obviously will produce a lot of new results, testing various Einsteinian theories, or possibly discovering something else about black holes we've never known before. And so these new extremely accurate observations from Cygnus X1 are very likely going to be producing even more papers in the next few months, helping us understand what happens around black holes, how accretion disks and jets are formed, and possibly answering more questions about these extreme, strange objects. But at the moment, we don't really know what's going to be discovered just yet. It's been over 100 years, specifically 106 years when I'm making this video, since the original Einstein's predictions for the existence, potential existence, of what we now call gravitational waves. The waves in the space-time itself
as various objects that have mass orbit, interact, collide, and produce all sorts of effects, which result in wave-like disturbances in the space-time itself that Einstein did not believe we'll ever be able to discover. 100 years later, we've proved them wrong by discovering them using huge detectors several kilometers in size, such as LIGO that you see right here. With the principle of detection actually being pretty simple. By shining two lasers across several kilometers, we can detect minute changes in space-time when the lasers become slightly out of sync, if the foundation of the fabric itself changes by even a few nanometers, moving the lasers out of phase. And so by actively measuring the lasers, and by actively measuring this in two different locations on the planet, it becomes possible to know exactly when a very large gravitational wave passes through planet Earth. And over 80 of them have already been discovered since the original discovery in 2015, which eventually led to the Nobel Prize in 2017. But it turns out that one of these detections from 2020 that was discovered by both LIGO and Virgo detectors was way stranger and way more unusual than anyone ever believed. It was still a collision between two black holes and still possessed very similar properties to everything else we see, with one of the black holes being kind of massive, approximately 40 solar masses, which makes it one of the larger black holes we've discovered so far, but definitely not the largest and not the most massive. But more intriguingly, it was also one of the fastest spinning, possibly even the fastest spinning discovered to date. It was actually spinning almost at its maximum limit. And because this was a spinning black hole, it started to produce some really strange additional effects. Actually also effects predicted by Einstein back in the days, but the magnitude of these effects was absolutely mind-blowing. In a nutshell, it resulted in what we usually refer to as precession. It's basically a kind of a twisting of the orbit that I guess is easiest to imagine if you look at the typical top. This sort of a top. Notice how the top, as it spins, starts to wobble just a little bit. This is very often known as precession. You might already know that one of the first tests confirming Einstein's theories was the test of the precession of Mercury that happens because of its close proximity to the Sun, which actually changes the orbit of Mercury just a little bit. Without Einstein and his theories, it's impossible to explain why Mercury does so. This was actually one of the biggest mysteries in astronomy. Einstein's theories explain it perfectly, with the precession in this case predicting exact position of Mercury and its precession for millions and millions of years. Although in this particular image this is a bit of an exaggeration. The actual change of the orbit is kind of minuscule and only becomes obvious over periods of hundreds of years. More recently though, a lot of precession has been measured from around different neutron stars and various pulsars, as they for example orbit around another object that causes them to sort of wobble back and forth. In this case the wobble is also kind of minuscule, but definitely much bigger than Mercury. As a matter of fact, it's usually visible in just a few weeks or just a few months. In other words, this particular effect is not really that easily detectable unless you measure it extremely precisely for a very long time. One of the most extreme examples known to us from previous detections was from the iconic binary pulsars, where a single orbit takes approximately 75 years to precess. This is the Holst-Taylor binary as it's also known. And so a single wobble here would be approximately 75 years, and all of this is caused by the Einsteinian theories. But in the black hole binary that collided with the waves detected in 2020, things were much more extreme. Roughly around 10 billion times more extreme. According to the scientists behind the study and the simulations they've conducted, this was essentially the most extreme physical event we've ever detected in terms of precession. The entire orbit of these two black holes was wobbling back and forth, precessing several times every single second, which in theory would even be faster than the top I showed you. As a matter of fact, right before the collision the precession was extremely high. You can kind of see it happening right around here. But this precession is slightly different from the one I showed you with a single object. This is more often known as the lens-Thirring precession, and you can find a few more links in the description that explain this a little bit more. But in a nutshell, the entire orbit of these two objects starts to wobble back and forth, producing extremely bizarre effects that I guess are kind of difficult for us to imagine unless we look at it in a simulation. So it was basically doing something like this, wobbling back and forth, moving faster and faster, and moving the entire space-time with it. In this case, several times per second. And this is of course a super bizarre event we've never seen before. The event that was believed to be completely theoretical and was also believed to be kind of rare up until recently. Moreover, at the end of the collision, there was also a clear sign of a relatively large kick where essentially the final black hole started to move somewhere pretty fast.
And that's kind of expected though, this is not unusual, although in this case this kick was measured, but the scientists discovered that the merger between these two black holes was definitely lopsided or one-sided, with the resulting speed being 3 million miles or 4.8 million kilometers per hour. And although theoretically this kind of makes sense and all of this has been predicted, what is actually kind of hard to explain is these types of events are supposedly only happen very rarely. But in this case we seem to have discovered one after just 80 observations, with extremely high precession, with very high kick, and all of this being lopsided as well, not to mention the fact that the black hole was also kind of massive. This was supposed to be a 1 in 1,000 if not 1 in a million event, not 1 in 80. And more importantly, we're going to be discovering more of these once LIGO and other detectors become fully functional again. I believe some of this research has been actually put on hold because of the COVID situation, but it's slowly getting back on track. And so, even though the actual detections have been kind of interesting so far, there are still so many mysteries we cannot answer. We've discussed some of them before, but in a nutshell, a lot of these black holes are way more massive than anyone ever expected them to be, and many of them seem to actually create objects that are even more massive. Originally, the scientists predicted something that was maybe 5 to 10 solar masses. Most of the black holes we've discovered so far seem to be at least 30 to 50 solar masses, something that doesn't add up. Although there was a super interesting explanation that someone proposed a while ago that you can find in the description below. But the fact that once again we were able to see these extreme effects from the Einsteinian theories, and in this case the most extreme precession we've ever seen, with the orbital wobble of several times per second, that by itself already makes it a kind of a historical event. An event that currently is kind of difficult to explain, but will probably result in some really intriguing discoveries in the next few years. Hello wonderful person, this is Anton, and today we're going to be discussing some of the new discoveries from one of the most fascinating supermassive black holes out there. Or to be more exact, an ultramassive black hole. One of the most massive ever found. It's probably within the top 3. From a relatively large galactic cluster that would sort of resemble this if you were to look at it in the X-rays, or resembling this if looking at this black hole and this region using combined wavelengths. And to date, this is probably one of the stranger black holes out there, definitively located right in the middle of a massive galactic cluster. The cluster known as MS0735, located around 2.5 billion light years away from us. But more specifically, we're going to be focusing on a recent study that came out not so long ago, that essentially analyzed this particular cluster and this region using a somewhat intriguing method, discovering something really interesting about this black hole in the process, or essentially revealing this region, this entire cluster and the black hole itself, in a completely different light. In this case, microwave light, that basically shows us a really intriguing cavity produced by the pressure from this black hole. And so what exactly is going on here, and what have we learned about this cluster from this study and from some of the more recent studies that you can find in the description below. And first, I actually wanted to start with another study from not so long ago that basically discovered and confirmed something else in our own galaxy, somewhat related to what we're observing from this distant black hole as well. You might remember that our galaxy has these unusual features known as the Fermi bubbles. These unusual binary formations that seem to stem from the center of the galaxy and actually extend up to about 30,000 light years in every direction. And it's always been speculated that these were most likely caused by some kind of a really large explosion coming from the central black hole in the Milky Way, or possibly some kind of an active event that must have lasted for some time. But a more recent study analyzing this using computer simulations almost definitively established that this was caused by a relatively long-lasting and very active wind-like phenomenon that lasted for approximately 10 million years and was basically produced by the central black hole. And this phenomenon of galactic wind has actually been found around a lot of different galaxies out there, and has definitely existed around our own galaxy as well. Here's one of the more extreme examples from the galaxy known as M82. But in case of the Milky Way galaxy, it was a lot more mild, and it very likely ceased to be active quite a long time ago. Here, the phenomenon is very likely quite similar, but it's probably at least 10 to possibly 15 times larger than what we observe in the Milky Way. Possibly even bigger than that. And more importantly, a lot of the recent analysis established that this has been actually going on for approximately 100 million years, so about 10 times longer than in the Milky Way, with some of the modern calculations suggesting that it must have consumed about 600 million solar masses to produce all of this energy for 100 million years. Or in other words, this black hole must have consumed a total mass of a smaller galaxy in order to release all of this energy we're observing and measuring from this particular galaxy. And that's of course a ridiculous amount of energy and a ridiculous amount of mass. And based on the amounts of energy that's being released even today, it also seems to produce some of the brightest and some of the most active galactic regions that we can actually see with modern telescopes. This used to be a record holder, but there might have been another discovery from not so long ago that seems to produce something even brighter. We'll talk about this in some of the future videos. And so the amount of energy released here every single year is equivalent to several gamma ray bursts, which are essentially the brightest and the most powerful explosions in the universe. But what can possibly produce this? Well, as you can imagine, a really large black hole, with some of the modern calculations suggesting that it could be one of the largest, if not the largest, known to us, with a total mass of about 50 billion suns, or about 10,000 or actually 12,000 times as massive as the black hole in the middle of our own galaxy, resulting in some of the most extreme environments in the universe, with average temperature of about 50 million degrees Celsius, and huge amounts of X-rays, gamma rays, and a lot of other radiation emitted from the center. With all of this generating these huge emissions, these very powerful winds, but also generating a lot of other effects, such as the black hole feedback effects, that sometimes are responsible for stopping the star formation, but sometimes have the opposite effect. And so this is actually a pretty fascinating object to study, just to see what effects it has on the nearby galaxies. But moreover, the power of this object can even be seen inside the map of the first light, the Cosmic Microwave Background, CMB. And intriguingly, the powerful wind coming from this black hole actually creates unusual cavities visible from 2.5 billion light years away, which was one of the most recent discoveries from the paper you can find in a description. This is based on a very intriguing effect known as the Sunyaev-Zeldovich or CZ effect, where the slight distortion in the CMB create unusual echoes visible from very far away. And so in this case you can actually see them at a frequency of about 90 GHz, and they appear as these very large pressure bubbles that existed here for at least 100 million years, with the study further establishing that it's most likely a combination of thermal effects mixed with the effects from the magnetic fields and the pressure from the cosmic rays, as well as overall turbulence that prevents these bubbles from essentially collapsing. With one of the main questions that the scientists are trying to solve is essentially figuring out how much of non-thermal pressure is produced by these black holes, because it's usually the non-thermal pressure that then leads to the formation of stars and essentially can help the scientists figure out how galaxies evolve and what triggers star formation in certain locations of the universe. But I guess the more intriguing part of the study is just the fact that this was confirmed to be a really massive black hole. So massive that it's visible in the CMB, and so huge and so massive that it seems to have created these effects for 100 million years, producing one of the most powerful emissions visible from planet Earth. And if this black hole is indeed about 50 billion solar masses, it's already technically above the theoretical limit for the most massive black hole we believe should exist. Today there is no theory or explanation for how black holes over 50 billion solar masses can exist anywhere. Yet at least 3 possibly have been discovered in the last few years, and so it does create a bit of a theoretical problem. And that's because, given the age of the universe and the composition of matter in the universe, the modern theories suggest that there's just not enough time for a black hole to grow so massive, even if it continuously consumes matter for 13.8 billion years. Generally, a massive black hole that consumes matter really fast starts to create so much wind that it creates a kind of a balance between the consumption and the emission of energy. And at that limit, if you were to grow a black hole, it would maybe reach the mass of 50 billion. But in this case, this black hole is a little bit more massive. So definitely a bit of a mystery. And that's on top of the fact that these jets may also be some of the most powerful jets coming from a black hole as well. Which makes this galactic cluster extremely intriguing for cosmologists trying to answer all of these questions about black holes and the evolution of the universe. Although at the moment these are just observations and we don't really have any actual answers. And we also have no idea how these black holes affect galaxies around them, if they actually affect star formation or planetary formation, or if life can possibly exist anywhere in the vicinity of these events. At the moment, the answer to all these questions seems to be maybe no. Maybe no life, possibly very few planets if any at all, and possibly no star formation either. But at the moment, there are no concrete answers just yet. But because we know something similar but on a smaller scale happened in the Milky Way, and of course may happen again in the future, that's why answering these questions potentially might be really important. For example, we know that this happened a few million years ago. So did it actually have any effects on planet Earth? And if so, what kind of effects? And so that's one of the main reasons why studying these particular galactic clusters can actually lead to some important questions about what might have occurred on planet Earth when the Milky Way was a little bit more active as well. In this case, remember this was for about 10 million years. Could this have had some major effects on the planetary atmosphere? But for now, we don't really know. Hello wonderful person, this is Anton, and today we're going to be discussing new discoveries in regards to black holes, and specifically discoveries coming from the iconic Gaia telescope. ESA's incredible telescope, essentially responsible for measuring extremely accurate motion and location of stars and a lot of other bright objects in the vicinity of planet Earth. Or to be more specific, using what's known as the astrometry technique that allows the scientists to extremely accurately measure even minute changes in various bright objects. And it's been doing so for several years, discovering incredible things in the process. But last year, in December of 2022, we've actually discussed a pretty unusual and somewhat intriguing discovery coming from this telescope that was not expected to be discovered by anyone. A discovery of a somewhat unusual black hole system where one of the objects was a star not so different from our Sun, but the other object was a black hole. Although unlike other black holes we've discovered to date, this one was literally completely invisible. Or, in more scientific terms, this was a dormant black hole. A black hole that's not emitting any light and is only visible through various gravitational observations, the result of various Einsteinian theories. And so in this video I wanted to discuss a little bit more about this new discovery, and specifically the second discovery of the second black hole, and why the scientists now believe that this is a completely new type of a black hole never seen before anywhere else. But first, I wanted to start with something a little bit different, something on a slightly different topic, and something that is even more mind-blowing. Microsoft Bing. What? Why am I talking about Bing? Okay, it's not really the Bing we're talking about. We're talking about the newly updated ChatGPT that's now part of Bing and is actually sort of mind-blowing. I wanted to show you why. Okay, quick side note. There's actually going to be a separate video on this topic exploring the current state of ChatGPT in terms of science, astronomy, and science education. And I'm actually currently making this video, and it should be on the channel sometime within the next few days, possibly the next few weeks. Anyway, subscribe if you don't want to miss this video. But here's the real reason why I wanted to start with this and nothing else. So as I was researching this particular topic, there was actually one question that I had trouble answering, mostly because some papers had somewhat conflicting results. I wanted to find out what is the closest black hole to the solar system when it comes to what's known as X-ray binaries. Essentially these types of black holes where there are two objects, usually a black hole and a relatively large star, where the two objects interact, and the black hole ends up capturing some of the material, becoming activated or no longer dormant, and thus becoming very bright and easily visible from really far away. Here's one of the most famous ones we've talked about on the channel many times, known as SS433. This is visible in radio waves. But essentially what I wanted to find was the nearest such object discovered in the last 10 years or so. Simply because it would show us which types of black holes are a little bit more common. I'm going to explain this in a few minutes a little bit more. But essentially my question was, so what's the closest such black hole? And as I was googling this, I was not able to get the exact answer right away. And so just to test ChatGPT, I basically copy-pasted my question, which is essentially, what is the nearest X-ray binary containing a black hole, pressed enter, and waited a few seconds to get the answer right here. Now this was intriguing, it was actually well articulated, but the thing is, this answer was incorrect, because this was describing that black hole we're talking about today, or one of them. This was describing Gaia BH1, the nearest black hole to us. But it was claiming this was an X-ray binary, where it was actually producing X-rays. I'm going to be talking more about this in that next video that I mentioned, but basically ChatGPT has a tendency to be extremely confident about its somewhat wrong answers. But there is a new update in ChatGPT 4. It actually tends to self-correct and does so really well. And so here's the part that really surprised me. I basically said, are you sure? Confidently, ChatGPT said, yes, I'm sure. The information I provided is from reliable sources. Is there anything else you would like to know? Now this really sounds like something from Reddit, where there is someone super confident in their ability, but sometimes provides somewhat incorrect information. But I kept going. Very confidently I replied, it's not an X-ray binary. And this really kind of blew me away. It was able to self-correct. I apologize for the confusion. You are correct. The nearest black hole to Earth is not an X-ray binary. And then it talks more about Gaia PH1. I'll be talking about this as well, so we'll come back to this in a few seconds. But this didn't answer my question, so what is the closest X-ray binary? The next answer was a little bit more generic. It basically mentioned that there are 22 known X-ray binaries in the Milky Way, and one of them is located in Cygnus constellation. First, but not the closest. Still not really that answer I was looking for. So I wanted to confirm, is it the closest? So basically it says no, but then comes back to Gaia BH1, specifically now saying that it's not an X-ray binary, but the closest black hole. And at this point, this is actually almost like a regular conversation. So then being, what is the nearest black hole in an X-ray binary? You can kind of see that at this point I was kind of giving up. I didn't think I was able to answer this. And holy cow was I wrong. This is the 7th reply. According to a study by Santana, the nearest black hole is known as V618 Monoceros at a distance of about 3500 light years away from us. That's the answer I was looking for, and turns out that it's actually correct. The study confirms it, nothing new has been discovered since, and more importantly, it provides all the references that you can sort of use to check all of this without needing to double Google this once again. And holy cow was this shocking to me. Because now we're going to be using this answer in the video to make another point. The point that previously, binary black holes were always in X-ray binaries, mostly because they're so easy to see. But, just like ChatGPT just told us, there are only 22 known to us, and the nearest one is about 3500 light years away from us. In contrast, the nearest black hole to us is actually Dormant. Gaia BH1 is about 1500 light years away from us, and there are now 2 Dormant black holes, with the second one, the one that was just recently discovered, now being the 3rd closest black hole at approximately 3800 light years away. And here's why this is important. These discoveries suggest that these unusual black holes are most likely the most common type of black holes, the solar mass black holes, in the entire galaxy. But because they're dormant, they're most likely going to be extremely difficult to find. Here's actually the list of the nearest black holes known to us, and the top 3 are basically that X-ray binary and 2 dormant black holes, both discovered in the last few months. All of the other black holes are essentially X-ray binaries as well, and are at much farther away distances. In case you're wondering, in our galaxy, so far this one is the farthest. It's about 30,000 light years away from us. But this new study that you can find in the description now discovers that second object known as Gaia BH2, another dormant black hole with very similar properties to the first black hole BH1, but extremely different to everything else. And because of this, currently the scientists have absolutely no idea how these black holes came to be. Their actual origin story makes no sense, or at least has no explanation. But I guess first let's talk about what's in these systems. So both systems, Gaia BH1 and Gaia BH2, are really similar to one another. They're both located in a binary system with a star in a somewhat eccentric orbit around a black hole. The first black hole discovered, Gaia BH1, is roughly around 9.6 solar masses in mass, with a Schwarzschild radius of about 26 kilometers. The second black hole is just a little bit smaller at 8.9 solar masses, and is slightly smaller in size as well. But both contain a star in a somewhat eccentric orbit, and a star that's very similar in mass to our own Sun. In the first star system, this is actually already a red giant, with a star that's about 1.07 solar masses, but it's about 8 times bigger than our Sun, with a slightly lower temperature of about 4300 Celsius. Essentially, this is what our Sun might become in the next few billions of years. But in the second system, the star is a little bit smaller at 0.93 solar masses, and the radius here is almost exactly as our Sun, with very similar temperature at 5600 Celsius. Or basically both of these systems contain relatively rare G-type stars, and stars that are so similar to our Sun, although I guess the distance to the black hole is maybe a little bit different. In BH1 system, the orbit takes approximately 186 days, and eccentricity is about 0.45. What exactly causes this unusual eccentricity, which by the way is really high for stars and for planets, is of course currently unknown. In contrast, Gaia BH2 takes about 3.5 years to orbit around the black hole, with a slightly higher eccentricity of 0.5. And so for some reason the properties here are just extremely similar. Very similar stars, very similar orbits, and both black holes seem to be dormant. And in this case, because this was Gaia looking for these objects, it only discovered them because of these minute changes in the motion of the stars across the night skies. This is what we refer to as astrometry. When it comes to, for example, planets discovered this way, only 2 so far have been found, and that's out of thousands of planets discovered using other methods. But in this case, these stars were actually wobbling way too much. It could not be a planet. They were shifting enough for this to be an actual different object, much more massive than the star itself. And because of this apparent motion, the only natural explanation was that there was a really massive, somewhat invisible object that could only possibly be some kind of a black hole. And so because of this confirmation, it now becomes a new mystery. What exactly form these black holes and these unusual star systems? Why exactly do both contain a G-type Sun-like star with a very eccentric orbit? Why are those stars so far away from the black hole? And the main question, how did these black holes form to begin with? Normally, these types of black holes are produced by various Type 2 supernova involving a much more massive star, but in this case, the second star should not really be in this position or in this unusual orbit. And more importantly, it's kind of difficult to explain the unusual eccentricity. Why isn't the orbit more circular? And so at the moment, these unusual black holes are most likely going to remain a mystery until more ESA's observations using Gaia telescope and the next data release planned for 2025. Because obviously the telescope is still collecting more data and is going to be sending even more in the next few years. Hello wonderful person, this is Anton, and today we're going to be discussing a discovery of yet another very massive black hole, but this time using an extremely interesting technique. A technique that's never actually been used before for this particular purpose. But before we talk about the actual discovery and how all of this was found, let's briefly discuss some of the record holders for the most massive black holes discovered and known to date. Now, a few years ago, I've actually made a video about one of these record holders, and it's a black hole known as Photon 618. It's located in a galaxy that you see right here, that potentially looks something like this if you were to come close to it, and is about 18.2 billion light years away from planet Earth, and potentially contains up to 40 billion solar masses, depending on what scientist you ask. Originally, it was actually believed to be about 66 billion solar masses, but this value has been recalculated to be a little bit smaller. Nevertheless, at this particular mass, it's almost at the limit of how big we think black holes can get. And even though it's so far away, it's visible as this bright quasar that you see right here, containing a luminosity of about 140 trillion suns. But a few years ago, a lot of recalculations and a lot of new discoveries led to two more supermassive, or technically ultramassive black holes. Black holes that potentially could be completely unexplainable using modern physics. We have this object about 2.6 billion light years away from us, potentially containing something that's even more massive, maybe up to 52 billion solar masses in total mass. And then we have another object in the middle of the Phoenix cluster, with this particular black hole being even more ridiculous, with the current estimate being up to 100 billion solar masses. And that's actually the double of what we think is even possible. And so how exactly this black hole can exist currently cannot be explained. But just like with previous black hole discoveries, it's really always about the way that it's all measured. Sometimes the measurements are just slightly incorrect based on the observations that are maybe slightly outdated. For example, in many cases, the observations are based on some kind of an emission coming from the black hole itself, where the flares produced by the black hole are then used to try to estimate the mass of the accretion disk and estimate the mass of the black hole. But that's not always correct, and thus leads to miscalculations later on. But then there is this unusual object. This is known as the Abell 1201 BCG. Bright Cluster Galaxy. It's roughly around 2.7 billion light years away from planet Earth, but in this case this very bright galaxy also seems to act as a gravitational lens. Or basically it produces an Einstein ring, and it's actually sort of visible if you look at it really close. It basically sort of resembles an eye with an eyebrow. And as you might know from previous videos, this can only be produced by a very massive object in the middle, usually a really massive galaxy with a lot of dark matter, that's able to produce these effects that can then be used to determine the total mass. But completely by accident, the scientists studying this particular object discovered something else within it. They actually discovered another tiny arc. Or when analyzing this lensing effect, they discovered that something in here was not really adding up if it was just caused by the galaxy and nothing else. Something else really massive was at the center, creating additional shapes. Now, the original larger arc was discovered approximately 2 decades ago, back in 2003. But the smaller arc was discovered back in 2017 using additional observations, and it wasn't really clear what was causing it until the scientists decided to work this out by creating various computer simulations and by trying to recreate this from scratch by using a hypothetical scenario where there were different objects in the middle of this central galaxy. Basically, they tried to see if there's maybe a black hole that's really massive that's maybe forming this. So they started to modify various simulations based on the total mass of the black hole, and in the process they started to discover that this arc would actually change in shape if the black hole was of certain mass. Eventually they discovered that one sort of a black hole was producing exactly what they were observing. That black hole would have to be approximately 33.2 billion solar masses. Although it doesn't have to be a black hole, it just has to be something really massive and really compact right at the center of this galaxy. And that most likely is a black hole. There's really no other way to explain this. And so after hundreds of thousands of different simulations, they discovered that the mass has to be 32.8 billion solar masses, making this one of the top 10 most massive black holes ever found, with the size of the event horizon being very similar to TON 618 at approximately 1300 astronomical units, way past the orbit of Pluto and nearly 10 times as far away as the Voyager probes, and also almost at that absolute limit of what the scientists believe supermassive black holes should be, which is actually about 50 billion solar masses. But I guess more intriguingly, even today there's really no explanation for how such giants can exist and why so many of these giants have already been discovered in really early universe, meaning that these black holes can form really quickly, or more importantly, why so many of them have been discovered pretty much all over the place, and how these ultramassive objects can actually even appear. At the moment the mechanism is really unclear. As a matter of fact, some of these black holes are so ridiculously massive that the scientists even had to propose a completely new term from them. Some of them are known as slabs, stupendously large black holes. And this black hole is almost at that limit. And although this particular black hole doesn't qualify as a slab, there's actually a very high chance that using this technique, the scientists might now start discovering even more of these objects with even higher masses, and thus create even more mysteries when it comes to their origin. But in this case, because of the overall accuracy of this technique, even though it's based on computer simulations, it does mean that the scientists might have actually created a very accurate way to confirm masses of various black holes, and might actually lead to more discoveries coming from a lot of other gravitational lenses. Quite a lot of these lenses have been discovered in the last 10 years or so, and many of them do contain unusual smears or unusual patches that are somewhat difficult to explain unless there's something really massive in the center. And that's obviously because in order to even produce this, you do need to have a really bright object behind and a really massive object right in front of it, creating the lens itself. And the other reason why this technique is really exciting is because it allows us to measure black holes that would be otherwise quite invisible. Previously, all of the massive black holes have only been measured when they actually emit a lot of different frequencies by producing astrophysical jets. With only one supermassive black hole, the one in the middle of the Milky Way galaxy, detected and measured by looking at the orbits of various very close stars, as you see in this beautiful 20-year-long time-lapse that technically resulted in a Nobel Prize a few years ago. But other galaxies and other supermassive black holes generally cannot be seen this way. It's extremely difficult to detect these stars, and so the black hole has to be active in order to determine its mass. But this provides us with a completely new technique where the black hole doesn't actually have to be active, and just has to be massive enough to produce at least some kind of a shape inside the gravitational lens, with the overall calculations also potentially being very accurate. But obviously it does require a gravitational lens and a perfect alignment between two galaxies in order to be able to calculate all of this. Hello wonderful person, this is Anton, and today we're going to be discussing some of the new discoveries coming from the center of the Milky Way, but also coming from centers of other galaxies in regards to very specific phenomenon that usually happens around central black holes. The phenomenon we refer to as TDE, the tidal disruption event that usually involves the central black hole and some kind of an unfortunate star approaching the black hole a little bit too close. And in this case we have several discoveries from different studies in regards to the nearest such event, but also in regards to this event happening around Sagittarius A star, the central black hole of the Milky Way galaxy. And so let's discuss all of this in a little bit more detail, starting with the discovery of what seems to be the closest such event ever found. The event you see in this image right here. And when it comes to various observations from other galaxies, today the scientists believe that such events usually occur every 10,000 years in the center of a typical galaxy. Or in other words, every 10,000 years we expect an average star to approach a black hole and basically create what you see right here. But to date, only approximately 100 of such events have been discovered in various distant galaxies, and mostly by observing various X-rays, and in some cases ultraviolet and optical light. And in pretty much most cases these events have been very similar. They involve a sudden brightening that usually lasts for just over a year, with very specific emissions that slowly decrease over time. But this time, the scientists studying the galaxy NGC 7392 that you see right here discovered something the scientists have never seen before. They found a TDE that was only visible in the infrared light and not in X-rays or UV light. Something that happened back in 2014 and 2015 and was initially missed by various surveys. But more importantly, this is the TDE that seems to be the closest to us, approximately 137 million light years away, and about 1/4 of the distance of the other closest TDE observed in the X-rays. Although the reason it's only visible in the infrared is actually because of an extremely dusty environment in the center of this galaxy. In essence, the center here just has way too much dust for most of the other light to get out, and because it's visible in the infrared, in theory we should be able to observe some of these events in the future by catching them with the James Webb Space Telescope. It hasn't happened yet, and obviously this particular event was already missed, but it's something that should be possible in the future. Now what about our own galaxy though? So let's jump back to the Milky Way that should be somewhere right here. Well, the Milky Way, by comparison, is a little bit more mild and dramatically more quiet. The observations from that other galaxy suggest that first of all the black hole there is a lot more massive as well, possibly as much as 8 times more massive, and is a lot more active, containing a much more active center. But the region of Sagittarius A star is really quiet. And the black hole here compared to other galaxies is also relatively small. It's just over 4 million solar masses. Nevertheless, in the last few years, the scientists have actually started to detect a few more X-ray emissions and a lot more flare-ups, suggesting that for some reason our black hole is entering a more active period. It's not entirely certain what it's caused by, but over the last few years, or more like over the last decade, Sagittarius A star started to emit a lot more X-ray flares, with a really big flare detected in 2019 that made the black hole about 75 times brighter. And with several hundred flares detected in the last few years, it looks like that on average all of them increased in brightness, implying of course that the galactic center is becoming a little bit more active for uncertain reasons. But it's obviously uncertain if any of this has anything to do with some kind of a stellar remnant, or if it's some kind of a dust cloud that's falling from some other region causing the increase in activity. But what is certain is that TDEs have definitely happened around the Milky Way, and the sign of an ancient TDE has now been found here as well. And intriguingly enough, this study suggests that it only happened 200 years ago, plus minus a few decades. And so here's how the scientists discovered this and what this implies for our galaxy. Even though the central black hole is still very inactive, it's possible to see previous activity by looking at interaction of ancient light with various structures around the center. And so, very similar to how the sun right here reflects from the clouds and announces its presence even though we don't see the sun itself, it becomes possible to basically identify previous events in Sagittarius A star region by looking at various gas clouds located in the vicinity of the center. And so here, by using various X-ray observations from X-ray Polarimetry Explorer, they discovered various clouds very close to the galactic center that were glowing because of X-rays, as if something powerful illuminated them coming from the center itself. And because light travels at the light speed, and the distance here was approximately 205 light years away from the center, the conclusion in this case was that something must have happened 200 years ago, and that something was very powerful, involved a lot of X-rays, but most importantly, only lasted a year and a half. Specifically 1.6 years, and involved a huge amount of energy, possibly equivalent to about 1.5 lunar masses, released all as pure energy, implying that for approximately a year and a half, the central region, or the black hole in the region, became approximately 100,000 times brighter, producing all of this energy, although most of this was in the X-rays and not really the optical light. And the only reasonable explanation for all of this, based on all of the observations from other galaxies, is a tidal disruption event. The overall timeline, the amount of energy, and the amount of X-rays produced match all of the previous observations. But even though astronomy was already sort of going on 200 years ago, and the scientists were already observing different stars and different phenomena, there's practically no way they would have seen this because we didn't have any X-ray observatories, and also because the optical light here would have been really dim. Although the obvious question would be, did it affect planet Earth in any way? Well, even though the overall X-ray emissions increased by 100,000 times, the distance to the central black hole is still really far, almost 26,000 light years away from planet Earth. And because of this, it would be almost impossible for any of these X-rays to do anything to our planet. which also means that the recent detections of the increase in activity should also not worry us at all. None of this will affect the planet. But this discovery is more intriguing in terms of the actual frequency of these events and in terms of what we think happens in various galaxies. Currently, when it comes to TDEs, based on the frequency and activity, the scientists generally divide galaxies into three types: blue, red, and green. Red galaxies are usually red because they no longer produce a lot of stars, and for this reason the scientists believe they also very likely do not produce a lot of TDEs. In contrast, blue galaxies produce a lot of stars and are usually much more active, which of course suggests that blue galaxies should have a much higher frequencies of TDEs as well. Although somewhere in between the two, the scientists also have so-called green galaxies, which don't produce that many stars, but produce some. This is the least common type of galaxies. And what's really strange is that, to date, pretty much the majority of all of the TDEs were actually discovered in these green galaxies, not blue as predicted. In other words, for some reason, galaxies that do not produce a lot of stars, but produce some stars, kind of similar to the Milky Way galaxy, seem to have the most stars falling into central black holes and produce the most disruption events. But the recently detected nearest TDE was from a blue galaxy that was producing a lot of stars. So there's definitely something that the scientists still don't really understand about the actual mechanism behind these events, or at least their frequency and what exactly makes them happen in some galaxies but not in other galaxies. But in terms of these events, right here in the Milky Way, based on this recent discovery, it of course suggests that these events are unlikely to be dangerous at all, and chances are we might be able to discover even more of these events by studying other clouds in the region and discovering other X-rays reflecting from other clouds, establishing the frequency of TDEs in the Milky Way.
Hello wonderful person, this is Anton, and today we're going to be talking about some of the recent discoveries in regards to these jets that you see right here behind me, the objects we usually refer to as astrophysical jets, a phenomenon that seems to form around various objects in the universe, including stars, including galaxies, and including neutron stars like the one you see right here, with one of the more iconic ones being this one from the galaxy M87, the galaxy that became famous for its black hole right in the center. Although galaxies like Centaurus A that you see right here represent some of the biggest objects in the night skies as seen from planet Earth. We actually discussed this in one of the previous videos you can find in the description. But in this particular video, we're going to be talking about the new discoveries, and specifically about discoveries of some of the farthest radio jets ever found and some of the longest ones discovered to date, which in the process allowed the scientists to discover something else about the formation of these jets, comparing them to, well, actually, another type of a jet, the type we usually find around airplanes. So the actual effects and the actual formation of the jets in this case seems to be kind of similar. And so first, let's start with that biggest jet discovered so far. It's actually from a relatively well-known galaxy, approximately 93 million light-years away from us, known as NGC 2663. In this case, the center of this galaxy seems to contain an active galactic nucleus, which basically means that the central black hole is active and is currently absorbing a lot of mass, producing a lot of energy in the process. Now, some of the first images of this galaxy presented it as this. Nothing unusual going on here. But very recently, the scientists behind this study right here, that used one of the Australian radio telescopes to look at it, discovered that it seems to contain another object that's about 50 times larger than the galaxy itself. The object in this case is the jet. So if you were to compare this to the iconic Centaurus A, where the jets are relatively small in comparison, the jets from NGC 2663 are at least 50 times larger than the galaxy. You can see the galaxy as a bright point in the middle, and they seem to be at least 1 million light-years across, shooting out material at almost the speed of light with huge amounts of energy. And so there's a tremendous amount of activity and huge amounts of power inside of this galaxy. The galaxy that seems to possess at least 10 times more stars than the Milky Way and resembles something that you see right here, a type of an elliptical galaxy that can also be referred to as an active galactic radio galaxy. But I guess more importantly, if this was visible to us using our own eyes, it would actually be bigger in size than the full moon. And that's at a distance of 93 million light-years away from us. But because we don't see radio frequencies with our eyes, it's obviously invisible to us. But there's actually something else really important that was discovered from this particular study. The scientists discovered that the matter between galaxies, the intergalactic gas,
seems to push back at the jets, which creates the shock diamonds that you see in this image, and it seems to resemble what we usually see around airplane jets as well. In the case of the airplane jet, as the material is being ejected at very high velocities, planet's atmosphere pushes back on the exhaust plume, which causes the jet to expand and contract, creating the shock diamonds that you see. And that's pretty much what the scientists observe coming from the black hole in this galaxy as well. As the material moves along the jet, it's being compressed in certain parts, which makes them glow more brightly, making them glow even more as the jet slams into the denser regions of gas, which of course implies that there is quite a lot of intergalactic matter in the vicinity of this particular galaxy. And this is something that's been observed around other galaxies from other jets as well. As a matter of fact, it's even seen in the iconic Centaurus A. But naturally, never really in these particular proportions, because this is one of the biggest discovered so far. Not the biggest, but definitely the biggest in terms of the size in the night skies. As I mentioned, it's bigger than the full moon. Although if you'd like to learn more about the biggest jet discovered ever, check out one of the previous videos in the description. But as we know today, these particular jets and the effects produced by these black holes are pretty much ubiquitous. They seem to be everywhere in the universe. We don't obviously always see them though, because it's really always about the perspective from which we're seeing all of this. Now, for example, we're able to see the jets in the Centaurus A because it's relatively close to us. And we're able to see these ones because they're very, very large. But in order to see some of the biggest radio jets out there, we actually have to be kind of lucky. The arrangement and the orientation has to be just perfect. And so that's pretty much what has been recently discovered in one of the other studies in regards to one of the most distant radio quasars ever found, possibly even the farthest discovered to date. It's definitely the most distant radio source found so far, and is actually sending light to us from when the universe was only about 700 million years old. In other words, the light here took 13 billion years to reach us. In terms of the actual distances, it's about 28.7 billion light years away from us. And so this seems to be the farthest radio signal ever found, and it's really because of the extreme power of this particular galaxy, and very likely extremely long and very powerful jet like the one I just showed you. But in this case, instead of being sideways, it seems to be almost directly pointed at us. And here's the image produced by the scientists. It doesn't really show us much, except for an extremely bright radio spot right in the middle that seems to be kind of stretched because it's not perfectly aligned. But just like with the iconic image of M87 black hole, it's important to understand that this is a false color image. We're not really seeing the light here. The yellow and the orange here is simply radio light that was converted to the colors we can see. And so that's very similar here, not the actual light, just the radio light. With all this being a result of a very massive black hole, at least 300 million solar masses, that's consuming the gas extremely fast. As a matter of fact, it seems to absorb the mass at the highest rate seen so far, which ends up producing approximately 600 times more luminosity compared to the Milky Way galaxy. But what's interesting is that it seems to be only happening now. And I'm saying now because when compared to the data from approximately 20 years ago, the discovery was that it seems to have lost some of the radioluminosity in the last few years. Which of course implies that it was very likely much brighter and much more powerful and absorbed even more mass just 20 years prior. But because this galaxy is also surrounded by a very large bubble of ionized gas, it essentially amplifies the radio frequencies, creating the unusual elongated shape with a lot of protrusions. And so a lot of the data coming from this quasar and coming from these radio emissions can actually help the scientists to directly analyze and to even map some of the early gas in the early universe, because a lot of these radio emissions are going to be passing through this gas. But I guess more surprisingly, when studying this, completely by accident, the scientists discovered another radio source that you can kind of see on the right. They don't really know what it is yet, or even how far away it is, but it seems to be another radio quasar, which are not particularly common in the early universe. And this one could even be farther away. Although if they are actually close together, and if this is some kind of a formation of early galaxies, that would be a pretty remarkable discovery. Mostly because the scientists have actually been trying to find examples of these early galactic clusters in order to understand how early galaxies came together and how they created the cosmic web, eventually forming the universe we know today. And so discovering these very powerful jets, specifically the ones producing radio frequencies that tend to pass through a lot of gas, can definitively help the scientists analyze the early universe, helping them understand how everything evolved over the past 13.8 billion years. And so because of the very powerful radio telescopes in Australia and South Africa and a few other countries that started operating in the last decade or so, we're now getting more and more data, helping the scientists uncover new mysteries and resolve a lot of old questions, but also uncover things we've never seen before, like this, or the jets in NGC 2663. Although I'm sure more and more radio discoveries are going to be made in the next few years, especially because a lot of these telescopes have just recently upgraded their capabilities, with the Australian ASCAP now being able to detect so much more than ever before, and we'll actually discover some of these recent discoveries in some of the videos in the description. We're going to be talking about spinning black holes, and more specifically we're actually going to be discussing the recent paper that managed to measure the spin of a very massive and somewhat distant black hole, or actually a supermassive black hole, technically known as a quasar, located about 3.4 billion light years away from us, and very likely containing 30 billion masses of the Sun. A black hole that you can see pictured right here, known as H1821 plus 643. And in this case, in one of the recent studies, the scientists were able to measure the spin of this black hole, which allowed the scientists to confirm how some of these most massive black holes are very likely produced, and why certain other black holes never really get to become so massive and end up a little bit on the smaller side. For example, the black hole in our own galaxy is nearly 10,000 times less massive, and all of this could be due to the spin of the black hole, at least to some extent. So the spin in this case may play a big role in how much mass a black hole can actually absorb. But that also means that we have to briefly talk about the rotation or the spin of black holes. Now it's actually a little bit difficult to visualize, but as every other object in the universe, black holes also spin. We're not talking about the accretion disk that you see right here, we're talking about the black hole itself, the blackness on the inside. And this spin can actually produce very interesting effects, changing how the black hole affects the environment around it. So here's actually an image of a black hole that's spinning at approximately 99% of the speed of light. It ends up creating effects that would not be possible otherwise. Now, as a result of this, technically there are 4 different types of black holes. We have the rotating and non-rotating black holes, and we have the charged and non-charged black holes. And though in theory all 4 could exist, when it comes to the actual practical discovery of black holes so far, we know that all black holes seem to rotate at least to some extent, and it's believed that most black holes have at least some charge. In other words, pretty much all black holes out there have at least some rotation and some charge that usually comes to them from various sources that fall into the black hole itself. This is also sometimes known as the transfer of angular momentum, and in this case it also applies to the transfer of charge. And since every single object we've detected so far has at least a little bit of rotation, it's kind of obvious to expect all black holes to have some kind of a rotation as well, even if it's just a small rotation. But we know that some black holes spin super fast. As a matter of fact, many of the smaller black holes, especially the ones that are usually only a few masses of the Sun in mass, spin to the point where they're at their limit, almost at the speed of light. Not so long ago, there was a paper about a very famous black hole known as Cygnus X1. A black hole that's pretty well known because it's basically the first black hole ever discovered. And in this case, it was determined to spin almost at its maximum limit, basically implying that smaller black holes will usually spin at an extremely high speed, which will very likely produce a lot of very unexpected properties. Although obviously at the moment, we're still not really sure what these properties are. But this is very common of many different black holes, and obviously massive black holes spin as well, especially because some of the massive black holes receive so much mass from everywhere. And a lot of mass that falls into these black holes will always contain at least some angular momentum, which will then increase or decrease the spin of the black hole. And so, for example, several papers, like the one you see right here, explore the spin of the famous M87 star black hole. And it's been determined so far that this black hole seems to have a somewhat average spin, not too fast, not too slow. which is sort of expected of a supermassive black hole. This one is also at least 1,000 times more massive than the one located in the Milky Way galaxy. And mostly because of the way that these black holes grow. Generally, when it comes to these really massive black holes, their mass is absorbed from every single angle. Their mass comes from both gas and different stars colliding with the black hole. And today it's believed that they usually grow by absorbing mass in random events and at random times. And so because of this randomness, they would usually acquire an average amount of angular momentum, which means that the rotation would not really increase or decrease too much. It would stay kind of average. Whereas smaller black holes or less massive black holes would very likely mostly absorb their mass from the accretion disk and not so much from anything else. And because of this, and also because the mass seems to come from the same angle at all times, in theory this means that a smaller mass black hole will always have much higher spin, much faster rotation. Or at least that's the theory. But to try to test this, the scientists need to find a way to measure the spin of various black holes. And it just so happens that faster spinning black hole will actually have certain effects around it. And specifically, it's going to allow certain types of mass to come much closer to the center of the black hole than would be otherwise possible. So in other words, because of the spin, it's possible to have a lot more stable orbits around the black hole. It even creates an area known as the ergosphere, which does create some really interesting effects. It's an area where, in theory, it's possible to inject an object and then have this object come out with even more energy than it had originally. In other words, it becomes possible to kind of steal some of the energy from the rotating black hole. A concept that's known as the Penrose process, named after the Nobel Prize winner Roger Penrose, who proposed this years ago. And the thing is, using analog black holes here on planet Earth, specifically using acoustic black holes, the scientists have been able to prove that this indeed exists, and it seems to be possible to extract energy from various black holes as long as they spin and as long as they have the area known as the ergosphere. Meaning that these spinning black holes are actually extremely interesting for a lot of different reasons. One reason being unlimited energy. In theory, it becomes possible to basically extract energy from these black holes, creating a source of free energy. Although in this case the energy comes from the spin of the black hole, meaning that every time you take some energy away, the black hole spins a little bit slower. But nevertheless, it seems to work, at least based on the experiments from planet Earth using acoustic black holes. You can learn more about this in the video right there, or in the description below. But this time, using NASA's Chandra X-ray Observatory, the scientists once again were able to measure the spin of a very interesting black hole. The one visible right here. Well, technically it's a quasar. And in this case, this quasar is, as I mentioned before, 30 billion masses of the Sun. One of the most massive black holes known to us. And so as I mentioned before, if the black hole is spinning, it allows some of the particles to come much closer to the center. Because a spinning black hole is going to drag the space around it, allowing the matter to orbit much closer to it than would be otherwise possible. And when the material in the accretion disk comes closer to the black hole, it's going to end up producing certain types of X-rays that would be different if they were produced slightly farther away. This is all because of the gravitational effects from the proximity to the black hole. So basically the X-rays coming from closer are going to be slightly redshifted, whereas the X-rays coming from farther away are going to be less redshifted. Which means that by using X-ray data, it becomes possible to measure the rotation of a certain black hole. And in this case, the scientists determined that H1821 plus 643 spins approximately half as fast as most of the black holes similar to the one located in the Milky Way galaxy. Or in other words, a black hole that's ridiculously massive is going to be spinning much slower than the one located in our own galaxy. Which sort of gives us a little bit of evidence for how we think these black holes grow. So just as I mentioned before, it's believed that more massive black holes will usually have mass coming from everywhere, and because of this they will probably spin slower. That's exactly what the scientists discover in this case. Smaller black holes will have mass mostly coming from the accretion disks, and as a result spin faster because the mass is always coming from the same angle. And that's kind of what we discover with some of the smaller black holes as well. In other words, the study and this observation kind of proves the main ideas the scientists have about the growth of various black holes. Massive black holes will have mass coming from everywhere, grow very fast, and thus acquire much lower angular momentum. Smaller black holes will usually have mass coming from just one angle and will acquire a lot of spin. Although in this case, the massive black holes also get a lot of their mass from the collision with other massive black holes, which would dramatically decrease their overall spin as well, mostly because it's unlikely that these two black holes are going to be spinning the same way. Which I guess also implies that a lot of these supermassive black holes usually grow through some really violent, very chaotic events, involving a lot of mass coming from every single direction and involving many different collisions. Smaller black holes don't seem to have as much of an excitement, and the one in the middle of our own galaxy very likely experience very few of these events. The Milky Way's black hole, Sagittarius A star, most likely spins much faster than this black hole, and thus also contains a lot less mass. And obviously some of the smallest black holes we've discovered so far spin the fastest. As a matter of fact, as of today, the black hole known as GRS 1915 plus 105 seems to be the fastest spinning black hole we've ever found, rotating at 1150 times per second, as close to theoretical limit as possible, as close to the speed of light. Although in this case this is a relatively small black hole, it's what's known as the stellar mass black hole, approximately 10 to 18 times the mass of the Sun. Either way though, I think it's important to understand that black holes in general do have different types. And in this case, the spinning black holes are actually very different from non-spinning ones, or from the ones that spin slowly. Spinning black holes are usually referred to as the Kerr black holes. But as I mentioned before, spinning black holes can also be charged, and in this case they're known as the Kerr-Newman black holes, and very likely possess very different properties to anything we can even imagine. And that's something we'll discuss in some of the future videos. So, in theory, depending on the rotation and the charge of the black hole, the properties can change quite dramatically, producing very different effects that would not be possible around a simple black hole that doesn't spin much and doesn't have much charge. So one day we might have to stop using the term black hole to describe these different objects, because some of them might actually possess very specific effects, something that we're still trying to investigate and trying to learn more about. Although in this case, this relatively slow spinning supermassive black hole definitively confirms that very massive black holes seem to grow through chaotic events involving collisions with other black holes that very likely make them lose a lot of spin. But it also means that the black hole in the middle of the Milky Way galaxy, Sagittarius A star, could be spinning really fast, and that's something that I would love to hear more about, because at the moment it's not actually known what the spin of the black hole is. And so for all we know, our galaxy might have one of the most unique black holes out there. Hello wonderful person, this is Anton, and what you're watching here is a new simulation that was recently released by NASA that shows us what happens when various stars, including stars similar to our own Sun, approach a massive black hole. The event that we usually refer to as the Tidal Disruption Event, TDE. And because this is such a fascinating event, with so many of them being discovered in the last few decades, I wanted to discuss exactly what was discovered in this particular new study, and also discuss some of the most well-known facts about these events, including some of these surprising findings. But let's actually start with a bit of a history, and specifically history in regards to black holes, and one of the scientists, astrophysicists, who's a little bit underappreciated in his original proposals and his original theories. As a matter of fact, this particular person is not really well known almost at all. Unlike Stephen Hawking, unlike Albert Einstein, despite some incredible propositions from this particular scientist, his name is not really commonplace even in his home country. And here I'm talking about Jean-Pierre Luminet, the French astrophysicist who even none of my French friends are aware of, but is an extremely important person in astrophysics and has actually made some incredible discoveries back in the 70s. As a matter of fact, Jean-Pierre Luminet was the first person to actually create an image of a potential black hole. By using rudimentary computer simulations, he was able to create this right here back in 1978. And considering that this was created more than 40 years ago, before advanced computer simulations, and also since this is relatively accurate in the way it presents black holes,
This by itself is a pretty big achievement. But he also made a lot of other propositions in regards to other events around black holes. And when working in Paris Observatory back in the 80s, Jean-Pierre Luminet and Brandon Carter invented the concept known as TDE, Tidal Disruption Events. Their first work was originally published back in 1982 in Nature magazine, and so in essence he was responsible for sort of helping us understand how these particular events work and what happens to various stars when they approach a black hole and when they shred it and spaghettify it into essentially what you see right here. And he actually referred to this model as the stellar pancake outbreak model, or pancake flambé in French. And in essence, because of the way that the star is shred, it sort of resembles a pancake once the star material starts to circulate around the black hole, with that one moment when a lot of energy is released from this activity being referred to as a pancake detonation or pancake explosion. But just like a lot of theories, it took quite a while to prove this, and it basically took over a decade, so until 90s, to finally show that this is exactly what happens and to discover one of these events for real. The first one was discovered using the German/NASA satellite known as Rosat that was able to discover the first X-ray emissions that seemed to match such an unusual event. And today all of them can be actually discovered in the catalog known as the OpenTDE catalog, the link for which you can find in the description. As of December of 2021, there are currently 98 different entries, with the most recent one being this event right here that was discovered somewhere in this galaxy back in June of 2021. And TDEs have also explained some of the unusual observations from various supernovae, such as the famous supernova discovered in 2015, known as Assassin 12LH, that was created when a star approached the black hole relatively close, and prior to it being destroyed and essentially absorbed, it sort of detonated, creating a superluminous supernova. But because generally speaking, when these tidal disruption events occur, a lot of the mass ends up in the accretion disk and starts to produce a lot of energy as most of this starts to circulate and emit different types of radiation. A lot of studies suggested that many of these emissions will be in different types of frequencies, including ultraviolet and the X-ray radiation, which will then be absorbed by the surrounding disk that's already around the black hole. And because of this, as a lot of this radiation hits the disk, it's going to be producing different types of radiation, mostly infrared radiation. And so by sort of measuring the differences in different frequencies detected from a certain event, it becomes possible to literally map the black hole itself, which kind of works like radar, by basically measuring the reflections from the black hole's disk, and by looking at different frequencies and also the delay between different frequencies, it becomes possible to create a three-dimensional image of the region around the black hole, and it's actually been done several times now. And some of the best examples of this usually come from supermassive black holes that have large enough disk where a lot of the emissions will then be easily visible. But I guess one of the other questions is, well, what exactly happens to the star itself? Well, here's one example. Normally, a star basically gets spaghettified. Because of the tidal disruption here, the entire star sort of turns into a really long spaghetti of various gases, with most of the gases then creating either the accretion disk or the astrophysical jets, and just a tiny part of the entire material then falling into the black hole itself. But in the recent simulation that you can also find in the description below, the scientists were more curious to discover if this happens to all of the stars. As a matter of fact, what if a star was more similar to our Sun, or even smaller in size? What exactly would happen to those stars? Well, so they did this by simulating a supermassive black hole, and by then also simulating various densities of stars approaching at a certain distance. And in a nutshell, here's what all of this looks like. Notice how some of these objects do become spaghettis, but some of them, at least one of them, doesn't. It actually remains as a star with just a little bit of material lost. And that of course implies that some of the stars will survive this process and will potentially even remain as typical stars. Which is actually a really important discovery because a few years ago the scientists studying our own supermassive black hole, Sagittarius A star, the one in the center of the Milky Way galaxy, discovered these peculiar objects we currently refer to as G objects. The video about this is somewhere right there. These G objects seem to be basically stars that don't really get spaghettified, or at least that's what the scientists think they are. And there are quite a few of them in the region around our own supermassive black hole, which also suggests that they probably exist around other black holes as well. And so this new simulation sort of helps us understand how all of this probably works. And so for this particular study, what the scientists did using a supercomputer is first of all create 6 virtual black holes with masses between about 100,000 and 50 million masses of the Sun, which would qualify as both intermediate and supermassive black holes. Just as a comparison, the one in the middle of our own galaxy is about 4.1 to 4.3 million masses of the Sun. Different values have been proposed based on different studies. Now then they took a few stars with different sizes, with some of these stars being very massive, about 10 masses of the Sun, but some of them being very small, about 15% the mass of our Sun. And then they basically chugged all of these stars into those black holes, seeing if any of them survive. And here's roughly what happened to all of them. Notice how the ones that are really massive pretty much fall apart, becoming spaghettis. But the smaller ones, specifically the one that's only about 15% the mass of the Sun, survives. While at the same time the one that's basically very similar to our Sun, 1 solar mass, also survives. These seem to be the only survivors in this particular simulation. And this helped the scientists work out exactly what you need for the star to survive and not to get spaghettified. Density. Density is the most important factor. Only the stars that were denser ended up not getting spaghettified, with some of them maintaining most of their mass, whereas the stars that were massive all got shred apart and became spaghetti. Although all stars, no matter how dense they were, lost some of their mass. Some of them were only partially tidally disrupted, but some of them were entirely disrupted, disappearing completely. But more importantly, they were also able to figure out the proportion of the star's mass that's going to be lost depending on the original mass of the star, the density of the star, and the mass of the black hole. In other words, they worked out the expressions needed and the math needed to figure out if the star is going to survive or not. And actually some of these stars, the ones that do survive, remain as stars. They actually still have nuclear reaction on the inside, and some of them, because they lost some of their mass, can actually, in theory, live even longer. Instead of billions of years, some of them might survive for trillions of years because they become red dwarfs. But I guess interestingly, because one of these stars was extremely similar to our Sun, and it was also the star that survived these passages, that's what kind of makes this a little bit more intriguing. It means that if, in theory, something similar to our Sun, or even our Sun, passed very close to the supermassive black hole, there's a very high chance that it's actually not going to get spaghettified, and it's very likely going to survive. But planets are going to disappear. Nothing will survive in orbit of these stars. Pretty much all of the tidal disruption events are going to strip the star system of any object in its orbit, so Earth would definitely not be there anymore. Nevertheless, a really interesting study, and a study that potentially helps us solve the mystery of these G objects discovered a couple of years ago. So it looks like G objects are basically just very dense stars, potentially with a lot less mass than some of the other stars in the vicinity. Although I guess for now, that's kind of all we know.
Hello wonderful person, this is Anton, and today we're going to be discussing a pretty unusual discovery coming from a somewhat distant galaxy, where a pair of astrophysical jets that resemble something like this were able to do something that nobody has ever seen before and currently does not have a very good explanation. In essence, changing the orientation of these jets from what you kind of see right here, when the jets are visible from the side, like in the Centaurus A galaxy, to something like this, where the jets are almost directly pointed at us. Which basically also changes the type of the galaxy this is. Even though originally this was a radio galaxy, it's now become what's known as a blazar. And this has never been seen before. But I guess more importantly, nobody knows exactly why this happened. So let's discuss this discovery in a little bit more detail, but first a little bit more about this galaxy. A galaxy sort of visible in this image, located approximately 650 million light years away from planet Earth. And the scientists studying various galaxies back in 2016 confirmed that this galaxy was one of many distant radio galaxies containing really large radio jets. Once again, very similar to Centaurus A, one of our neighbors, but actually more similar to one of the more iconic galaxies known as Hercules A, These extremely large jets very often expand for thousands of light years and sometimes create some of the largest structures in the entire universe. One of the previous videos that you can find in the description discusses this galaxy you see right here, known as Alcyone. The galaxy is several million light years across and basically the largest galaxy we've ever discovered. But in this case, this is obviously only visible in radio light, with these emissions from the jets interacting with various intergalactic dust and thus creating these radio emissions and these very large protrusions. None of this is visible in any other light, and because of this, these galaxies have always been known as radio galaxies. But from what we know about the jets in general, it's really always about the orientation. If you were to somehow look at this galaxy from a different direction, or just to give you a kind of an illustration here, if you were to see this from, let's just say, this direction or this way, you would start seeing something a little bit different. As a matter of fact, you would start seeing a lot of other emissions in a lot of other frequencies. This is what's known as a quasar, and these are some of the brightest objects out there. But in case of quasars, most of this light is actually produced by the accretion disk, not so much by the jet itself. And so in this case, the combination of the jet's emission and the orientation from the accretion disk managed to create extremely bright light visible in many different frequencies. So bright, as a matter of fact, that these are visible from billions of light years away from planet Earth. And as we've discussed in some of the previous videos, many quasars today are used in different types of navigation, including extremely accurate measurements in regards to GPS. Mostly because they don't really move much across the night skies, and because they generally produce relatively similar emissions if you look at them long enough. There is a lot of variation, of course, but overall, it's usually very easy to recognize a specific quasar. Over time, they tend to do very similar things. And they can actually last for millions and even billions of years, as long as there's material falling into the black hole, creating the accretion disk and feeding the black hole. But as you might have learned from one of the previous videos, when the jet is pointed this way, you get some of the brightest objects in the entire universe, blazars. And in case of a blazar, usually the jet is so bright, mostly because it's pointed directly at us, that you can't really see much else. It even overshadows the accretion disk and thus makes calculations very difficult. Blazars, however, are much more rare, because you have to get really lucky to get a perfect orientation of the jet toward planet Earth. Which is why this particular galaxy was actually a huge surprise to the scientists doing this recent investigation. Turns out that this galaxy is a blazar. Or basically, when the scientists looked at this galaxy using multi-wavelength observation, they discovered that the jet in this case is pointed directly at us, producing a lot of bright light in a lot of different frequencies. But that's kind of strange because years ago, back in 2016, and even today, the radio jets are also visible, but they seem to be pointed in a different direction, almost 90 degrees away. Which makes this galaxy really strange. It seems to be both a radio galaxy and a blazar. And at the moment there's really only one explanation to what might have happened here. For some reason, sometime in the past, the black hole orientation, and specifically the accretion disk and the astrophysical jet, suddenly shifted by approximately 90 degrees, pointed at planet Earth. But in this case we're talking about a central black hole, an object that's at least several million solar masses in terms of mass, and possibly up to several billion. In order to nudge such an object, you would require a lot of power. Something really catastrophic must have happened inside this galaxy in order to make this happen. And this something must have happened not so long ago. Well, we're talking about maybe thousands, maybe millions of years, not more than that. And really the only explanation right now is maybe another massive black hole and possibly a galactic collision. And so, for example, if two massive galaxies collide and their black holes combine, there's a slight chance that maybe the final project changes the orientation just enough to shift by 90 degrees, although the actual chance of this happening is extremely unlikely. Basically, you would need to have a perfect collision with a perfect distribution of matter where suddenly things move by 90 degrees. Not impossible, just extremely unlikely. Or potentially a collision with another really massive object, most likely another massive black hole, coming from somewhere else. But once again, the actual things would have to get extremely lucky for all of this to shift by 90 degrees. Alternatively, maybe the black hole was always actually pointed that way toward us and only recently started to become active and essentially became a blazar, with the radio jets possibly produced by something entirely different. As a matter of fact, the current jets have been observed in radio, optical, infrared, X-ray, ultraviolet, and gamma ray emissions, so they definitely exist and are definitely pointed toward us. But the radio jets seem to be a little bit older and must have been created many years ago, indicating radioactivity coming from this galaxy sometime in the past. So maybe there is something else going on inside the galaxy to explain these radio jets. Now, one potential explanation is a phenomenon known as X-shaped radio galaxy. And so literally galaxies that seem to contain some kind of an X shape formed by various types of interaction in the middle and related to the central jet. It's actually not entirely clear how these are produced, but some explanations involve the change of spin of the black hole in the middle, or maybe a binary system in the center, or once again possibly an accretion disk that seems to form in a very different way from the previous accretion disk, creating a kind of a double jet. But both of these jets are usually in radio frequencies only. In this case though, the galaxy seems to be producing light that's not just radio light, but once again in a lot of different frequencies, including very energetic X-rays and gamma rays. And so in this case, it didn't just change the orientation, it also changed the frequencies, literally changing the type of galaxy. And so whatever happened in this galaxy around the central black hole currently is a pretty big mystery, and so far this is the only such galaxy discovered, so I'm sure we'll be talking more about this in the future. Although intriguingly, approximately a day after this discovery, there was this beautiful picture from Hubble showing us the galaxy known as Z229-15, a galaxy that in a nutshell explains to us that some galaxies are just really weird. Although in this case, when they posted the image, they also gave it a kind of a tongue-in-cheek name, the Everything Everywhere All at Once galaxy. And that's because this galaxy just happens to be an active galactic nucleus galaxy, AGN, also a quasar, and also a Seyfert galaxy. Several types all at once. And that's because generally all of this is produced by the same thing. Supermassive black hole in the middle, consuming a lot of mass and producing a lot of energy. But depending on the location, orientation, and depending on the size of the black hole, it can sometimes appear like a regular galaxy with a bright center. And because it has an active galactic center, it's known as AGN. But because it's also so bright and visible from very far away, it's known as a quasar. But because you can actually see the outline of the galaxy in this case, and the quasar is not just some really bright distant object, it's also known as a Seyfert galaxy, Seyfert 2 to be more exact, which sort of highlights the main point. These massive black holes, powerful black holes, can generally produce a variety of very unusual effects, very unusual phenomena, and some really intriguing looking galaxies, including of course some record holder galaxies, the largest galaxies in the entire universe, or even galaxies possessing really unusual shapes. But all of this just a result of interaction of the central black hole with the environment around it. Although in this case, the scientists might have actually observed a completely new effect nobody knew existed. Some black holes seem to change orientation and possibly even entirely change their properties, basically turning around 90 degrees and becoming something extremely powerful. But how this happens, that's of course going to remain a mystery for a pretty long time. But we'll probably come back and talk more about this if the scientists discover something else very similar, or if there's a little bit more clarification about what exactly happened in this unusual galaxy. Hey look, something else is spinning around me once again. Hello wonderful person, this is Anton, and today we're going to be talking about some new mysteries discovered in regards to phenomena that are already mysterious to begin with. Phenomena involving black holes. And more specifically, we're actually going to be discussing a relatively recent concept that the scientists were able to discover only 3 decades ago, the concept known as the TDE, or Tidal Disruption Event. In a nutshell, representing something like this. When a star or some kind of a star-like object passes relatively close to a relatively massive black hole, with the star falling apart, very likely creating some kind of accretion disk around the black hole, and then very likely producing a lot of high energy emissions, which can then be seen from really far away and have actually been detected several times now using a lot of modern telescopes. The phenomenon that involves the concept of spaghettification, where the object is literally spaghettified or turned into a very long spaghetti and then sort of falls into the black hole, although the majority of the material ends up producing the accretion disk. And although theoretically the scientists believed that they kind of understood how all of this happens, very recently another major mystery was uncovered and have been reported in 3 separate studies, with some of the scientists referring to this as radio bursts from zombie black holes. And so let's talk a little bit more about this because it is once again somewhat intriguing and somewhat interesting. But first, a little bit of history. The initial idea behind TDEs was proposed by 2 scientists working in the Paris Observatory, the iconic Jean-Pierre Luminet, the French astrophysicist who was actually the first to create a simulated picture of a black hole back in the 70s, and his colleague Australian Brendan Carter, who along with Luminet back in the 80s proposed the idea of these tidal disruption events, which would involve a massive black hole, some kind of a star, and a lot of spaghettification effects, which they believed would produce very specific types of emissions. And within about 10 years they were proven correct when some of the first black hole interactions started to be discovered. This was found back in the early 90s using the Rosat satellite, one of the first X-ray satellites that was able to produce and detect quite a lot of interesting data. But since then, several dozen different TDEs have been already discovered and confirmed, and most of them seem to exhibit properties originally predicted by these two astrophysicists. But naturally, all of these detections were not without mysteries. For example, some TDEs were only partial, meaning that at the end, there would still actually be some kind of a star-like object left behind. Some of the recent studies simulating this discovered that it basically all has to do with the mass of the star. Stars that are similar to our own sun, or are even less massive, are generally going to survive the TDE, even though they are going to lose a large chunk of their mass, while more massive stars will most likely get completely destroyed, creating a much larger accretion disk. And the majority of the star material in this case is going to be creating the accretion disk and all of these very powerful emissions, with only a very small part of the star's mass making it inside the black hole. Although interestingly, even among some of these recent discoveries, unusually some of these sources were actually quite visible in the ultraviolet or even visible light, something the scientists did not really anticipate, with some of these black holes being able to produce more light than a typical supernova for several months at a time, but afterwards returning to their quiet state and becoming more or less invisible once again. And so even though there were some mysteries in regards to the emissions detected, most of them could be explained one way or another. But that's of course until now. In these 3 separate papers, the scientists discovered something nobody can explain or anyone expected at all. For some reason, some of these black holes reawakened and became active once again months or even years after the initial disruption event. And at the moment, nobody is certain what's exactly triggering these unusual delayed outbursts, with this one here being the first discovered, back in February of 2021. This was a radio burst that became active 6 months after the initial TDE. And though obviously it could have been explained by maybe something else falling into the black hole, not so long after this detection, the scientists discovered more. In this case, this was a very unusual rapid increase in radioactivity 2 years after the initial disruption by a relatively distant black hole. And then another one was found in a completely different galaxy, but in this case emitting radio frequencies but also X-rays. And so because these black holes seem to come back to life for unknown reasons, the scientists refer to them as zombie black holes. But I guess more importantly, at the moment there is no explanation for why this happens, and because this doesn't happen in every case, obviously presents a mystery nobody knows how to answer yet. But more importantly, because of these new detections, the scientists now think it might provide us with a lot of answers about the mysteries of black holes, and more specifically the mysteries of the formation of their jets. Since these galactic jets have so much power over the evolution of different galaxies, their origin and their influence on the galaxies is currently one of the more important mysteries the scientists are trying to solve. But at the moment, there are only some theories explaining their origin. Most of them involve the magnetic fields and the magnetic lines formed around black holes by the very powerful accretion disks. And in this case, any radio wave emissions coming from these black holes can definitively help the scientists answer some of these questions. These radio waves are believed to be created when the plasma expelled from these jets crashes into some of the gas surrounding the massive black hole in the center, which in this case is believed to happen right after the star falls apart and creates the accretion disk, which then slowly starts to form the jets around the center. And so by detecting these delayed radio waves, the scientists might be able to resolve the mysteries of the formation of these jets. But when it comes to the actual formation of these radio waves, the scientists have at least one possible explanation coming from smaller black holes. Here we're talking about the systems often referred to as the X-ray binaries, the system with a black hole and some kind of a star, where the black hole absorbs the mass from the star and creates various X-rays. And so in this case, some of this gas that's spaghettified and forms the accretion disk could actually stay around much longer, for months or even years at a time. But with time, this disk that's initially relatively thick grows much colder and much thinner and becomes a lot more unstable. And eventually, because of the interaction with the magnetic field or the magnetic lines from the black hole, this disk can break apart and suddenly release some of the material into the outskirts of the black hole. In some sense, kind of similar to how our sun often has these magnetic reconnections, which sometimes produce solar storms. And this material, as it travels away from the black hole, ends up crashing into the gas nearby, which then results in the production of very powerful radio waves and potentially some other emissions. And so in other words, all of this might have to do with the instabilities in this accretion disk, but also with very specific interaction between the magnetic lines and the density of the gas itself. Although the scientists still do not have the definitive answers for why this happens, but they do believe they've already discovered several other candidates that have not been published anywhere. As a matter of fact, this seems to be a relatively common phenomenon that nobody noticed before. But like I mentioned, it's a phenomenon that could help the scientists solve a lot of mysteries about black holes and about how they form various features in their vicinity. And more importantly, what happens in the accretion disk and the jets when various objects fall into the black holes and become spaghettified. So a few years ago, the scientists predicted this very intriguing event that was supposed to occur in October of 2022. An event involving a distant object suddenly becoming one of the brightest objects of its kind and creating a lot of emissions all at once. And here we're talking about emissions in a lot of different frequencies, anything from radio waves all the way to very powerful X-rays. And the reason they were pretty certain it's going to do so is because this object has been doing so extremely regularly every 11 to 12 years since the scientists started observing the night skies, with even some of the earlier observations from roughly around 120 years ago showing us that this object was actually doing so even back then. Yet in October of 2022, even though it was expected, nothing here happened. And because nothing here happened, and something was expected to happen, relatively recently the scientists released this paper that as always you can find in the description below. So in this video I wanted to actually talk a little bit more about exactly what this object is, exactly what the scientists now think about it, and why they believe nothing was detected even though everyone expected it. And so essentially it's a bit of a mystery, but possibly not a very big mystery, because this particular paper does seem to resolve it. First, what exactly is this object, which is actually why I wanted to talk about it. This object is known as OJ287, one of the most well-known extremely bright objects in the night skies, occasionally becoming the brightest ever. This is a blazar. And I think one of the best ways I can explain very quickly what blazars are is by basically using the simulation from a space engine. So this is a central black hole, and specifically here this is the famous M87 black hole, whose picture was the first picture ever taken of a black hole, and this is a pretty good illustration of what it might actually resemble. It has a really large torus around it, and two very powerful astrophysical jets coming from both directions. Now the vast majority of these types of black holes around the universe are very often in sort of this formation, or this orientation toward us, and normally they don't really show us much. We'll usually see quite a lot of emissions coming from the center. We'll also occasionally see the effects from the astrophysical jets, which very often also resemble these very beautiful radio jets visible from very far away, but other than that we don't really see much. Mostly we just see quite a lot of dust, and usually a lot of emissions that don't really show us any specific detail. Once in a while, in certain galaxies, the orientation can be sort of this way, and this creates a relatively bright object. Now here we can actually start seeing the astrophysical jets coming almost directly toward us. The vast majority of the objects we call quasars are basically that. Very distant, very powerful black holes that sort of point their jets almost directly at us and thus create very bright objects. In most cases though, we can still actually see the emissions and the effects from the accretion disk itself, because that's basically what produces all of this brightness. It's very rarely that the astrophysical jets are brighter than the accretion disk. But occasionally, in extremely rare cases, we sort of get the orientation that's kind of like this. Now that is an extremely bright object, and that's essentially a blazar. A blazar, in a nutshell, is a quasar with a perfect orientation toward us. And this creates a bit of a problem for astronomy. The problem being that, well, it's kind of hard to see anything in this galaxy and it's impossible to actually tell anything apart. This covers everything. It even covers the extremely bright accretion disk that's usually visible from far away. Here only the jet itself is visible because it's basically shining directly at us, and these ones are the most famous known to us. Now, because this particular jet is so ridiculously powerful and so ridiculously bright, very often it does create some of the brightest light in the entire night skies, at least in some frequencies. And even at a distance of 3.5 billion light years away from planet Earth, this supermassive black hole very often flashes with brightness of over trillions solar luminosities, much greater than the entire Milky Way. But more importantly, over the years the scientists realized that it seems to actually increase in brightness very periodically. Because there are observations of this from back in 1887, the scientists were able to plot an average magnitude for this object, discovering that every 11 to 12 years, it dramatically jumps in brightness. And because of this unusual increase in brightness and because of this periodicity, it implied possibly only one thing. Something seems to be orbiting around it every 12 years. But not just any something. Something really massive that is able to produce quite a lot of disturbances and very likely suddenly increase the emissions by basically dislodging the accretion disk. And so pretty quickly the scientists proposed one of the possible explanations. It was another massive black hole. A black hole that was very likely on a somewhat elliptical orbit that was also precessing, which meant that it wasn't always perfectly 12 years in length. But more intriguingly, the actual masses involved here were absolutely ridiculous. The initial proposition assumed that the central black hole was about 18.3 billion solar masses, making this one of the larger black holes out there. As you can see, it would be at least 9 times bigger than the orbit of Pluto, and even the smaller black hole orbiting around it being at least 150 million solar masses as well. That's about 30 times bigger than the one in the Milky Way. And that would create a very unusual system, an extreme system that nobody ever thought would be possible. On top of this, the extreme size of this black hole would be also difficult to explain, and it also possessed an extreme spin, possibly spinning almost at its limit. So none of this made a lot of sense. But it was still an exciting system because the scientists have always been trying to find these supermassive black hole binaries, or basically black hole systems where two black holes are very massive and are on a collision course. And one of the reasons the scientists want to actually find these black holes is because of what's known as parsec problem. There's another video on the channel somewhere in the description that explains it in detail, but in a nutshell, the scientists today, or modern simulations today, suggest that technically two massive black holes should not be able to collide with one another even after 1 trillion years, simply because the physical mechanism responsible for smaller black hole collision is actually absent in the larger black holes. And so the scientists have always been trying to find these binary systems that would help the scientists resolve this unusual paradox. So far it's still actually not resolved, but systems like this show us that black holes can definitely approach each other much closer and thus eventually collide. Although right now nobody knows how. But because of these earlier predictions and observations, and due to the assumed mass of 18.3 billion solar masses, the scientists were then able to work out the next possible emission that should occur around October of 2022 as the smaller black hole passes through the accretion disk. Well, at least that was the prediction. So far, nothing has been observed, and it's been a few months and the scientists have seen nothing. In other words, the prediction did not come true, and some of the scientists decided to figure out why not. They essentially decided to rework some of the initial assumptions and basically rework the model, in the process discovering that it's quite likely that previous emission that happened sometime in 2016 was probably the one that was supposed to happen in 2022. But more interestingly, because of these earlier predictions, this also involved one of the longest and one of the most complex observations of an astronomical object ever conducted, referred to as MOMO, Multi-Wavelength Observation and Modeling of OJ287, something that involved observations in 14 different frequencies, including X-rays, radio waves, UV light, gamma ray band, and microwave band. And so altogether, this allowed the scientists to see exactly what's happening around this object, but actually most importantly, it finally allowed the scientists to sort of see through the jet itself. This super complex observation allowed them to kind of remove the jet from the picture, at least for a little bit, uncovering the accretion disk and some of the other stuff in this galaxy that was previously invisible. And this was achieved simply because of the amount of observations and the amount of frequencies the scientists were using. At some point during their observations, the jet became dark enough, or basically faded just enough, for some of the other stuff to be visible as well, which in the process allowed them to directly calculate the overall mass and size of the accretion disk, and thus work out the mass of the black hole. And turns out the disk here is not very bright, approximately 10 times fainter than originally believed, which by the way is still ridiculously bright, about 5 trillion times the luminosity of the Sun. But this allowed the scientists to work out the mass of the black hole, which turned out to be much smaller, maybe about 100 million solar masses. And actually just for fun I decided to try to create a miniature version of the system right here using Universe Sandbox. So here we have the central black hole that's about 100 million solar masses, and we have the smaller black hole orbiting around it with a somewhat eccentric orbit of about 0.65, and this happens approximately every 12 years. And so that's kind of what the scientists now believe is happening here, with the smaller black hole possibly being about million solar masses or even smaller. And just to give you a visual comparison, the original assumption involved a black hole that was basically this big, so significantly bigger, way more massive, and potentially a lot more difficult to explain than what was discovered very recently. And so by using a smaller black hole that's a lot more acceptable, it now became possible to explain all of the observations, including the absence of the predicted emissions in 2022 and the appearance of emissions much earlier in 2016. And though it still involves a black hole binary with two black holes that might collide in about 10,000 years from now, it does not involve impossibly massive black holes, so nothing in billions of solar masses. And at the same time, these observations showed us that these unusual outbursts seem to be non-thermal in nature, or basically implying that it's not coming from the accretion disk, but it is coming from the super bright jet after all, which most likely has something to do with the generation of very powerful magnetic fields responsible for these jets, and a black hole passing through the accretion disk, disturbing the magnetic lines, increasing the power of the jet, is the most likely explanation here. And so definitely a pretty intriguing study and a pretty intriguing discovery, but also a very intriguing observation that lasted for several years and involved pretty much one of the most complex multi-frequency collaborations ever. In the end, producing observations in a lot of different frequencies and generating huge amounts of data. But at least for now, that's pretty much all we know about this unusual system. We know that it's still some kind of a binary black hole, just much smaller black holes, and we know that these black holes are going to be colliding in the next possibly 10,000 years or so. They're still relatively far away from one another, with the closest point between black holes being over 1,000 astronomical units, 50 times farther away than Pluto is from the Sun. But this is definitely not the last time we're going to be talking about OG-287, because by themselves, blazars are some of the most mysterious and most fascinating objects, and I'm sure we'll be discovering so much more about them in the next few years.
Hello wonderful person, this is Anton, and today we're going to be discussing one of the most fascinating black hole collisions ever discovered. The one we've talked about many times before, and the one that still is kind of mysterious even today. The collision between two relatively massive black holes of at least 85 and 66 solar masses that might have resulted in the creation of the first confirmed intermediate mass black hole, the black hole that was at least 140 times the mass of our Sun. And that of course created a bit of a mystery, because first of all, these two massive black holes were actually thought to not be even possible. Their masses are in what's known as the mass gap, the mass limit where certain stars, if they reach certain mass, instead of exploding in supernova creating black holes or neutron stars, explode leaving nothing behind. These are usually known as pair instability supernova, and most likely involve stars that are at least 130 to maybe 250 solar masses. Anything above that, and the star actually just collapses into a black hole directly, leaving behind a more massive black hole. Anything below that, and we get normal supernova resulting in typical stellar mass black holes. But for two black holes of 66 and 85 solar masses to exist in the same vicinity, and to then actually collide forming an even more massive black hole, that's way too many unlikely coincidences all at once. So statistically, this just made it kind of incredible, almost impossible. And so even today, this collision, that's known as GW190521, is still very difficult to explain. Even today, it raises way too many questions and doesn't provide enough answers. Or at least it didn't at first. But more and more studies came out in the last few years, slowly explaining things in the process. While at the same time, assuming all of these discoveries have been correct so far, potentially even allowing us to understand why exactly we've been seeing so many of these black hole collisions, and why so many involved relatively large black holes. Here is a rough map showing us some of these collisions in the last few years, with these blue circles representing various black holes, and you can kind of see that the majority of them were at least 20 to 50 solar masses, resulting in something even more massive in the process. Yet, a lot of the original predictions from approximately a decade ago have always predicted this to be much less, maybe 10 solar masses, maybe 15, not 50. So what exactly is happening here, and why are we seeing so many large black holes collide, and why have we actually been detecting so many in the process? But more importantly, how is this black hole collision even possible? Where exactly did these two black holes come from, and what did they produce at the end? Well, interestingly enough, the data here does suggest that they did produce an intermediate mass black hole with nearly 9 solar masses of energy that released as space-time distortions that basically resulted in these gravitational waves that traveled for approximately 17 billion light years to reach planet Earth. And that's how we were able to detect it. But something else was detected a few months afterwards by a completely different team using completely different telescopes. Scientists using Zwicky Transient Facility discovered a really bright flash of light coming from the same direction that happened around the same time, sort of resembling a typical supernova, except that the emissions were just a little bit different, and did not really last very long. Now, because of the distances involved, it was unclear if it came from exactly the same point, but because of the relative similarity of time and the location, the scientists then started to propose that these two events were probably related. But how can two black holes produce a flash of light bright enough to be visible from such a huge distance and essentially resembling a supernova? Well, eventually, after months and months of deliberation, the scientists realized that maybe this was actually a solution to their problem. They might have realized what exactly happened here. It's quite likely that these two black holes were in a very peculiar location. They were orbiting a much larger black hole, a supermassive black hole, with a very large accretion disk. And in this case, once they collided, the resulting black hole very likely flew directly through the disk, disturbing it in such a way that it basically resulted in an enormous explosion that from a distance would resemble almost a supernova-like explosion, but a very quick explosion that wouldn't last very long, with the resulting black hole of approximately 140 solar masses traveling through the disk at approximately 200 km per second. Although when I originally talked about this back in 2020, the scientists also suggested that we might be able to see this particular explosion once again, once the black hole comes back for a second passage through the accretion disk in approximately 1.6 years. And from what we know so far, it doesn't seem like it actually happened, so I don't know if maybe nobody was watching at this time because, well, I guess it was during the COVID peak, so maybe the actual data has not been processed just yet, or maybe the black hole did not pass through the accretion disk again, or potentially, it might have been a wrong explanation. Either way though, we'll discuss this once more data becomes available. What is important here though is that this explanation provided all of the answers for everything we've observed. And most importantly, it suddenly provided an explanation for why we are actually seeing these unusual black holes to begin with. These black holes that should not exist must have been created as a result of previous collisions of other smaller black holes. And the reason it was so frequent, and actually the reason we're even seeing so many black hole collisions, is really because most of them seem to occur around various supermassive black holes, which very likely have a lot of black holes orbiting around them. Or in other words, most of the black holes we've seen so far, if not all of them, at least when it comes to black hole collisions, were all around a typical supermassive black hole. And many of them became more massive from previous similar collisions. And that, of course, made a lot of sense to a lot of scientists and actually kind of met the expectations of other theories. And so all of these unique circumstances suddenly made sense. Nothing here was statistically impossible, all of this was just in a very specific environment. But this was a few years ago. Now we have even more analysis and even more data, providing another piece of evidence, making this either one of the most fantastic and most unlikely black hole collisions to ever occur, or definitively suggesting that it happened around a supermassive black hole. With this study right here that you can find in the description describing what they found. They've discovered something important about these black holes based on the observations of the actual shape of the waves created by these black holes as they reached planet Earth. In this case, determining that first of all these black holes were not spinning unlike other black holes, but on top of this were also approaching each other from what's known as a hyperbolic orbit. Or in other words, they weren't orbiting each other at all. They basically collided as they passed close to one another from different regions of space. And statistically, this can only happen in a region where there is a high concentration of black holes already. So maybe some kind of a cluster, or maybe around a supermassive black hole where we do believe a lot of black holes orbit already. And because it's extremely rare for objects to collide in the universe in such a way without orbiting around one another first, so far the best, most likely explanation for everything observed
is really this: a supermassive black hole with a really large accretion disk that already has a lot of stuff orbiting around it. But, assuming the study is correct, now we have a new mystery, and basically it's the old mystery we had from the beginning. If these were two non-spinning black holes of approximately 66 to 85 solar masses in mass, if these were basically individual solitary black holes, how exactly were they formed? In order for a more massive black hole to form, original explanation suggested that these were results of different collisions from smaller black holes, but these individual collisions would probably produce a spinning black hole. A non-spinning black hole produced by a collision of two smaller black holes is extremely unlikely, probably even impossible. And so in this case we're back to not really knowing exactly where these black holes came from. But the densely populated black hole cluster is still in this case the best explanation. There's actually one such cluster that was discovered not so long ago with a video in the description, where many different black holes have been found inside a globular cluster. But it can also obviously happen in a supermassive black hole region as well. And when it comes to explaining the origin of individual black holes in this case, only one other explanation comes to mind, the one involving something a little bit more exotic. The video in the description explains it a little bit better, but in a nutshell, in the same way that we have light redshifted over certain distances and it becomes more redshifted as you go farther and farther away, there has been an unusual proposition that suggested that masses of black holes can actually grow in size as a result as well. In other words, the mass itself of a typical black hole increases as you go farther and farther in terms of cosmological distances. It's a pretty intriguing explanation, and you can learn more about it in the description below, but naturally there is no direct proof of any of this just yet. Just the fact that this was a very distant black hole collision, with the black holes in this case being really massive as well. But that's not enough evidence to prove any of this.
Hello InfoPerson, this is Anton, and today we're going to be discussing a relatively new proposition and a relatively new study that finds unusual evidence that black holes may be directly connected to the idea of dark energy. And more specifically, they seem to actually maybe even produce it to some extent. Although in this case, it's also important to understand that all of the discoveries in this paper so far are really more or less correlational, not causational, indicating a direct relationship between dark energy and black holes, but not necessarily showing that one causes the other, although there have been theories proposing that as well. So let's discuss this in a little bit more detail, but because this is such a loaded topic, I do have to make a few clarifications about what exactly is going on here, and what exactly we currently believe about dark energy, dark matter, and so on. As you might have learned from some of the previous videos, some of which you can find in the description below, today the scientists believe that inside our universe, we don't just have visible matter, so things like atoms and things that we're made out of, but we also seem to have certain mysterious invisible things that we only are able to see because of their effects on matter around them. So for example, the invisible dark matter that's responsible for creating a lot of gravitational effects that would be almost impossible to explain otherwise. A good recent example here is from the James Webb Space Telescope that shows us this very famous galactic cluster where gravitational lensing effects from something invisible in the center allow the scientists in the process to discover a lot of really exciting things. Very distant galaxies, very distant stars, and a lot of unexplained phenomena in the process. You can obviously learn about this in some of the previous videos about James Webb Space Telescope. But these gravitational effects cannot be purely explained by actual visible matter such as gas and stars. Something else is going on here. And so today the scientists believe that approximately 27% of everything in the universe is this invisible dark matter. But in 1998, so basically over 2 decades ago, a lot of older images from the Hubble telescope revealed something else very unusual. They helped the scientists discover that distant supernovae were for some reason actually recessing away from us much faster than they should be. Or in other words, that the universe was expanding faster and faster as you move away in time. And this unusual discovery led to major propositions about the universe. It looks like the universe was not just expanding, it was also accelerating its expansion. This was the so-called dark energy, the mysterious something that's causing the universe to expand faster and faster and faster. And it seems that there's actually a lot of it. About 68 or maybe even 70% of everything in the visible universe. This proposition, by the way, resulted in a Nobel Prize a few years later. But the important part here is of course that, well, this was the original discovery of this unusual phenomenon that we actually still have no idea how to explain. Some scientists or some physicists suggest that this is basically a constant.
part of a formula where things just expand because it's, well, in a formula. The formula, originally proposed by Einstein, known as the Einstein field equation, with the cosmological constant presented as lambda, directly connected to other constants such as the Hubble constant. But this is exactly where the problem starts. After years and years of measuring and investigating things with several different telescopes, the scientists started to discover that, well, it doesn't actually seem to be that constant after all. It might have actually changed in time. Today this is known as the Hubble tension, and it's essentially a series of various observations that all seem to imply that there might be two different values of this unusual constant, depending on where exactly you look at. But that's just one of the problems. The other problem is that the actual formula does not provide the explanation for what exactly is creating these effects. If this is just a constant, just a number, it still has to have some kind of a physical explanation. And so this physical explanation currently is just known as the dark energy, sometimes explained with the unusual phenomenon known as the vacuum energy. The phenomenon that exists because of quantum physics, and a phenomenon that has been to some extent shown to exist from various other observations based on a lot of smaller experiments. It basically suggests that there is no such thing as vacuum. Empty space does not exist. Even inside empty space, you're always going to have these minute fluctuations of energy that are going to always end up creating various particles that appear and disappear because of quantum fluctuations. And since, according to Einstein, energy and mass are equivalent, and both also result in gravitational effects, we should observe some effects because of this vacuum energy observable throughout the entire universe. This is also sometimes referred to as the quantum vacuum state, and there have been quite a lot of different experiments directly showing us that the vacuum fluctuations definitely seem to be a real phenomenon that seem to exist. And the first such experiment was actually conducted back in 1948. This is the experiment of Casimir effect that we've discussed in one of the previous videos. Something that technically you can even perform yourself if you have a sensitive enough apparatus to measure pressure. In a nutshell, the experiment shows that empty space between relatively thin plates will actually start receiving a lot more pressure from the outside because the space on the inside is small enough that not enough quantum particles are going to be produced, which results in actual physical pressure, even though all of this is vacuum and there's really nothing on the inside. This experiment is pretty well known and a lot of scientists try to maybe explain it in other ways, but at the moment the quantum fluctuations is really the best explanation and provides direct evidence for this vacuum energy. But, like always, the original explanations were from someone else. Probably one of my most favorite people in physics, Georges Lemaitre. He explained all of this in 1934. He basically tried to interpret the cosmological constant by combining it with perfect fluid equations of state and by physically showing that it could be some kind of an energy or even some kind of a particle. And as you might have learned from one of the previous videos in the description, completely by accident, a Belgian TV station discovered an interview with this absolutely brilliant person who even today is still sort of underappreciated. I mean, we're talking about a person that was able to prove Einstein wrong, and that was also the first to propose a lot of these brilliant ideas. But that's beside the point. Check out the video in the description if you want to learn more about him. The main point here is that the more the scientists tried to understand dark energy, the more confusing it got. But it seemed to be an actual phenomenon, causing the universe to expand faster and faster. And more importantly, it seemed to be directly connected to the fabric of the universe itself, but its actual source was still not entirely understood. But a few years ago, we've discussed another intriguing study that actually discovered something unusual about supermassive black holes in very distant galaxies. They discovered that if you were to look farther and farther away into the universe itself, a lot of black holes, on average, seem to be a little bit more massive than they should be, as if there was some kind of a connection between black hole mass and the expansion of the universe itself. And though it was an intriguing proposition, not a lot was done with it back then, and not a lot was actually explained from this observation. Now, however, in a new study, the scientists found even more evidence that a lot of central black holes in very distant galaxies seem to be directly connected to dark energy, or even could be the source of dark energy. Or to be more exact, discovering first evidence, for what's known as cosmological coupling between dark energy and black holes across the universe. And this concept of cosmological coupling just simply relates to how the universe evolves over time, and how things like temperature, density, structure, and a lot of other parameters inside the universe change as the universe grows larger and larger. With one famous example being the cosmic web, the structure inside the universe that directly evolved over time as a result of the expansion of the universe and as a result of dark energy very likely pushing on the web itself and making it stretch over time. But in this case, the scientists have also discovered that this cosmological coupling applies to the masses of very massive black holes, but also in galaxies where the black holes should not be growing at all. And specifically, we're talking about galaxies like what you see right here, the elliptical galaxies. Galaxies that predominantly have a lot of really ancient stars, but practically no activity anywhere. No star formation, no galactic collision, with the black hole at the center maybe being a little bit active, but not absorbing a lot of mass and definitely not growing very fast either. And more specifically for their study, they focused on the very inactive elliptical galaxies from various regions in the universe, anywhere from being extremely close to us up to several billion light years away. Or in more cosmological terms, anywhere from the redshift of 0 to the redshift of 2.5, which in this case suggested that these black holes should not be accumulating matter and growing from normal processes understood by previous studies. If they were growing, it was for an entirely different reason. But when comparing the masses of these black holes inside these galaxies to the predicted value, they discovered that as the universe progressed in time, the black holes increased in mass as well, with the confidence value of approximately 99.98%. Still not perfect, but definitely something intriguing that needs to be investigated even more. And on top of this, by removing the mathematical concept of singularity and replacing it with vacuum energy, or essentially making these black holes as vacuum energy black holes, this allowed them to directly explain the expansion of the universe as observed by various telescopes. First of all, suggesting that black holes are definitely not just empty points with an infinite point on the inside, the concept referred to as singularity. Instead, they seem to be much more complex, potentially even being the source of huge amounts of vacuum energy, most likely through some kind of a quantum interaction that we still don't understand. Or essentially, they don't just produce extremely powerful gravitational effects, but on top of this, they seem to produce huge amounts of vacuum energy, which potentially causes the universe to expand even more. Which once again means that we just don't really understand black holes very well yet, and there's still a lot to explore. But naturally, because this is such a huge proposition, it will probably take months, if not years, to confirm or disprove all of this, and a lot more observations and a lot more analysis are required as well. More importantly, because they've only used less than 10 galaxies to measure this would first have to be confirmed by looking at hundreds, if not thousands, of different galaxies to see if the same effects apply there as well. Nevertheless, if the discovery that black holes are somehow cosmologically coupled to the rest of the universe and to the expansion of the universe, this would be a huge discovery. It would essentially show that black holes play a much bigger role in the structure of the universe than anyone thought was possible. And because this is a second such discovery in the last few years, it's definitely something the scientists will be investigating for many years to come. Although obviously there are some other potential explanations to all of this as well. For example, maybe these black holes that they investigated in those 6 or 7 galaxies actually managed to find a way to grow differently from your typical black hole, which is why they appeared much bigger than they should be. Or more importantly, maybe we really have no idea how various supermassive black holes grow over time. Nevertheless, super exciting discovery, and one day might serve as a potential explanation for what exactly dark energy is, and for why exactly the universe is accelerating its expansion over time. But there are other explanations as well. A few years back, someone during one of the streams asked a very interesting question. A question that sort of has been bugging me for a pretty long time. When it comes to gravitational waves produced by, for example, black hole collisions, can you physically surf them? In other words, can you actually do something like this, although I guess using spacecraft or some other unusual tool, in order to surf the gravitational waves produced by black holes or really pretty much anything massive enough to produce these effects? And back then, it took me a few weeks to figure out exactly what the answer would be. But the thing is, I sort of forgot to answer it. Or I guess to some extent, I forgot to make the video about it. And so now, a few years later, I'm finally ready to give you that answer. The answer is sort of no. But there is a small caveat and a small explanation that's needed to actually explain what's going on here and why we don't believe you can surf these waves in any way similar to what you see right here. Although there was actually another intriguing question asked about black holes back then, and I'm going to be answering that in a separate video coming out really soon, so make sure to subscribe. Anyway, so why not? Why can't you surf these waves? Well, there's no one answer, but there are several mini answers,
that all imply that all of this would be impossible. First, the location. Here on Earth, you can really only surf waves when the wave itself forms what we refer to as the tube. And in order for these tubes to form, they have to be in a location where two different substances or two different media start to interact. In this case, water that produces waves interacts with the ground itself, causing certain types of shallow water waves to appear, with the height of the wave increasing as the depth of the water decreases, and eventually producing these tubes. So you do have to have two different substances or two different media in order to produce these effects. But when it comes to understanding the gravitational waves, from what we know so far, there is no such possible location. The waves themselves pretty much go through everything in the universe, and there's no possible location for these gravitational waves to crash against the shore. And so there's really no equivalent for the shore in the entire universe, at least according to modern theories. And so instead, everything in the universe sort of acts like a typical buoy in the middle of the ocean. Things just move around as different waves pass through them, and it's pretty much impossible for any buoy or for anything in the middle of the ocean to surf these waves. And then there's also the question of the shape of the wave itself. In this case, this is pretty much possible because the water waves do something like this. In this case, water molecules describe a kind of a circle, and so a buoy on the surface of this water is just going to move up and down, left and right, but overall have no net motion. But a typical gravitational wave would instead stretch objects toward and away from the direction of the wave itself. It's literally the space itself stretching and compressing. And in this case, as the wave approaches toward us, you kind of slowly move toward it, move away from it, and then return back to the original position, with the gravitational waves themselves passing through the entire object without any interaction with anything else. And so in the end, these gravitational waves do not produce any displacement from the center of mass. Moreover, there's also the problem of speed. When it comes to surfing the waves, water waves slow down as they approach the shore, but gravitational waves move at the speed of light, and no physical object is able to move at that speed, no matter how big or small. And so here the speed of light itself provides a very important limitation to all of this, with the other limitation coming from the idea of surfing itself, or the physics behind surfing. In order for a surfer to stay on top of the wave, and in order to even move along the wave, the gravity from planet Earth has to pull down on the surfer as the buoyancy pushes them up. And on top of this, there's also an electromagnetic interaction or electromagnetic repulsion between the physical surfaces of the fluid, in this case water, and the surfing board that moves along the water. And when it comes to gravitational waves, nothing we can think of or nothing we know of has similar effects. And there is no external force equivalent to gravity that would push the surfboard down in order to make the riding possible. And the fact that these are plane waves and not sinusoidal waves, like what we see on water, makes this even more challenging. And the last intriguing component here is the strength of the force itself. When it comes to the electromagnetic force, or the force that provides the repulsion necessary for the surfing to even occur, the force between electrons inside atoms, it's something like 10 to the power of 36 times stronger than the force of gravity. Or to give you a better illustration here, let's take a look at what actually happens when these black holes collide. During the moment of collision, a typical merger will actually release approximately 3 solar masses of energy, converting the mass itself into gravitational energy propagating across the universe as gravitational waves. And so that's kind of like taking 3 suns, turning all of this into energy at the same time, and then releasing it into the rest of the universe. And if this event were to create electromagnetic energy, it would result in the most powerful supernova we've ever seen. It would be brighter than any galaxy in the universe. The amount of energy released here would be absolutely ridiculous. And even being 100 light years away from this event would be deadly to any life. Yet gravitational waves are so weak that they barely produce any effect. You can actually be relatively close to a typical black hole merger within approximately several astronomical units. You can even be on a planet orbiting these stars, and you are unlikely to feel almost anything. Okay, not entirely true. You would actually hear something, but I don't want to spoil this because this is going to be in a separate video coming out really soon. And so because the gravitational forces are so much weaker, they're just unable to produce the same effects. And because of the weakness of these forces, it once again means that surfing them would be almost impossible.
And so instead, a typical gravitational wave simply just makes things contract a little bit, stretch a little bit, by a tiny amount as the waves pass. Which is exactly why the scientists had to build a huge facility like LIGO with lasers that are several kilometers long in order to even see the effects. And so here they basically are able to detect tiny stretches even smaller than the atom itself. And then by figuring out the distance to the original event, we're able to work out what exactly collided with what. But even if the effects were much larger and stretched the objects by a much bigger amount, it would still be practically impossible to use this for surfing in any way. Except for maybe one way. So basically there's maybe one possible exception. If we could somehow find a way to transfer some of this impulse and some of this momentum from the waves into a physical object. In other words, if we found an appropriate type of a surfboard that can somehow use these types of waves to contract in just the right way to then apply momentum into one direction. So for example, if we have some kind of a surfboard with just the right shape and just the right material, that somehow starts to oscillate from these events in a way that generates momentum. Or maybe generate secondary gravitational waves which can then cause it to move in one way. And this is actually a somewhat interesting mathematical problem that currently has no solution, but is also not very practical either. Simply because you would have to be extremely close to a black hole collision for any of this to take effect and to even give you a little bit of propulsion. Because most objects would still basically just act like buoys, moving back and forth, and just oscillating without moving anywhere. But if this object starts to oscillate and create its own gravitational waves, which then create all sorts of interference, in theory it's possible to make it move just a little bit. It's unlikely to be practical or unlikely to lead to this, but would possibly provide just a little bit of propulsion away from the black hole collision. With I guess a more intriguing question being in regards to the wave interference in general. At least in theory, gravitational waves can also interfere with one another to produce much larger waves than usual. But the thing is, we still don't really know much about them, and we still are not able to measure larger waves in order to actually find answers to any of these questions. Although, since in 2023 a lot of observations are going to be resumed, including a new facility in Japan, there might be more answers coming in the next few years. But we'll talk more about these discoveries and some of the other discoveries in regards to gravitational waves in some of the future videos. For now, well, hopefully this answers your question. Surfing gravitational waves, for many different reasons, should be pretty much impossible. But it might be possible to get a little bit of a boost and a little bit of a momentum using specific materials and using specific shapes. In modern cosmology and in modern astronomy, black holes have become a kind of a hypothetical answer to a lot of different mysteries in the universe. And by trying to understand how a lot of matter and energy interacts here, and by trying to understand what happens at the edge of the black hole, but also what happens around the black hole or even inside the black hole, one day the scientists are hoping to find answers to many different questions. But at the moment it's still kind of difficult. First of all, because we obviously cannot see that far, and a lot of black holes are relatively small in terms of the size of their event horizon, and second of all, because there are still so many different mysteries, and we actually don't even have the correct physics to try to describe what happens inside the black holes. Generally speaking, the modern physics ends somewhere right here, right at the edge, and what happens past the event horizon is kind of unknown. And so because of this, for many decades now, the scientists, I guess to some extent, were more or less stuck, with ideas like quantum gravity possibly in the future explaining what happens past the event horizon. But at the moment this is still in its infancy, and everything right here is basically unknown. Or is it? Is there actually a way for us to try to assess what happens inside the black hole by possibly seeing something on the outside? And so today we're actually going to be talking about one potential proposition, a very important one, about a feature of a typical black hole that not a lot of studies usually explore, but that the scientists now think is actually exceptionally important. A feature that sometimes is referred to as the photon ring. Something that ever since the original picture of the M87 black hole has become more and more prominent in various studies. Hello wonderful person, this is Anton, and so today we're going to talk about some of the recent discoveries and recent studies on the idea of the photon ring, what it means for our understanding of the universe, but more importantly, what the scientists currently know or don't know about it. But to start, so what exactly is it? So normally in most of the modern media, and I guess in most movies today, the black holes are presented in this way. We have the beautiful accretion disk that creates the beautiful orange shape around the black hole. We have the invisible dark part in the middle, with a lot of media and movies often portraying the event horizon as one of the most important regions around the black hole. The region past which we cannot really see. No light can escape, everything just falls into the black hole after this, and it's impossible to escape even if you were to move at the maximum velocity. With a lot of modern explanations suggesting that at some point, everything just kind of falls into singularity. Although it's important to understand that the idea of singularity, or this infinite something, is just our limitation of physics. Today we actually have no idea what happens past the event horizon. With two other features that often appear in media being the accretion disk and the relativistic jet. But not so long ago, we also discussed this much better interpretation by some of the NASA scientists that actually help us understand some other really important features that are often ignored in media, while also explaining why we actually see these unusual shapes, such as the underside of the black hole, which actually represents the opposite side that's just folded and bent by the black hole itself. So in this image, first of all, you'll notice that there's also one edge that's slightly brighter. This is referred to as the Doppler beaming. Because the light on this side is coming toward us, and is actually moving away on the other side, it creates a kind of a Doppler effect, making one side appear brighter and the other side darker. We also have what's known as the black hole shadow, which is actually that black part that we usually see, which is normally about twice the size of the event horizon itself. In other words, this right here is not really the event horizon yet. This is the shadow, the event horizon is much deeper inside. The shadow is the area where a lot of light is trapped and can generally not escape the black hole, but in some situations it's still possible to maybe extract some of the information from here. But then you'll notice something else here, and this is the region we're talking about. The photon ring. It's extremely difficult to see it, it's actually very thin, and it's also practically invisible here as well. But interestingly enough, when the Event Horizon Telescope team were trying to produce some of the earlier images, it would often appear in a lot of original data. And more recently, the scientists started to realize that this region is exceptionally important if we want to understand what happens inside the black hole. But how exactly is it formed and why is it so important? So first of all, it's not really a ring. It's technically a sphere, mostly because it surrounds the entire black hole. And it's formed by a lot of different energy, a lot of light, approaching the black hole. Some of this light will end up passing the black hole and escaping, changing just a little bit because of the interactions with the black hole, while some other light will be stuck inside and very likely falling into it. However, certain particles might end up circling the black hole just once, or maybe even multiple times, and will actually start creating a kind of a ring that becomes easier visible as more and more light gets trapped around the black hole. In other words, it represents this unusual region where the light doesn't fall into the black hole, but interacts with it in just the right way to be trapped around it for just a little bit and to then escape, reflecting the rest of the universe. It's actually been previously even referred to as the kind of a cosmic movie camera, or infinite light trap. Because in this case, in theory, it could trap a photon indefinitely until it eventually escapes because of something else. And so here at this region, the light itself starts to orbit around a black hole, although not really in the circular manner like we would expect around a star. It's going to have its own unusual orbit. But because we're talking about all of the photons coming toward the black hole from basically the entire universe, at some point they're going to reflect everything in the universe as this ring that you see. And so at least in theory, if you were to take this ring or the sphere itself and to somehow reconstruct it, you would kind of have the entire universe reflected in a kind of a frame-by-frame manner, almost like a movie. And some of these objects reflected here, you'll actually see several times. So it becomes possible to learn a lot about the universe itself by observing this particular region. However, unlike the event horizon or unlike the regions inside the black hole, this region we can see and we can study. And more importantly, now the scientists believe that this region doesn't just reflect the rest of the universe, it also kind of reflects what happens inside the black hole, as in its properties or its measurements can help us understand what goes on inside the black hole as well. And so a lot of the modern quantum gravity theorists realize that by using the photon sphere or photon ring, they might actually get a little bit further in developing their ideas and in potentially creating just the right physics to explain the black holes entirely. With at least one recent study that you can find in the description below, focusing on the idea of symmetry that seems to occur around various spinning black holes. And this symmetry suggests that the ring itself will encode some of the quantum information from inside the black hole, making it appear on the ring as a result. Or essentially they believe that the quantum nature of the black hole then encodes some of the information on the ring, which means that by studying these rings, we can finally figure out what happens inside. With their paper even proposing that the photon ring in some sense can actually be seen as a kind of a holographic mirror of the internal structure of the black hole. Or I guess in other words, whatever happens inside the black hole plus the reflection of the entire universe should be visible and should be discernible on various photon spheres. And since the initial observations from M87 galaxy and all of the initial calculations and studies seem to have always produced an unusual ring around the M87 black hole, something that's sort of visible in these early simulations, it suggests that this could exist around all sorts of black holes out there. But I guess more importantly, presents an opportunity for us to actually see black holes. Or I guess in some sense, breaking their definition. Black holes are no longer invisible. You can actually see what happens inside the black holes by potentially observing this photon ring, which might also help the scientists solve a lot of other mysteries, including the so-called information paradox we discussed in one of the previous videos, should be somewhere in the description, and eventually lead to a completely new physics model that might help us explain a lot of other things as well. Or to rephrase this, these explorations could maybe lead to the final bridge between the quantum physics and the general relativity, something that the scientists have been trying to do for the past few decades. And the theory here also suggests that various patterns observed around black holes seem to be generally governed by the photon ring. And as you move through various layers of the photon ring, you can also start looking at different layers of the black hole itself. With the study also suggesting that, in this case, the event horizon kind of becomes pointless. There's really nothing we can do with it, and there's nothing we can study to help us understand the black holes better. But the photon ring is an excellent candidate to study everything about black holes, with one of the potential explanations for the information paradox being that the information is stuck in the photon ring and eventually just dissipates as the black hole grows smaller in size. Or at least that's one of the potential explanations. The scientists in this case still have no idea how any of this works, or specifically how the information would be stored in the photon ring, but it's definitely a potential solution. And more intriguingly, one of the most recent studies on this topic might have been able to recreate the actual photon ring from the iconic M87. In this case, the scientists from that study remastered some of the original images from M87 galaxy, and by removing certain elements, were able to recreate the environment around the black hole, detecting a potential ring as you see right here. In this case, it was actually several layers of rings produced over a period of several days, once again implying that this is a kind of a frame-by-frame movie, and naturally produced in a way that you see right here. As the photons get deflected by the black hole, or as they orbit around it a few times, they'll start producing more and more observations, and they'll start producing different thickness of layers, with some of the thinnest layers being the one that stayed around the black hole the longest, forming this right here as a result. Although this is still a very preliminary study, and some of the scientists are not entirely certain if this recreation is actually going to be accurate. As a matter of fact, some of the scientists already suggested that the current observations are just not sharp enough to resolve a very accurate ring, which means that it might not be super helpful to have this particular image. But the reality is that once the Event Horizon Telescope acquires new members and becomes even bigger, and once it's able to produce even more accurate images, at some point a much more accurate image of M87 black hole, including of course the photon ring, can definitely become a reality, and then allow the scientists to finally start studying this using actual data, which in theory might happen within the next few years. But until these future upgrades, the scientists are probably not going to be able to see these photon rings and can only rely on various simulations and mathematical calculations. It's also unlikely that we're going to learn much about them from various black hole collisions, because those collisions, even though they do produce certain reverberations and certain vibrations, generally lose the information about the photon rings themselves. But it's possible that someone might figure out how to do this using black hole collisions as well. Nevertheless, more and more scientists now think that the future studies really should be focusing on the photon sphere or photon ring, not so much on anything else. In other words, this is really where a lot of mysteries of the universe are probably hidden, and this is really the part of the black hole we should be studying in order to try to understand what's going on everywhere else. 2015 was a super exciting year for a lot of scientists studying black holes. This was the first year we finally confirmed that black holes do collide. With all of this confirmed when the scientists detected gravitational waves that could only have been created by two massive objects, very likely colliding millions of years ago, millions of light years away from us. With this particular detection being known as GW150914. And since then, the scientists have detected quite a lot of these gravitational waves, with the majority being caused by various types of black holes that we usually refer to as stellar mass black holes, simply because they are very likely formed from various stars exploding in the past, with some of the most massive ones visible in this image, with the vast majority being approximately 40 solar masses. But today we're going to be talking about something a little bit more mysterious, something that the scientists originally discovered early in the January of 2022, with the most recent paper from just a few weeks ago confirming that something exciting is indeed happening in this particular galaxy. And here we're talking about a type of a collision we've never seen before, and the one that the scientists have been hoping to see for a very long time. A collision between two supermassive black holes. Black holes we usually find in the centers of various galaxies. And specifically, two really massive black holes, millions of solar masses, which will very likely produce ridiculously powerful gravitational waves. But something that unfortunately right now we're unable to detect with instruments such as LIGO that detects smaller black holes. And that's of course because of their design. By design, LIGO that you see right here is only able to detect certain frequencies. Frequencies produced by smaller collisions, smaller black holes, or objects like neutron stars, not supermassive black holes, which will usually produce much longer wavelengths. So, hello wonderful person, this is Anton, and today we're going to be talking a little bit more about this particular detection, or what exactly the science discovered in this case, but more excitingly, about the fact that there's a very high chance we might be able to see this within the next 3 years. So not in some distant future, but this is literally something that's about to occur. And all of this starts with a paper that you see right here, with a very intriguing title, Tick-Tock, the imminent merger of supermassive black hole binary. And in this study, the scientists were investigating the galaxy that you see right here. It's known as J1430 plus 2303, and it's what's known as a Cipher-1 galaxy. A type of a galaxy such as M77 right here that generally has extremely active core on the inside and very likely has an active galactic nucleus. And specifically, Cipher-1 galaxies are also extremely bright in the ultraviolet and X-rays, as well as producing a lot of optical light. In other words, they're usually defined by extremely bright and active centers, with very massive black holes in the center producing pretty much all of this. But this particular galaxy has never really been studied much before, mostly because, well, first of all, it's kind of far away. This is nearly 1.1 billion light years away from us, with the redshift of 0.08, and second of all because there are a lot of other exciting galaxies out there. However, when studying this elliptical galaxy, the scientists discovered an unusual pattern. The X-ray and UV light, along with the optical light, was shifting in magnitude with a very specific amplitude, with the period in this case not actually being constant, but instead reducing in time, with some of their earlier assumptions sort of looking like this. This implied that something was orbiting around the center of this galaxy, and this also implied that whatever was orbiting here was actually decreasing in period, potentially resulting in a collision eventually. And in this case, in this first paper, their initial calculations suggested that it might actually happen before the end of 2022, this year, when I'm making this video. And so this was actually the first detection of rapid decaying periods ever seen in any galaxy with potentially supermassive black holes in the middle. And in this case, the periods decayed from approximately 1 year to 1 month in just 3-year time. And if these were black holes, they were now orbiting around one another, only taking about 1 month to complete a single orbit. Now, as I mentioned before, unfortunately LIGO is unable to verify this because in this case, the wavelength is 1 month long. And on top of this, these observations could have been created by something else. Maybe it was some kind of an oscillation within the accretion disk, or something else causing some kind of a wobble that seems to occur every month. And so to try to confirm this, another team of scientists wanted to analyze this more using some other data. With this new study right here, using a lot of other X-ray observatories and other observations from this region, with the focus being identifying high-energy signatures that should only be visible if these were two supermassive black holes on a collision course. And the discoveries from this recent paper are super exciting, because they did see the variations in the X-ray light that were expected from binary black holes. But on top of this, they also saw the emissions that can only be associated with iron falling into the black hole itself, suggesting that something is definitely approaching the black hole and falling into it, and suggesting that something is indeed orbiting the black hole, but once again it's not 100% certain yet if this is two black holes, or possibly something happening around a massive black hole and causing these particular observations. And I guess more importantly, a slightly different paper that used radio observations from this region was unfortunately unable to discover any radio bursts that would be expected from two infalling black holes. Or in other words, there's still a chance that something entirely different is happening around this black hole that we just don't understand. The scientists are definitely certain though that something unusual and never before seen is happening in this particular galaxy and around this particular black hole. A black hole that's believed to be at least 10 times more massive than the one in the middle of our own galaxy. However, if this is two black holes, their total mass could be 200 million solar masses, or about 50 times as much as Sagittarius A star, the one from our own galaxy. And so at the moment it's kind of unclear what this strange behavior is, but I guess what is clear and what's super exciting is whatever is happening there is going to be resolved within the next 3 years. This is actually the conclusion from this recent paper. In this case, the X-ray observations revealed that the signal should disappear completely within the next 3 years. And the main conclusion from a lot of these papers is really simple. If this is indeed the first ever supermassive black hole collision we've ever seen, we should probably get ready for it. Ready as in telescope ready. We should try to organize a multi-wavelength observation of this region in order to make sure that whatever happens here is not missed and is detected by everything we currently have. Because if there is some kind of an outburst here, it's going to teach us so much about the universe, including how supermassive black holes grow, what happens when they merge, and how this affects their parent galaxies as well, making this a once-in-a-lifetime opportunity to detect one of these events. And there's at least one technique that we can maybe use to confirm this afterwards as well. It's known as the pulsar timing array, and it works by looking at various minute deviations in the pulsations of pulsars in the Milky Way galaxy. We've actually discussed some of the potential discoveries from this technique in one of the videos you can find right there or in the description. And so by using this in a few years' time, the scientists might be able to confirm exactly what happened in this galaxy. Mostly because the waves produced by this collision are going to be detectable by this technique. It's also quite possible that various neutrino detectors on the planet would be able to detect a lot of the emissions of very powerful neutrinos coming from the region as these two black holes collide, once again confirming that this is exactly what happened in this case. With a lot of other emissions, such as some kind of a large explosion similar to supernova, very likely confirming the collision between black holes. In this case, these powerful emissions are mostly going to be produced by the interaction and the final collision between the accretion disks as well. The black holes themselves are not going to be producing the explosion, but the accretion disks might. And one of the observations here is actually really interesting. It suggests that the velocity of the object orbiting here changed from about 20% of speed of light to about 2%. With all of this happening within just 20 days. To change the velocity by so much, you would require some ridiculously massive objects. Something that we kind of expect if there are two supermassive black holes orbiting in just the right way. However, the scientists also think that some kind of a very specific black hole wind could potentially explain this as well. So whatever is happening here, we'll learn in a few years' time, although possibly even this year. So this is definitely one of the most exciting discoveries of 2022. But until we know for a fact what's happening here, we're going to leave it at that. It's still a bit of a mystery. A mystery from a galaxy nobody looked at until relatively recently. Hello wonderful person, this is Anton, and well, let's talk about that picture of Sagittarius A star, the black hole in the middle of our own galaxy. The picture that was actually only revealed yesterday from when I'm making this video. And so in this video, I guess first of many videos that we'll be making about the discovery, I really wanted to talk about some of the details that were revealed during the presentation if you haven't watched it, and also talk a little bit more about some of the more common questions with potential answers about what we've just observed. Essentially trying to figure out exactly what we're looking at right here, this is the image, and exactly what some of these features are, including the unusual dots, the 3 bright dots you see on the picture. And so let's discuss the black hole itself and of course the image of the black hole, but think of this as part 1 of our investigation because there are so many things to discover
which I guess is a good way for me to remind you to subscribe if you still haven't. Let's begin. So first of all of the info, all of the studies and everything, as always, is in the description below, so if you'd like to check this out by yourself, you can find everything there. But what I wanted to start this is with the name itself, because during my stream yesterday, one of the more common questions was, why is it called Sagittarius A star? Well, first of all, what you're looking at right here is known as Sagittarius A. It's a very unusual active radio source region in the center of our own galaxy that, as you can see from this radio image, has a lot of activity pretty much everywhere. If you look closer, there are some regions called Sagittarius C, there are certain regions called Sagittarius B, and that's because everything here is in constellation of Sagittarius, the constellation you see right there in the video from the ESO. But if you were to look around the radio region of Sagittarius A, you would actually discover an extremely bright point. A point that seems to represent a gravitational center of this particular region. This point is known as Sagittarius A asterisk or Sagittarius A star, with the star itself just being the way that we pronounce that asterisk. Although in this region you can also find some other activity in, for example, a very ancient supernova remnant in Sagittarius A east, and a very unusual spiral structure in Sagittarius A west. But it's of course that unusual, bright and variable spot in the middle, Sagittarius A star, that's always been of the most interest. And over several decades of observation in different frequencies, including the X-rays, the scientists were able to determine that this is most likely where our central black hole is located. With this iconic animation produced by the scientists from ESO, definitively illustrating that a lot of stars in the region definitely seem to orbit something unusual in the middle, something that possesses a mass of over 4 million masses of the Sun. With further evidence coming from many different so-called S stars, for example the most famous one being S2, we've discussed this one somewhere on the channel, should be in the description below, whose orbits even indicated that there are a lot of Einsteinian effects, including Doppler effects, happening when they approach this unusual center that seems to be some kind of a massive, supermassive object. And although there have been suggestions that maybe it's some kind of unusual dark matter chunk, maybe some sort of a exotic matter that we've never seen before, possibly even exotic matter that was predicted by various ideas and theories, some of the recent papers definitively established that whatever it is, it seems to be in an extremely small region of space, and so by definition this could only be a black hole, because nothing else can be so dense. And one with a mass of approximately 4.2 to maybe 4.3 million masses of the Sun. All of this was established by observing those S stars and a lot of other objects orbiting in this region for many years, actually over 2 decades now. But then a decade ago, back in 2009, several scientists kind of decided to create something unusual. They proposed an Earth-sized telescope in order to possibly observe some of these black holes, or maybe even create an image of one. The idea sounds a little bit preposterous at first, but as more and more radio telescopes became operational around the planet, it actually sort of became a reality. This idea became known as the Event Horizon Telescope because their main purpose became taking a picture of a black hole. And so since roughly around 2017, by using 8 different observatories on the planet, they started to essentially collect a lot of radio data from several regions in the universe, specifically focusing on 2 black holes, M87 and Sagittarius A star. Here's, by the way, what the size of the aperture of this telescope in theory looks like. So it's an Earth-sized telescope. But there's a small side note I'd like to make that I also mentioned on the stream. Since there were only 8 observatories involved here, it's as if you had only 8 pixels in your camera. So imagine having a smartphone camera where only 8 of your pixels work. Now in order to take a picture with that camera, you're going to have to take a look at something for an extremely long time and very likely come up with some kind of an algorithm in order to work out what each of those pixels saw and how all of this connects into a bigger picture. That's literally what they had to do for many years. Since 2017, all these observations then had to be combined using very complex algorithm and also using thousands of terabytes of data collected from several observatories on the planet, with the most difficult location to reach and also get data from being the one in Antarctica. You're about to see the observatory right there. And so creating this image literally involved a bunch of different points from different telescopes trying to sort of create a full picture at the end. And in this case, the picture would actually look entirely different if certain telescopes were absent. So the more telescopes, the higher resolution we get. And also, in order to create an algorithm that would work with all of these observations, the scientists had to run computer simulations using supercomputers in order to determine what they're most likely to see in this region. So essentially, this was a combination of computer simulations with physical observations from these 8 radio telescopes. And there's obviously a reason why they chose these 2 black holes and nothing else, not Andromeda Galaxy, for example, which has been mentioned on my stream. Both of these black holes, if you were to look at them in the night skies, would represent the largest possible objects. Although largest here is a bit of a misnomer. Here they actually compared the size of this to essentially seeing a donut on the surface of the moon. That's how tiny these black holes are in our night skies. But still, these are the largest black holes we see in the night skies, so these would be the easiest to potentially image. At the moment, we don't actually have technology for anything else. And here's the donut. But there's a reason why Sagittarius A star was not shown to us back in 2019, but instead they chose to present us with M87. Even though M87 looks slightly smaller in the night skies, as you're about to see here, it's actually significantly bigger. If you were to basically place it much closer to us, it would be a gigantic object. Here's what it's going to look like, very close to Sagittarius A star. So here's another way of visualizing this. If you were to look at the M87 picture, you'd notice that you can fit the orbit of Pluto into the black hole's shadow, with the Voyager 1 probe being at the edge of the shadow. But inside of this, a tiny pixel would literally represent the size of our black hole and even the size of its accretion disk, with Mercury's orbit representing the approximate size of the entire image we saw. And so the difference here is actually quite dramatic. The black hole inside M87 is approximately 1500 times more massive than the one in the Milky Way, but it also happens to be approximately 2000 times as far away from us. So because of this, their size in the night skies is relatively similar. But the advantage of taking a picture of M87 is really in regards to how fast things move here if you were to look at them from a distance. So first of all, M87's black hole, or M87 star, or Poway as it's also known, happens to be an active black hole. So there's a lot of activity here, there's also a lot of sort of churning and turning, but the material here, because of the size of the accretion disk, moves much slower. As a matter of fact, you can actually look at the same spot for a pretty long time and collect a lot of data from that spot. Specifically, gas can actually take anywhere from days to even weeks to orbit around this black hole. But around our own black hole, because Sagittarius A star is not an active black hole, and also because the accretion disk here is much smaller, things here move very fast. It could actually take anywhere from a few minutes to possibly a few hours for some of the particles to move around. And that means that collecting data here is way more challenging. You basically are looking at something that's moving so fast that any kind of an exposure photography is going to be practically impossible. One of the best images I found recently to illustrate this is actually this. If you haven't seen this before, take a guess at what you're actually looking at. Well, you might be able to guess simply based on the observations of the environment near these unusual lights. This is a train. It's a fast-moving train, the picture of which was taken during nighttime using long exposure. And in essence, this is kind of similar to what you're seeing here, except that these images were produced slightly differently. In this case, the pictures of these 2 black holes were produced using 2 techniques, clustering and averaging. This video right here kind of explains how this works. So first of all, you take a bunch of creations and you try to cluster them into different most common images. Cluster 1, cluster 2, 3, 4, 5, and so on. Then, by taking each individual most common cluster, you try to average everything out, creating the most likely representation of what this black hole might look like. So in essence, this kind of explains some of the features we're seeing here. These 3 unusually bright dots, for example, were simply created because these were the most common elements appearing in most of the pictures. If you look closer here, you can actually see that, for example, in the first cluster, there were only 2 of these bright dots. In the second cluster, there was this very bright dot right here, which obviously appeared in at least a dozen of different images. And then we had these other spots in the other locations as well. And so by averaging all of these images, they've created this. European Southern Observatory also created a kind of a more easier to understand simulation to help us understand how this works. In this case, using this mountainous formation to show us how they did this. So here we're taking a bunch of images of the mountains, and we're taking them during different times of the day and during different types of weather. Then, by taking all of these images and clustering them together, we're going to find most common elements. Then, by averaging these clusters, we're going to be creating something that looks like this, like the image on the right. And so this image shows us what the average representation of this structure is, with the skies behind it sort of representing a blur of different weather effects, even though individual frames might actually look entirely different depending on the time of the day. And so we're not seeing the exact image of the black hole, but we are seeing a kind of a averaged out version of everything that happened here during the period of the observation, which lasted for a few months. And also, a super important addition here is that this is not an optical image. The orange and yellow here represents radio light. So in that sense, we're not actually seeing this. What we are seeing are various radio emissions coming from various parts of the accretion disk due to the interaction of matter, plasma, and most likely magnetic field that create this super hectic environment with a lot of radio waves coming our way. So in that sense, this is more of a scientific/symbolic representation of the black hole, as opposed to an actual image. In reality, if we were to potentially be there and look at this with our own eyes and possibly some other sensors using, for example, X-rays and gamma ray detectors, we would probably see an extremely powerful, fast-spinning torus of dust and a lot of material, where things move very fast, things flicker a lot, there are a lot of explosions, a lot of different emissions, or maybe even something resembling what you see in this video, with a large dark object in the middle producing certain dilation effects and also certain Doppler shifts and other effects predicted by Einstein. And since all of this stuff is essentially plasma, it would to some extent resemble our sun. And also, one of the more common questions during the stream was in regards to maybe using other telescopes like the iconic James Webb telescope to maybe take a better picture of this so we can actually see what it looks like in, for example, infrared and optical light. Well, once again, that would probably not be possible because this right here is already a much bigger telescope. The size of the mirror on James Webb is very tiny in comparison. But even if we were to capture an image from here, we would most likely see almost nothing, for one simple reason. The galactic center is very thick, and most of the dust here pretty much makes the observations in optical light, or even in infrared light, quite impossible. But even if we could see the black hole in optical or infrared light, because of the distances involved, nearly 26,000 light years away from us, we would still not really be seeing much. And here we would still be dealing with the same problem of things moving way too fast around the black hole, because of the dramatic changes in brightness and a lot of other changes, including the changes in the shape of the accretion disk. Even without dust covering everything, James Webb would still not be able to produce a very good picture. As a matter of fact, the only way for us to take a better picture of all of this, specifically using radio light, is to add more observatories around the planet, or potentially launch observatories into space, which can create an even bigger aperture for this particular telescope. And this is something that has been planned by the AHT team, but at the moment there's no future plans for any of this. And also, generally this would be pretty expensive. Any kind of a space telescope usually requires huge amounts of funds. And so that averaging and clustering technique is really, at the moment, the only way to make these images and to make any observations possible. But this is just obviously the first such step. As a matter of fact, now that we know that the region around our own black hole doesn't seem to be as active as some of the other black holes, it might actually be possible to take even better images in the future, or even help the scientists see the event horizon and the shadow of the black hole, studying it in a lot more detail. And one of the more surprising discoveries coming out of this image is really in regards to how all of this seems to fit well with Einstein's theory of general relativity. Specifically, the size of the ring, and even the size of the shadow, fits almost perfectly into every prediction scientists have been making for many years. And this applies to both M87 and Sagittarius A star, which of course confirms that many theories in regards to black holes for the most part seem to be correct, which also means we can start making other predictions. But just the fact that despite size differences, these two black holes seem to appear quite similar to one another already means that by observing one black hole, we can start making a lot of assumptions and inferences about other black holes as well, including some that are really small. And so even though these two black holes are located in two completely different galaxies and seem to be generally quite different from one another, they seem to be still very similar, especially at their edge, with most likely any differences that we see just being because of certain types of material that's present on the outskirts. For example, maybe more dust,
more different types of stars, or some kind of a supernova remnant, which could have added material that would not be there otherwise. But these differences can actually help us figure out how these black holes interact or even shape the environment around themselves. In other words, by looking at these minute differences between different black holes, we might be able to finally start figuring out how a typical black hole might actually affect the rest of the galaxy. Although for our own black hole, Sagittarius A star, it's still a bit of a challenge to see things and to actually analyze things. Mostly because the orbital period extremely close to the black hole is only approximately half an hour. But to get really accurate data from planet Earth, we want to observe something for at least 12 hours. So unfortunately, there's just no way to try to resolve this just yet. With a lot of this very turbulent and extremely powerful plasma basically blocking a lot of the other observations in other types of wavelengths. But despite all of these successes from the Event Horizon Telescope, and despite the fact that there are now 2 images of black holes, there are still so many unanswered questions. Even simple questions, such as, for example, how far away is this? Like, for example, during the stream, the distance was mentioned as 27,000 light years away from us. But the most accurate observations from Japan, from only a couple of years ago, suggested that the black hole is approximately 25,700 light years away from us. So even the distance to the black hole is still currently unknown. Then we have more questions in regards to astrophysical jets. How exactly are these formed? Today it's believed that a lot of magnetic interaction happens around the black hole that causes this to happen, but it's still a bit unclear. Also in this image, what exactly happened around the spot here? How is it that so many different images from the black hole seem to have a much brighter spot on the far side of the black hole? One explanation could be because of the flares in the far side of the accretion disk, which could then be seen because of the bending of light from the far side, but at the moment it's not really clear. But I guess the biggest question out of all of this is, what exactly is the orientation of the black hole toward us? During the ESO stream, some of the scientists suggested that it could be actually sort of almost facing us. As in, instead of being sideways with the accretion disk possibly showing us the edge, we could be looking at this from maybe this angle. Now that currently does not make sense, and as I mentioned in the stream, the reason it would make sense is because of the discoveries from just under a year ago, where the scientists identified actual remnants of ancient astrophysical jets that might have been created only a few thousand years ago, and they were pointed more or less perpendicularly from us. So something here doesn't add up, or maybe the black hole has some kind of a precession / some kind of a wobble where it does sort of move around this way. Now that's of course a huge assumption, and right now there's really no proof of any of this. But this is sort of where I reached the level of my ignorance in regards to this image right here, and I'm definitely going to have to follow up on this because I would love to find out what exactly the scientists discovered in regards to the orientation of the black hole. At the moment it's super unclear and seems to be the biggest mystery. So I think by now most of you have seen this image. The image of Sagittarius A star, the massive black hole located in the middle of our own galaxy. And you're probably familiar with this image as well. This is the image of M87 black hole that we discussed many different times on the channel, produced by the same team using the same technique. The team known as the Event Horizon Telescope. But the thing is, there is a video I should have made a long time ago, the video investigating the science of all of this. How do we know that this is exactly what all of this looks like? Has anyone else tried to reconstruct this using the data that was created by the team? Are we actually certain that this is accurate? Hello wonderful person, this is Anton, and so today we're actually going to be addressing this from the more scientific perspective. We're going to discuss these 2 recent papers that kind of question all of this, or at least to some extent, with one paper from Japan being exceptionally critical. And that paper even suggests that the image of M87 black hole produced 3 years ago might have been created this way because of a certain scientific bias. And the real image could be entirely different, with something else somewhat exciting discovered in the process. With one very important thing I have to mention before I start. Remember, this is science. Confirmation and reproducing the same result using the same data is really important. And so the fact that it took 3 years for the scientists to finally start questioning this is a little bit disappointing. But I'll talk a little bit more about this near the end of the video. So let's start with that paper from Japan, as always available in the description below. And the scientists here do make a pretty big statement and a pretty big claim. Now, I'm not saying they're right, and I'm not saying that the AHT team is wrong, but what they are saying is kind of important. All of this is encouraging a healthy scientific discourse.
So in essence, they tried to use the same data that the AHT team used, but then used a slightly different processing method. And specifically, they changed what we usually refer to as the FOV, or field of view. To be more specific, they increased the field of view by approximately 3 times. So I guess one way of imagining this is, instead of looking at it from this perspective, you're now seeing all of this from slightly farther away. And the most interesting part of their study is that they couldn't really detect any ring structures that would in essence create this donut. But they found emissions at approximately 230 GHz that could only be visible from this wider field of view. The emissions that could have been representing the jet region around the black hole. And so their reconstruction here makes this look like some kind of a knot structure with certain weak spot-like features along the jet, which resembles the jets detected by some of the previous studies as well. And so in essence, their image is pretty much entirely different. Although they do also mention that there is still a lot of uncertainty here because of the distances involved and because the actual procedure only involved those 8 different telescopes on the planet and did not produce enough data. Nevertheless, the results show 2 very bright peaks, one being at the core and one being inside the knot structure formed by the jet. And possibly even some kind of a third feature that they refer to as a W right here, that seems to be in a slightly different region as well, which according to the scientists behind this paper and their observations, supports the existence of what's known as the radiatively inefficient accretion flow. Basically this very active and very chaotic torus shape around the black hole itself that represents an extremely active and very powerful region right next to the disk itself. Here's what all of this would look like from a side view, although in this case you're looking at different stars. But as we know, stars and black holes do seem to have very similar effects around them. And the scientists behind this paper suggest that this is actually the most accurate measurements of this particular region ever conducted. In this case, not really representing the accretion disk, but this unusual feature that they refer to as a knot. Although in this case, they're still having trouble to explain what, for example, the W is, but they suggest that it could be a result of the gravitational lensing effect produced by the black hole itself. Or maybe some kind of an unstable structure that separated from the black hole and from the jet. But that's not really the most important point from the paper or the discovery that they made. The most important point is that they were unable to recreate this. They couldn't create the ring that we're observing in this image, and they think it's because of the so-called data sampling bias, with their explanation being really interesting. So before the scientists even looked at this particular black hole, they already knew the approximate mass of the M87 black hole in the middle. They estimated the mass to be about 6 billion masses of the Sun, a lot more massive, approximately 1500 times more massive than the black hole in our own galaxy. And because they knew its mass, they sort of knew what the approximate size of the event horizon and obviously the black hole itself is going to be as well, based on the calculations from the Einsteinian principles. Because of this, before they even started processing the data, they set the field of view setting in order to potentially create or recreate the black hole of this particular size. In other words, what the scientists are saying in this paper is that the image was created from this original bias of sort of knowing the potential size of the black hole, while also criticizing how the scientists behind the AHT calibrated their images afterwards as well. And so because the scientists expected the black hole to be of this size, they set the field of view to be of that size as well. And this represents a major bias in the analysis, at least according to the Japanese scientists. But once you change the field of view and, I guess, zoom out, and then reprocess all of the data collected over several days once again, everything changes dramatically. The ring disappears, and something else starts to appear instead. And on top of this, they are also disappointed that no jet was considered in this study either. They're saying that the jet should be visible in this picture as well. And they're also obviously saying that the ring that we're observing in the image of M87 is really some kind of an artifact that seems to be produced as a result of potential noise in the data. But once they change the field of view, all of this disappears and the jet appears instead. In general, researchers should have been conducting a more of a blind approach. They should not have taken a certain field of view with certain expectations. But I guess the question is, who's right? And that's of course science at work. We're not going to know for certain until further studies, which is why I'm basically making this video. I'm hoping more people will join in and will analyze this even further. Not that I have this kind of power, but you never know. But the main reason I'm even making this video is because this is a really important argument, and it should have been made a long time ago. It should have actually been made back in 2019. But there's also obviously the question of the Event Horizon Telescope team. They are extremely experienced, And so according to them, choosing a different field of view would create an image that would not really make much sense. As a matter of fact, by zooming out too much, the data that you start collecting can actually end up producing pretty much absolutely anything. It does become more noisy and a lot less meaningful. So in this case, this particular field of view was chosen because it made the most sense. So in this particular case, this is still an open question. But then we have this other second paper that came out not so long ago, which actually underlines a slightly different problem with the process that Event Horizon Telescope team took. In this particular case, the scientists did try to recreate the image following every single step that the AHT team took as well, using everything including the same data, the same principles, and of course the same processing pipelines, in order to basically see if they can get exactly the same results. And long story short, as you can see right here, they did reproduce pretty much exactly the same pictures. So in that sense, everything was correct. But this paper is also critical of the AHT team for a different reason. It took the scientists behind this paper a lot of extra skills in order to basically try to recreate this. So for example right here, notice how a lot of things were just unavailable. The raw data was not there, only the process data. Different scripts that were used by the AHT team were also unavailable. And although the code for the software was available, a lot of extra scripts and also the actual steps to how to use those scripts were also not publicly available either. In other words, it makes it almost impossible for an outside user, let's just say from a different university, or even from, let's just say, high school, where the students are trying to recreate this themselves, although I guess that's a pretty cool high school, to try to recreate this as you should be able to do in any scientific experiment. And in the end, the scientists behind this paper had to basically reconstruct everything and create their own scripts and some of their own software. But that's not really how things should be done. The main point of a scientific study is that it should be easily reproducible. This is definitely not it. Without some kind of an internal access or internal knowledge or knowing people on the AHT team, it becomes almost impossible to reproduce this. Now, given this is a really complex study with some ridiculously complex processing and a lot of different steps, but still, if you're making such a huge claim that this is a picture of a black hole, it should still be reproducible and the data and everything else should still be somehow available somewhere. Which actually reminds me of a personal experience with some of the previous papers that I really wanted to discuss on the channel, but unfortunately could not reproduce the results myself. It was actually in regards to that other theory known as MOND, or Modified Newtonian Dynamics, and the paper made some really incredible claims about some discoveries. This was like a couple years ago. Unfortunately, when I tried to do this myself and then when I tried to reach out to the professors behind the study, instead of getting a relatively easy answer with basic steps on how I can reproduce this, instead I got a lot of, yeah, we don't remember how we did this. Which is a pretty common problem with some of the more complex scientific studies. A lot of scientists often forget that science is about reproduction, and a lot of professors do become complacent over time and often forget that the methods is really the most important part of any study. Everyone should be able to repeat your experiment and confirm your results. If they can't, then you're not doing science. But I cannot be really too critical of the AHT team. Their actual experimental process is just way more complex than anything we've done before. This took a team of hundreds of scientists several years to produce. So in that sense, okay, yeah, maybe they didn't include all of the steps. And naturally, the team behind this paper was able to reproduce everything at the end. So the science here is still pretty good. But now we also have this new picture that used pretty much the same analysis and very likely very similar methods, so this too has to be confirmed now. And that also means that some other studies might be coming out in the future, possibly criticizing this as well. And that's the problem with having studies with incomplete design or incomplete description of certain steps or even missing datasets. And because several pieces of software were already missing from the description in the Event Horizon Team Telescope analysis, it means that even with this image, we have to take a very thorough approach in confirming the final results. And actually, thanks to the team behind this paper, which by the way mostly consisted of the undergraduate students that were just very interested in trying to recreate this, we now have a more thorough understanding of how this can be reproduced and how this image can be tested as well. And if you are a scientist, or I guess even AHT scientist watching this, and you're asking yourself, why even bother? Well, okay, ask yourself, who are you actually doing this for? The undergrad students behind this paper, the postdocs, various high school students, could actually benefit so much from being able to access all of this code and all of these methods in order to try to recreate this and possibly learn something in the process. With the ultimate goal of being one day becoming like you, becoming a researcher doing all of this for a living. And that's very common in science. Often we get so carried away by the activity itself
that we really forget the main purpose. And though obviously the level of complexity behind some of these studies is absolutely ridiculous, by itself, this right there could be a potential future profession for someone. Being able to connect the amount of data analysis required for some of these studies and explaining how all of this is done. Now, it's not really science communication. In this case, it's really communicating the process of scientific analysis. It is a very complex task, but it's super important, especially as all of these studies become more and more complex over time. And I'll be honest with you, if I were to try to recreate some of this myself, and then try to explain how to do all of this, it would probably take me at least a year, possibly even longer. A lot of the stuff I'm barely familiar with, and I would still have to learn a lot just trying to understand how all of this connects together. But that's a super important process. And it's a really important process if you want to connect super advanced fields of studies with people that are just learning and really want to understand how all of this works. With this team also mentioning that they've experienced similar problems with the results from the LIGO, the detector responsible for detecting gravitational waves from collisions of different black holes. There, because of the complexity, a lot of the methods and a lot of the techniques are also not very well explained. But these students are really interested in studying this, so why are we not providing them with everything? Why is everything only accessible to this ivory tower? So maybe something to think about if you are responsible for some of these really complex studies and if you want the students to follow your steps. Alright, enough criticism of the so-called ivory tower. So the studies, both of them, are really interesting, but to be honest, I'm not sure where all of this goes. But more studies like this are required in order to actually see if there is a problem or if maybe these scientists are just being a little bit too cautious. Maybe the original study was correct to begin with. And we'll probably know all of this once more studies come out and once the scientists are able to determine how accurate all of this is.
Hello wonderful person, this is Anton, and today we're going to be discussing some of the recent discoveries about some of the most fascinating objects in our galaxy, the objects we sometimes refer to as the microquasars, which essentially represents some sort of a very dense body, usually a neutron star or a black hole, orbiting a really massive star. And in most cases, this black hole or this neutron star absorbs so much mass from the partner star that it ends up producing huge amounts of emissions and a lot of different effects we've never observed anywhere else in a universe. With the recent studies also discovering something else unusual about some of these microquasars, something that the scientists simulated right here. What you're looking at is actually a comparison between a person's heartbeat and various types of emissions coming from a microquasar known as GRS 1915 plus 105. And according to the scientists, there is a very eerie similarity between the radio pulsations coming from this quasar and the heartbeat of a human being. Which is not to say that this functions like a heart, but it does display a lot of really interesting effects and a lot of really interesting pulsations that in some sense resemble a beating heart. And so in this video we're going to discuss some of these new discoveries, what they actually mean for our understanding of how these objects work, but I guess more importantly, talk about the mysteries of stuff we just don't really get yet. With all of the major studies, as always, available in the description below. But first, I guess let's start with the two objects we're going to be taking a look at today. They're both extremely well known to various astronomers. One of them is known as SS433, which is the object you see right there in the middle of this extremely beautiful nebula, the nebula we sometimes refer to as W50 or Westerhout 50. And as you can probably imagine, the object in the middle is responsible for the production of this nebula. And this particular star system is one of the strangest and most exotic star systems we've ever observed. It's essentially an eclipsing X-ray binary. Here we know that there is an extremely powerful black hole or possibly a neutron star, and this object is orbited by an A-type star that's probably at least 30 times the mass of our Sun. This is also the first ever discovered microquasar, and in this particular case, microquasar just refers to the phenomenon of producing these astrophysical jets and the accretion disk very close to the smaller black hole, something that we usually observe around very large black holes in the center of various distant galaxies that we usually refer to as quasars. So the name itself just implies that these tiny objects seem to possess extremely similar effects to really large black holes in very distant galaxies. With all of this being located at a distance of about 18,000 light years away from us, and all of this displaying really powerful emissions visible from this distance. And there are actually several types of emissions coming from here. For example, there are obviously the astrophysical jets you see right there, with the material moving at approximately 26% of the speed of light. But apart from the emissions from the jets, we're also observing various X-ray emissions from the accretion disk as well, with all of this possessing a periodicity of approximately 13.1 days, suggesting of course that this is how long it takes for the black hole to move around the star. But interestingly enough, there are quite a lot of effects here that were discovered in the last few years that nobody really expected. One of the more intriguing effects is in regards to the astrophysical jets. They seem to be slowly stretching out the entire nebula, distorting it into a somewhat long shape. It's slightly easier to see it from this angle, and you can see that the shape here is actually formed by the jets coming from this object. And because of the orbital periodicity of the system, everything here sort of repeats every 13.1 days. So essentially here everything sort of repeats itself once the star is close enough to the black hole, and once the jets start emitting more material, or alternatively, as the accretion disk starts growing and emitting X-rays. But one of the more unusual discoveries from the last few years is really in regards to what happens at a slightly farther away distance. All of this is so ridiculously powerful that it also seems to affect some other parts of this unusual nebula, specifically at a distance of over 100 light years away from the center. And it's actually something you're about to see right there, somewhere in the left corner. If you look closer, you'll notice that something else is sort of blinking at you from that particular corner. That something is gamma ray emissions coming from the spot that seems to have exactly the same periodicity as the microquasar itself. But this particular spot, first of all, does not seem to align with the jets at all, but also seems to be, at least from the picture here, somewhat independent of the actual binary. Here's actually one of the figures from one of the studies you can find in the description, showing us how all of this looks. So the jets are going this way, that's the nebula, but then in this spot right here, there seems to be an unusual pulsation, or an unusual illumination in extremely powerful gamma rays that follows an exactly same pattern as this microquasar. Although how all of this works and why exactly this happens is really unclear to anyone right now. All of this is definitely connected, but the connection is somewhat mysterious. And because the distance here is over 100 light years away from the microquasar, it's really unclear how any of this is even possible. One of the explanations is in regards to the accretion disk, and possibly the accretion disk causing some of the very highly charged particles to move in this particular direction and then slam into the cloud, producing these gamma rays. But that's just one of the explanations that doesn't have any proof yet. Nevertheless, it's quite clear that this entire nebula seems to be pulsating, with the pulsation being every 13.1 days, and more importantly, seems to be powered entirely by this microquasar in the middle. And so that's of course one of these unusual objects, the object known as SS433. But then we have this other object, also discovered nearly 3 decades ago, known as GRS 1915+105. Another microquasar located approximately 36,000 light years away from the Sun, in this case also most likely possessing a black hole in the middle. And in this case, the scientists actually wanted to directly explore what happens in the middle of these black holes and how these unusual pulsations are generated and what sort of activity is going on in order to create these very strange, very unusual and eerie observations. Here they actually looked at approximately 15 years of data, looking at a variety of light, including the X-ray light and of course the radio light emitted by the quasar, with the main purpose of the study being jets themselves. They really wanted to understand how these jets are generated and what exactly causes them to suddenly appear and to disappear once in a while. And in this case, the data involved approximately 400 different points, both in X-rays and in radio light, with the first major discovery being an interaction between the two. So when the radio light is extremely strong, it seems that the X-rays are extremely weak. And vice versa, when the X-rays are very strong, the radio light becomes extremely weak, which to the scientists in this paper suggests only one thing. All of this energy from the microquasar can only be used for one function, either the generation of the X-rays or the production of radio light that's generated in a slightly different way. And because normally X-rays are usually coming from the accretion disk, whereas radio light usually comes from the astrophysical jets, it suggests that there is some kind of a feedback mechanism happening in the middle of these quasars. And specifically, they believe this works in a relatively simple way. So this black hole that's approximately 12 masses of the Sun, which is actually one of the largest and most massive solar mass black holes we've discovered in our galaxy, absorbs the mass from its partner, the star that orbits around the black hole, losing its mass to the black hole itself. And in the beginning, when the accretion disk is still growing and as a lot of this mass starts to coalesce around the black hole, this is when we start seeing a lot of X-rays. But then, at the end, as the accretion disk becomes smaller and smaller, it starts to release the jets that produce the radio light. And so in between the jets generating one type of light and the accretion disk, or actually more specifically, the black hole's corona generating the other type of light, all of this starts to kind of oscillate, moving around, producing something that actually does resemble a typical heartbeat. Sometimes you'll have a lot of X-rays but not enough radio light. Sometimes it's the opposite, a lot of radio light, not a lot of X-rays. And so in other words, in this particular system, it really looks like the corona turns into jet, and jet then becomes corona once again. And once again, the jets end up producing radio light as they move away from the black hole, and as the magnetic field starts to interact with all of the matter in this particular region, whereas the corona around the black hole ends up producing X-ray energy, as a lot of the electrons present around this black hole accelerate to extremely high velocities and release a lot of X-rays that are then visible from really far away, which at the end produces these unusual observations to some extent resembling heartbeat. But at this point, it's still not really clear how all of this is generated. For example, we know that this is one of the more extreme black holes out there, spinning ridiculously fast, over 900 times per second. So because of this, it might actually create a lot of highly entangled magnetic fields, or magnetic lines, and as these lines snap, they might produce all of this energy we're observing. In other words, this could all be connected to the magnetic lines and the magnetic field around this really powerful black hole. With an extremely entangled magnetic field and magnetic lines, there might be a lot of heating up in the corona, but when all of this snaps, that's when the jets are released, and that's when we observe the radio light. But for now, that's just one of the many explanations that are possible here. And in some sense, this is actually something that most likely happens around very massive black holes in the center of various galaxies, so by studying this, we might be able to understand what happens on the larger scale as well. For now though, this is still a mystery, and a very intriguing mystery, because a lot of these heartbeat-like connections, or a lot of these powerful events that resemble some kind of a cosmic heartbeat, are still extremely difficult to explain, but the fact that they seem to affect regions really far away from the actual binary is even more difficult to explain. So there are quite a lot of mysteries that are still unanswered, and quite a lot of things for us to learn. Hello wonderful person, this is Anton, and today we're going to be discussing some of the new propositions in regards to the unusual phenomena that could be happening in many different black holes out there. Phenomena that the scientists are now exploring using quantum physics, and something that can actually help us understand why certain galaxies have certain features and what happens in certain black holes that spin really fast. But before we discuss the black holes, it's actually important to understand where a lot of these ideas originally come from. They do come from quantum physics, and specifically from this really unusual state of matter, usually referred to as BEC, back, or Bose-Einstein condensate. Something that happens to certain particles of gas as you cool them down. And here these particles have to be what's known as bosons. Usually this is particles of helium. As you start to cool them down, each particle starts to acquire bigger and bigger wave function, and eventually each of these wave functions start to sort of interact and then even joins in, creating one single wave function that sort of acts as a single object. And this is what we refer to as back. This is essentially how the scientists have been studying various quantum effects, and this particular state of matter has even been created on the International Space Station, and we've discussed this in a video a few years ago. But the most important part about this state of matter is that it really doesn't act like classical matter at all anymore. It acts like a quantum wave, and its behavior and its interaction with other stuff can actually no longer be predicted by classical physics. For example, if you do something to this matter and you expect certain type of reaction based on what we know about, well, let's just say normal helium gas, the results are always going to be very surprising. It almost always acts in a way that's only explainable through quantum physics. And because of this, in the last few decades, Beck has been one of the most exciting prospects in order to learn more about quantum physics and to try to understand how things work in the universe. But while studying these Becks not so long ago, I guess around 6 years ago, back in 2016, the scientists discovered a new feature of these unusual Becks, specifically the ones that tend to spin really fast.
So in classical physics, for any kind of a spinning liquid or a spinning gas, we can generally predict exactly what's going to happen to it as it spins faster and faster. As a matter of fact, hydrodynamics and aerodynamics explain a lot of different spinning water and gas particles with extreme precision. But for these quantum particles, for these bags, things are very different. A typical bag, as it starts spinning around, starts exhibiting entirely different structures and entirely different properties, something that nobody could predict until the scientists started to do it. They actually start producing what the scientists today refer to as vortices. But even here, they're not at all similar to the ones we find in the water. They don't act like this at all. Here's a microscopic image of what they really look like. This right here is a spinning bag, spinning Bose-Einstein condensate. And each of those tiny dots you see, those are tiny vortices that appear inside the condensate. But here we're talking about a kind of a quantized vortex that's formed with very unusual patterns, all almost resembling a crystal. Here are some other examples from similar experiments, but with the bag of different size. And so as you can see, this phenomenon seems to appear in any kind of quantum material that starts to spin. And when analyzed, this particular lattice sort of looks like this. It has very specific order, and it does seem to have its own physics that it obeys using quantum mechanics. Today, the scientists believe that these vortices can actually help us explain different phenomena such as superfluidity and superconductivity. But even though the scientists have been studying them for many years, they're not there just yet. You can actually see some other visual examples in one of the links in the description with quite a lot of different recreations of what happens to these bags as they start spinning. But these patterns are not permanent and they do change with time. For example, in this case, it lasted for about 40 seconds before changing into something a little bit different. So these are definitely not permanent structures. But what does it have to do with black holes? Well, when it comes to trying to explain what black holes are, a lot of modern physicists realize that modern physics cannot explain what happens inside the black holes. For example, Einstein's relativity only explains what happens right until the event horizon, with everything after this basically becoming infinity, which in physics just means that we don't really have a good explanation. And so the scientists believe that quantum physics and potentially the idea known as quantum gravity could provide some answers. And what happens inside black holes could be entirely quantum in nature. In other words, black holes could be basically very unusual quantum states of matter. Although naturally at the moment nobody really knows exactly how any of this works. But there is at least one hypothesis, and it does involve the hypothetical gravitons, the particles that some scientists believe could explain how gravity works as well. And in this case, because this is also a boson, it can also create bags, very similar to the ones that I showed you previously, and thus exhibiting very similar effects, especially when it starts spinning. And so a few years ago, the scientists proposed that, well, maybe bags with gravitons could explain certain types of black holes, with the most recent paper that was just released going further, establishing that for a spinning black hole, assuming that it's made out of quantum gravitons, it can actually start forming these vortices as well, with each individual vortex then producing a lot of other additional effects we observe, including very powerful magnetic lines that currently do not have a really good explanation otherwise. Or in other words, the implication here is really simple. Some black holes, or maybe even all black holes, could be these very unusual Bose-Einstein condensates and might possess very similar properties to what we actually discover in these experiments as well. Even showing that a black hole that's spinning can also be described using similar physics, but as a graviton Bose-Einstein condensate that possesses vorticity, implying that this right here is just a bigger version of what the scientists were able to take pictures of before. And if correct, it might provide certain answers for a lot of different mysteries of black holes. First of all, it would suggest that a very fast spinning black hole would be really stable and would not emit any Hawking radiation. In other words, it would not evaporate and would actually remain relatively constant. At the same time, they show that each individual vortex traps a lot of the magnetic field lines, which end up releasing very specific signatures that would be impossible to produce otherwise, and that can actually be experimentally detected by observing certain black holes. Which of course implies that this is not just a hypothesis, it's a testable hypothesis that some future studies could maybe test if very specific observations are made. At the same time, this could also explain why certain galaxies, and specifically certain galactic nuclei, tend to have very powerful magnetic fields that otherwise are kind of difficult to explain. As a matter of fact, a lot of the magnetic fields in various galaxies could maybe stem from these unusual effects from these unusual spinning quantum black holes. But I guess more importantly, it also adds a completely new property to a typical black hole. Today, black holes are generally explained by three different properties. We have mass, we also have charge, and lastly we have spin. So we know that all black holes spin, they all have mass, and they all possess at least some charge. But now there seems to be a fourth one, vorticity. This could also be one of the features if the scientists behind the study are somewhat correct, and if black holes are indeed quantum objects exhibiting quantum features similar to what we find in Bose-Einstein condensates here on Earth. So definitely a pretty exciting proposition, but something that we're not going to be able to test until some of the future very powerful observations from extremely distant black holes that we know most likely spin. So definitely not testable anytime soon. But BACs in general always create so many different surprises. As a matter of fact, we'll discuss some of them in videos you can find in the description below. And so this unusual state of matter can definitely help us resolve a lot of different mysteries in the universe that would be very difficult to explain otherwise, because this right here allows us to test and to observe quantum effects by using actual microscopes and by using larger objects. Something that normally only happens on subatomic scales.
Hello wonderful person, this is Anton, and today we're going to be talking about some other pretty incredible discoveries from the center of our own galaxy, from the region known as Sagittarius A star, animated in this series of images taken over approximately 20 years. With this discovery from just a couple of decades ago, eventually resulting in a Nobel Prize. But as you probably remember from just a few months ago, the scientists from the Event Horizon telescope also recently revealed the image of the central black hole that we believe kind of looks like this, with this becoming one of the bigger revelations of 2022. And we've actually discussed all of the specifics of this image in the video you can find in the description. But during the campaign responsible for the production of this particular image, and during several months of observations of Sagittarius A star region, several other telescopes were also observing, trying to discover something else at the same time. And for some of these telescopes, the data actually took a little bit longer to analyze, and they've only recently started to announce exactly what was found in this region on top of the image that was created. And so very recently, some of the scientists working on the data from the ALMA observatory, the Atacama Large Millimeter Array, released the paper you can find here with something else pretty incredible discovered in the region, something that was previously unseen and took a few months to confirm based on the observations from several other telescopes. There seems to be a blob of gas orbiting around the black hole, and it was actually identified using several different frequencies. And in this case, this blob is orbiting away from the black hole at the same distance as planet Mercury from the Sun, except that a single orbit here only takes approximately 70 minutes. Which means that whatever it is, it's orbiting around the black hole at practically 30% of the speed of light, nearly 100,000 kilometers per second. But what exactly is it, and how exactly was it discovered? Well, first of all, some of these initial observations were actually taken for a slightly different reason. They were taken because there was an unusual flare of X-rays detected coming from the black hole itself, or at least very close to the black hole. And so back then, the scientists really wanted to figure out what this was, and what produced these unusual emissions, or more importantly, if it's actually going to happen again. And these kinds of flares from various black holes have been already discovered around other objects in the X-ray frequencies, but also in the infrared frequencies as well, with the explanation being very hot gas bubbles or hotspots that seem to orbit very fast and very close to various black holes. Although previously these blobs or these hotspots were only visible in the X-rays and the infrared. They have never been discovered in any other frequencies up until now. And now by using the ALMA radio telescopes, the scientists were able to confirm that they are also visible in the radio light, suggesting that these observations, these hotspots or these hot blobs, are very likely the same phenomenon, but produced when the gas that was producing X-rays or the infrared now cooled down, becoming visible at longer wavelengths. Or in other words, these blobs seem to orbit around black holes and seem to be in different temperatures. Sometimes they're very hot producing X-rays, sometimes they cool down producing just the infrared, and sometimes they cool down only producing radio waves. With all of this very likely being produced as a result of various magnetic interactions, as extremely hot gas orbiting close to the black hole interacts with the magnetic field and then ends up producing all sorts of different emissions as a result. And the reason the scientists believe it's magnetic in nature is because of the observations of what's known as polarization. Polarization or polarized light is essentially a direction of light as it comes toward us.
Normally, when the light detected is extremely highly polarized, it implies it came from very highly magnetic regions, such as the ones we, for example, detect around various pulsars, various neutron stars, or other extremely powerful objects with a lot of magnetic lines around them. And so in this case, the light detected from the black hole and the actual emissions were extremely polarized, with the polarization actually changing every 70 minutes. Or basically, the polarization here was rotating at a timescale of just over an hour. With the best explanation, of course, being that this is something that's orbiting around the black hole, and depending on the location in its orbit, being polarized differently because of the differences in the magnetic field in the vicinity of the black hole. And because all of this was also connected to the X-rays here, and because these X-rays were also polarized, it of course implied that all of this was the same event, and possibly even the same kind of a blob. And at some point this blob became very hot, producing X-rays. And one of the reasons why it's actually really important to detect the polarization from the light here is because it then allows the scientists to measure the magnetic field around this black hole, revealing a lot more details about this region and also helping us understand all of the other properties of Sagittarius A star. In other words, it helps us uncover the magnetic field of the black hole and the accretion disk. At the moment, it's not entirely clear exactly what's happening here, but the initial observations have already revealed several important details. For example, there are definitive hints that this black hole is spinning, and is spinning in the same direction as this particular blob. In other words, the rotation seems to be in the same way, with the accretion disk also spinning in the same direction, so all of this is moving clockwise as seen from planet Earth. And more intriguingly, it also allows us to understand the plane of motion of this object and possibly the accretion disk as well. In this case, it appears that we're looking at the accretion disk and of course this blob of matter orbiting around it almost exactly face on, with very likely only about 20 degrees inclination. And this is based on observations from ALMA and also another project known as Gravity, which implies that some of the matter around the disk is orbiting in the way that you see right here. But naturally, what produces these hotspots or how these unusual blobs of matter are formed is not currently known to us. We only know that it's magnetic in nature, but exactly why they form is unknown. And these phenomena don't even have a good name yet. But now the scientists are really hoping to see these particular objects using new observations from the Event Horizon telescopes once again. Because this is the most powerful radio telescope we have right now, it might be able to reveal something else that was missed the first time, and naturally help us understand a little bit more about black holes and the environment around them. For example, not so long ago, I've discussed this new proposition from some of the scientists that suggests that if black holes are quantum in nature, they might actually have these unusual vortex-like formations on the surface, which could be responsible for some of these magnetic lines. And so if all of this then connects to these blobs, the scientists might actually find evidence for all of this and thus resolve the nature of black holes by resolving the nature of these unusual phenomena.